So before that, just our students are there in the group.
Yeah.
To just introduce the chair, and then you have to take care of, Professor.
Okay, then okay. Let us start. I suppose it is almost time now.
Yeah. Now.
Yeah.
Yeah. Students, let us start. Sir.
Okay.
Yeah. Sadhulakshmi.
Yes, sir.
Ready, isn't it? You are ready?
Yes, sir. Yes, sir. I am ready.
So before that, let me good morning, good afternoon, and good evening to all esteemed delegates. Now our today's session is starting. We have in fact, Professor Kumaran Mash is here. And he is always a lighting force or a guiding person or a model to me always. And my student Sadhulakshmi, you please introduce the chair and invite the and help the chair to for the further proceedings of this session, please.
Yes, sir. A warm greetings to all. On to the third day. Moving on to the very first session, we have Dr. M. Kumaran as a session chair. Dr. M. Kumaran is the former principal, head of Department, Nehru Arts and Science College, Kasaragod. Professor served as the course director of Department of Statistical Sciences during the year 2008 to 2016, which is at the campus of the Kannur University. He is a very proficient academician and has produced many PhDs. He has over 100 publications in journals of national and international recognition. I warmly welcome Dr. M. Kumaran to chair this session. Sir, please.
Yeah, thank you, Sedhu Lakshmi. Now, good morning to everybody. A warm welcome once again to all the eminent scholars to the third day of the program. Let me make a brief introduction of the esteemed speaker of the session. Scott H. Holland is a professor of statistics at the University of Missouri and senior research fellow in the Research and Methodology Directorate at the U.S. Census Bureau. His area of research includes dependent data modeling, Bayesian methods, official statistics, survey methodology. He is an elected fellow of the American Statistical Association, elected member of International Statistical Institute, elected fellow of Institute of Mathematical Statistics. Professor Holland is currently co-editor-in-chief of International Statistical Review. He has his PhD from the Texas University. As you know, the topic of his presentation is computationally efficient Bayesian unit level model for non-Gaussian data under informative sampling with application to estimation of health insurance coverage. I hope his presentation will be highly informative, useful, and interesting to all the participants. On behalf of all the participants, I extend a very hearty welcome to Professor Scott. Sir, let me invite you to make the presentation.
Yes, thank you very much. Somebody's going to share the screen, right, so that we have the slides. But I just wanted to say thank you to the organizing committee for having me, give this presentation. And a special thank you for being super accommodating because of the time differences and such with the United States, and trying to make sure that it worked out pretty well in terms of the timing. So this is joint work with a former student of mine, Paul Parker. He's now at UC Santa Cruz. He's an assistant professor, and my colleague at US Census Bureau, Ryan Janicki. Next slide. So this acknowledgement just happens to say that the views are my own and not that of the U.S. Census Bureau. I used confidential microdata, so there has to be a disclosure review board number, and that's on there. So next slide, please. So just to give a brief overview of what I'm going to discuss today. I'll provide a little bit of motivation why one would want to even undertake the type of modeling that we're doing here in this presentation, and then I'll describe the methodology. And once I've described the methodology, I'll show the results of an empirical simulation study. And it'll be more apparent what I mean by an empirical simulation study rather than a model-based simulation study. And then I'm going to show an important application to health insurance estimates here in the United States, those people with health insurance coverages, and then I'll give a conclusion. So next slide, please. Right, so this just talks about the motivation. Next slide. So the motivating goal in small area estimation is that you want to estimate the population county for some subdomain. And that's typically because you haven't sampled enough or at all in those areas and you want to make some estimate. And typically we'll rely on survey data to do this. And the traditional direct estimates or design-based estimates, those can have excessively high variance. And so you might want to use a model-based approach. And some examples are the small area income and poverty estimation and the small area health insurance estimates that are published by the United States Census Bureau. They're actually mandated. Next slide, please. So when you look at small area estimation models, you can think about these in two buckets. You can think about them as area level models or unit level models, and they proceed a little bit differently. So in the area level model, you treat a direct estimate. So you get an estimate from the survey, you tabulate it up. Maybe it's like a weighted sum, like a Horvitz-Thompson estimator. And that's typically the response variable. And usually you incorporate some sort of smoothing through a model. The issue here is that oftentimes policymakers want things to aggregate spatially. So they want, in the United States, we have things called counties, and they might want the county estimates in a state to add up to the state level estimate. And in order to do that, when you have an area level model, you have to use what's known as benchmarking techniques, and that can be somewhat ad hoc. The unit level models treat the individual survey responses as the input to the model, the response variables, and they lead to potentially more precise estimates. And the nice part about the unit level model is you can make predictions for all units in the population. And then as a byproduct of the approach, the estimates at differing spatial resolution, so counties now would add up to states quite naturally because we estimated from the unit level up. So one is bottom-up approach, being the unit level. Next slide. With the unit level model, there's also some challenges, right? Even though they offer some advantages, they present a few challenges. And one of them is they can be computationally demanding. The data sizes are orders of magnitude bigger. So if you think about, like, if I'm modeling county estimates in the state of Missouri, the state of Missouri in the United States has about 100 counties. So my sample size would be 100 there. But if I wanted to model from the unit level, I would be thinking of each person in the whole state of Missouri that enters into my sample as being part of the sample size. The other issue is that the data tend to be non-Gaussian. So in the case of the unit level model, you'll need to account for the survey design, and we'll talk more about this as I progress through the presentation. So next slide, please. Okay, so this is what I mean when I say you have to account for this survey design. Oftentimes when you collect a sample from a survey, the response is correlated with the probability of selection. And so the survey design is said to be informative. And so it's critical to account for this informative sampling mechanism within the unit level model. And to do that, the sample likelihood is often adjusted in some manner. And the reported survey weights can often be used to capture the design information. The problem is if you don't account for this informative sampling mechanism, then you'll end up with biased estimates. And we have a paper that's on the archive, Parker et al. 2019. It's under revision for publication. And it's a survey paper that talks about all sorts of different methodology for accounting for this informative sampling. Next slide. Also, I should note, so I'll talk a little bit about the methodology. You can go to the next slide. I also want to note that the information in these slides, this comes from a paper that was just recently published in Annals of Applied Statistics. So if you want to look online for this paper, it's available, and there's also code that's associated with this paper that's available through the Annals of Applied Statistics website. So one way to account for the sampling design is to use a pseudo likelihood, and so this is just a exponentially weighted likelihood where it's exponentially weighted by these weights wi, and in this case yi is the response variable, wi is the survey weight for the unit I, and then s is just the sample. And then in a frequentist context, you can just maximize this pseudo likelihood to get point estimates of your parameters theta. Next slide. So one thing that was a recent paper, it's a pretty good paper, was in Electronic Journal of Statistics. It was by Savitsky and Toth, and what they did is they showed that you could use this Bayesian, you could use this pseudo likelihood in a Bayesian setting. And if you do this, this pseudo posterior distribution converges to the population generating distribution. So they showed some theoretical justifications for doing this in the Bayesian context. Here, this wi tilde now represents the survey weights after scaling them to sum to the sample size. If you don't scale them to sum to the sample size, you'll get erroneous variance estimates. And then predictions can be made for the entire population using the posterior predictive distribution. And then once you have the values for the entire population, you can aggregate those as necessary to create population estimates. And much more detail is given in the Annals of Applied Statistics paper, and also, like I said, associated code. So if you wanted to try this out, if you had access to survey data and you wanted to try this out, you can do this on your own as well. Next slide. Okay, so oftentimes in official statistics, the data that's collected has spatial dependence because we collect the data over different geographies. It's not surprising. And typically in small area estimation, an area level random effects are modeled through a latent Gaussian process, and that's usually used to capture this spatial dependence. And the reason that that's convenient is the latent Gaussian process is conditionally conjugate when you have a normal response data. So that makes the estimation more straightforward, is that you can sample from these distributions directly. However, in the unit level models, oftentimes, as I indicated, the response is non-Gaussian, so sampling from the posterior distribution can be quite challenging. So there was a paper by Poulsen et al. In 2013, which developed a data augmentation scheme that allows for conjugate sampling when you do like a logistic regression model and you use a latent Gaussian process. So that's what we're going to use here. Next slide. So this just talks about the polyagamma distribution. The interesting thing is this equation 2, but they basically go through the whole theory of this polyagamma for this data augmentation. I won't go through that here. Next slide. So the thing to note is if you have an unweighted binomial likelihood, it has the form of that first equation. If instead you use a pseudo likelihood, as we did in Parker 2020, the form becomes just this same form as that first equation, except now we have something yi star and eta I star, or ni star, which is just yi times wi tilde and I times wi tilde. So the form of 3 is the same as that's given in that previous equation on the last slide. And so we're able to sample from conjugate full conditional distributions using a binomial type pseudo likelihood with Gaussian prior distribution. So the upshot of this, after looking at a bunch of equations, is that we've got a solution to the problem that allows us to sample from the distributions directly, and so it allows for efficient computation. That's basically the upside of it. Next slide. And so what I show here is that you can write down this pseudo likelihood mixed binomial model, this is just sort of the standard of what you would do, right? You would model the logit of the probability of being a 1. And here, this phi that I have in that first equation for the logit of pi, that's a vector that represents either an indicator vector, like an incident vector, like you could think about an area level random effect, or you could think about putting some spatial dependence on that. And then we have some fixed effects, some covariance, and these are pretty standard priors in the Bayesian literature. Next slide. So what I wanted to show in this slide is not like I can flash up a bunch of equations, but what I mean to show in this slide is that in this Gibbs sampling approach, all of the full conditional distributions that you need to sample from have a closed form. And so you can do this pretty readily. This PG up at the top, this polygamma, there's a package in R that's by Nick Polson that you can sample those WI directly. So everything here is pretty easy to sample from. Next slide. Okay, so that's the upside, but the downside is that suppose I wanted to do more than like the state of Missouri, the sample size can become really excessively large for some applications. Like if I wanted to do the whole United States at once, even though I have all of these closed form distributions, it's going to be too computationally expensive to fit the model. And so one popular alternative to Gibbs sampling is a variational Bayes approach. And I put some references down here. And really what you're trying to do there, you have a class of distributions D, which is chosen for some Q star. And then that Q star is the approximation to the true posterior P of theta given X. So what you do is you use optimization techniques to minimize like a Kullback-Leibler divergence between this approximating posterior and the true posterior. And so that's one way of getting around having to sample from this high dimensional setting. Next slide. So one thing that's good is there was this paper in 2003, there's this variational Bayes EM algorithm focuses on a specific case of variational Bayes. And what it allows us to do is factor the approximating distribution into a product of global parameters and local latent variables. And so with this factorization, you can use an iterative approach to minimize the Kullback-Leibler divergence. And then the upside of this is that for models that are fully conjugate, that have fully conjugate full conditional distributions, as well as likelihoods from the exponential family, then you can factor these approximate distributions, and they're of the same class as their corresponding full conditionals. So all of this is just meaning that it provides a convenient framework. Now, I'm not really, I put this algorithm here, and there's just a lot of math there, but my point was we adapted this algorithm from Durante et al. 2019. The takeaway message here is it's really, once you've done all the math to get this algorithm, running through this algorithm is quite straightforward, right? You can do that fairly easily, just even on a laptop. Next slide. Next slide. So the real thing of interest here is to do a multinomial model. And there's a couple of things I'll say at the end that are takeaway messages from this presentation. But the multinomial model allows us to do more than just binary categories. So now we can do several categories at once. And this is a similar model to what we would write in the binomial case, you know, in terms of the model specification. Next slide. From this is one, if you want to sample a binomial distribution, there's a couple ways that you could do that, you know, like this logistic type regression. In the Bayesian framework, you could have used an Albert and Chib type data augmentation framework, which was used as a probit model, or you could use this Polson approach with this polygamma data augmentation. Once I have the binomial model, this paper by Linderman et al. Shows that the multinomial distribution can be written as a product of independent binomial distributions using this stick-breaking representation. So once I have the binomial figured out, I can really easily scale that up to do the multinomial. And so I can do that using the Gibbs sampler or the variational Bayes approach. Next slide. Okay, so this is just rewriting that multinomial model as a stick-breaking representation. There's not much to that, but all the details are in the paper, so I won't dwell on them here. Next slide. Okay, so once you have all this methodology in place, you want to know, how does it work? Is it worthwhile? So we performed an empirical simulation study. And so next slide. So what we do is, rather than creating synthetic data from a parametric distribution like a model, what we try to do is mimic the real survey setting where the truth is known. So what we do is we create an existing survey sample as our population, and then subsample from that population in an informative way. And then we compare the model results to the weighted and unweighted direct estimates. So under an informative sample, right, where the response probability is correlated with the probability of selection is correlated with the response, then under that informative sample, the unweighted direct estimate will have greater bias than the weighted direct estimate. And we would hope that our model does better than the weighted direct estimate as well. Next slide. Okay, so this was motivated by the Small Area Health Insurance Estimates Program. It's an important use of the small area estimation that relies on the American Community Survey. The American Community Survey is an ongoing survey in the United States that replaced the decennial census long form, and it collects a lot of socio-demographic information on the population of the United States. And the goal is to estimate the proportion of individuals with health insurance by county for a number of income to poverty ratio categories. So the number of people within each of these categories, these IPR categories, that's not known, and so we'll have to create these estimates. Health insurance and IPR category simultaneously. And we have different IPR categories under consideration. So 0 to 138% and so forth, all the way up to 400+%. And then within each of those categories, an individual may be categorized as having insurance or health insurance or not. So we view the individuals as falling into one of 10 distinct categories this way. And so we have the CJK for categories, the IPR categories 1 through 5, and then the health insurance indicators 0, 1. Next one. So here we treat the 2014 one-year ACS American Community Sample in Minnesota, state of Minnesota in the US, as our population, and that has roughly 120,000 people across 87 counties. And then to create the subsample, we use something called the Poisson probability, which is proportional to size sampling without replacement. And that gives us an expected sample size of 10,000. And then we use a size variable, this SI, where this WI star is the original survey weight. This is really just creating this informative sample. And then to construct the health insurance estimates by county and IPR category, we fit that pseudo-likelihood mixed multinomial model. Here, the covariates consist of race category, sex, and age category. And then the phi is just a vector indicating which county in Minnesota the individual is in. We did this estimation procedure 50 times, and then we compared the MSE and the bias. Next slide. So what you can see here is that in this case, the variational Bayes does the best in terms of the MSE and the bias, and it takes significantly less computation time. The only thing is that the uncertainty is probably a little bit underestimated because our coverage is only 87%, and the nominal level is 95%. So in both cases, using the markup chain Monte Carlo and the variational Bayes, you can see we do much better than just using the ground-based estimator. Now, the one thing to note here is that this is done, just for Minnesota. We'll see with the real application in a moment here that you can't even do the MCMC for the whole United States. Next slide. So this is just a picture of the mean squared error. In the two middle rows, you can see that's the model-based MC and the model-based variational Bayes. This is really just the empirical mean squared error by county across the simulation estimates for the state of Minnesota. And what you can see is the two middle columns are significantly less in terms of mean squared error. Next slide. Okay, so this is the application to health insurance, the real application. Next slide. So the goal here is to create health insurance estimates by county for these IPR categories for the entire United States, similar to what's done in this AHI program. There's roughly 4.5 million individuals over 3,000 counties, and the computational efficiency of this is a major bottleneck for this problem. Next slide. So the approach that we use is to use that pseudo-likelihood mixed multinomial model again, and we use 10 response categories from the simulation. NR in this case is equal to 1, and we consider the same covariance. Here we use spatial basis functions. I'm not going to go through that, but these PI are basically capturing spatial dependence in this case. And we sample 1,000 independent draws from the variational posterior distribution in order to generate the posterior predicted distribution. And if you do this, you can do this computation time. It was about 17 hours, on a regular sort of laptop. Next slide. So these are our results. This is the direct estimates on the left and the model-based estimates of the proportion of the population with health insurance by county and IPR category for the continental United States. And you can see that we're capturing the trends in the data fairly well, what you'd expect given the direct estimates. Next slide. And then here is the direct and the model-based estimates for the proportion of population with health insurance by county for the whole continental United States. Next slide. And then here is the ratio of the model-based standard errors to the direct estimates. And so you can see that anything below 1 means that the model-based estimate's doing much better than the design-based estimates. And you can see that for the most part, all of the counties across the United States are less than 1. So it gives us assurance that we're doing quite a bit better than the design-based estimators in terms of standard error. Next slide. Now, just to conclude, next slide. We developed a computationally efficient approach to model binomial and multinomial survey data that has informative sample. And we used the pseudo-likelihood approach to account for the informative sampling. We used a Bayesian hierarchical model to capture the spatial dependence, and we did this using that polygamma data augmentation approach. And we do that to construct both the Gibbs sampler and a variational Bayes approach. And then we applied this to the health insurance estimation by county and IPR category. Future work includes some misclassification and multi-type data and also accounting for temporal dependence. Next slide. And these are the takeaways here. I mean, this work really illustrates that it's feasible to use unit level models to create small area estimates for non-Gaussian data, even when you consider the computational complexities. And these estimates that are produced, for such as health insurance are useful for researchers in social sciences, but programs such as SAHI and SAPI are also used to allocate lots of money in the United States for different programs. So they're important things to estimate well. And we've also developed extensions to this type of modeling using deep learning. This highlights how complex surveys can be used to improve estimates. Next slide. So that's where you can reach me if you have questions beyond, I'm happy to answer questions now, but if you have questions that you want to ask me later, feel free to send me an email as well. So thank you.
Good. It is for the participants to ask questions or clarifications. Hello? Hello? Participants, any questions? Clarifications?
Yeah, it's a lot to digest, I know, in a half hour. So if you also want to read the paper and reach out to me, that's cool also.
Sir, for implementing the particular technique, do we have a standard computational techniques, software package?
There's not a software package for this, but there is code that reproduces these results that's available on the website for Annals of Applied Statistics. So it's part of the supplementary material. So the estimation is done in R. So if that's free software, and you can try out the software, and then if you have questions, you can feel free to email me.
Okay, that is fine. So those who are interested will actually use the package for implementation of the technique. Well, that is good. Hello, Satish. I think there are no queries from the side of participants.
Yeah, in fact, Professor Scott has finished in time. Within
Yeah.
yeah.
It was very clear also. He covered all the details and it was very clear. In fact, I had almost like a class itself.
Yeah. Very interesting.
Very nice presentation, sir. Very nice. Very nice. Very clear.
Yeah, useful to students, young researchers, in fact. Isn't it, Professor?
Okay.
Yeah.
So in that case, I hope we can thank the professor for his very nice presentation and novel idea.
Sure, yeah, let us.
Okay. Thank you, professor. Thank you. Thank you very much.
Yes, have a good morning.
Okay.
Bye-bye.
And in fact, first of all, let me to thank Professor Scott for your excellent talk. Also, Professor Kumaran for chairing the session. In fact, we extend our gratitude on behalf of the Department of Statistics, University of Kerala, and the organizers side. On behalf of the organizers, we extend our gratitude to you both, professors.
Okay, thank you. Thank you. Okay.
By the way, I was at this conference, just as an aside, 2015 in Pune. I went to this Wsta. I visited you all and went to this conference about 6-7 years ago. So it was great fun.
Okay.
Thank you, Professor. Thank you.
Okay. Thank you.
Conference.
Okay, Satish, I will join in the afternoon. I have some other.
You mentioned, Professor, you mentioned earlier.
Okay. Okay. I will join in the afternoon. Okay.
You can.
Okay, Scott sir. Bye.
Bye.
Okay, fine.
Now let us, before moving to the next session, we have, I think, some time is there, because Professor Somesh Kumar, we have scheduled the talk at 9:40, and in between there are 5 more, 8 minutes there. It is better to start at the right time, otherwise some.
Yeah, that is right. Yeah, we'll follow the time. So maybe I'll just keep it in the silent mode now, and after maybe around 9:37, 9:38, I'll join.
Yeah. In fact, it is better. Otherwise, some delegates will miss the talk of our talk.
Yeah, sure. Yeah. Okay. I just put myself at the mute and
No. Also, by the time you can, if you want to give any, you can utilize this time to give some message to our youngsters.
Yeah, I mean, actually, it is being held in the honor of Professor P.C. Mahalanobis, and actually, I am a direct descendant of him, academic descendant, because his student was Professor S.N. Roy, and actually, this session is actually is in honor of Professor S.N. Roy. And so he happens to be grand guide of my grand guide.
Yeah, great. In fact, accidentally, I have put your name, and I know some intuition.
So it is actually a pleasure, because I am conducting I'm giving a talk in honor of my ancestor, academic ancestor.
Okay, great.
So one common thing, which like my supervisor, then his supervisor, Professor Maurice L. Eaton. My supervisor was Professor Divakar Sharma from IIT Kanpur, and his supervisor was Professor Maurice Eaton from University of Chicago.
Yeah.
His supervisor was Ingram Olkin, and his supervisor was S.N. Roy. So one common thing which you note here in all the people, like Professor Ingram Olkin or Professor S.N. Roy, they were extremely, you can say, rigorous statisticians. Like whatever theory they gave, it was backed by experimentation as well as by deep mathematical reasoning. If you read their papers, a lot of mathematics is there. Somehow it has come into my nature also. And in my all papers, you can see a lot of theorems, proofs, apart from, of course, a lot of simulations and data analysis is there. But the primary thing is that the theory should be backed by some strong mathematics. So that I have followed throughout my life. Statistics as a practical thing, it's not that you just prove some theorems, but those theorems should have a use. But those theorems should be sound theorems. You should not be just that we take some data and do some analysis and say blah, 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 that, oh, I have got this result. And that is one of the reasons which the statistical young people should learn, that any data is not a statistical data. You talk to 10 people and say something, then you get some information. That is not a statistics. So a statistical data has to be, because R.A. Fisher and P.C. Mahalanobis both were very strong advocates of randomization. That was the primary thing, because of which they could convince the governments. That was the time of British government actually, and it was not easy to convince them that from a small set of data we can actually collect a lot of information and say something about the entire population. So very clearly, Mahalanobis or R.A. Fisher, they emphasized on the randomization. And like I am in IIT, so I get a lot of students from other departments, even faculty members, they come usually with their data and ask for the analysis. So the first thing that I check, that you please don't come after you collect the data. You come before you collect the data. So that's why they put me in their PhD committees, so that I can advise them at the time of registration seminar and all. That is there. So I think this is very important, that the young people, they should know the actual use of statistics. Otherwise, see, we give rise to people who give some adverse comments that you can prove anything by statistics and all that wrong kind of things. So we should not encourage such people. And that can be done only if we are strong enough in statistics. And I must congratulate you that within a short time you arranged such a huge conference. I was seeing that from morning 9 to evening 10 o'clock you are having the talks. It is exceptional actually. Having a conference almost 12 hours, 13 hours per day. It is exceptional, and you have collected people from all over. So I must congratulate you actually.
Thank you so much, Professor, for your compliment and nice words. In fact, we are very much honored through these types of deliberations.
Actually, in IIT system, we get a lot of people, because I am a statistician. Somehow people know me that I know statistics. So students from agriculture, from humanities, from mechanical engineering, from computer science, from electronics and communication, everybody, they come and discuss statistics with me. Like electronics students, so they have some signal data. So they would like to see whether it is Poisson fitted or not. So students from like physics department, so they have some solar observations, like this cosmological thing. So they want to see the scatter, how the scatter is. So then I suggest them that you take in the small area, small spatial dimensions, then it becomes something like a Gaussian. So these things I show them actually. So I think being in IIT system, I developed myself as a statistician. When we study as students, we study Rao-Blackwell theorem and Rao-Kramer inequality without knowing that actually what it will do. But now we know that what it does, the concept of information and all those kind of things. I think that is very important.
It's very true, very true. In fact, that circumstance create, in fact, really build a statistician.
Yeah, yeah. Over last, I think 20-25 years, I have grown as a statistician. I mean, initially I was like writing some papers and all, but now I know what it is.
Great. No doubt that we utilized these moments, these 7 minutes, very valuable. Your advice, in fact, these experiences, sharing these experiences, as well as your advice to the youngsters is very valuable and motivate them in fact, to achieve such professions, as well as build their career and build our statistics to greater heights. Thank you, Professor Somesh Kumar, for your nice words. In fact, before luckily we got this time, and also thank to God, I have put this session as Professor. In fact, put you in this session in honor of our great legend, S.N. Roy, Professor S.N. Roy. I hope now let us come to the session. Let us start the session. My students, Sedulakshmi, you please introduce the chair and then support the chair to do whatever needs for the smooth running of this session. And Professor Somesh Kumar already he will do something, introduce among you. He is even though he is popular all over well, I know. His also his classes are also very exciting. Let us wait for her his words. Sedulakshmi, Neha,
Sir.
Neha, please.
Warm greetings to all. Now we move on to plenary session 4. This special session is in honor of Professor S.N. Roy. I respectfully invite Professor G. Jayashree, Vice Principal of University College of Science, Osmania University, Hyderabad. She completed her MSc in Applied Statistics in 1995 and PhD in Statistics in 2003. She is a life member of Indian Society for Probability and Statistics and Society for Development of Statistics. She is also a member in Board of Studies in Statistics and Departmental Research Committee since 2017. Major areas of research is probability distributions. Dr. Jayashree has published 15 research articles in reputed national and international
editorial board member and reviewer of many national elected member of the International Statistical Institute and National Academy of Sciences, India. Sir has been elected as member of the Executive Committee of the Indian Society for Probability and Statistics, council member of the Forum for Interdisciplinary Mathematics. Sir received the Platinum Jubilee Lecturer Award of the Indian Science Congress Association in 2016. Sir also received Professor from Indian Society for Probability and Statistics in 2022, which was held very recently. Sir, video courses on probability and statistics, statistical inference, and statistical methods for NPTEL and YouTube. And Sir have received millions of views worldwide. He has delivered more than 150 invited lectures or talks in various national and international conferences. Sir has been teaching courses on probability theory, statistical inference, stochastic process, decision theory, multivariate analysis, sampling theory, regression analysis, time series, design of experiments, the University of Ulm and the University of Dortmund. in Germany as a guest professor. Sir also has visited Middle East Technical University, Ankara, University of Wollongong, Austria, University of Colombo, Sri Lanka for delivering invited lectures. He also has interest in contributions of ancient Indians to mathematics and regularly Sir, we are very much honored that you are here, sir. Thank you very much for joining us, sir. Please, sir.
Sir, good morning, sir.
Good morning.
Sir,
Thank you, Professor Jayashree, for giving a very nice introduction with the statistical intervals coming in between of interruptions. So one can find out the distribution of the failures
Network.
in between. So this is a very good example, actually. I mean, like when I start my probability class and when I introduce the Poisson process, I mean, I usually give such examples, actually, because it's very good to give, because suppose I am teaching using electronic mic and this one, so there will be some occasional failures or some disturbances. So I just tell them that you find out the timings and then calculate the distribution of the inter failure timings. So they come up with something, and it is interesting, actually. So I mean, that's what statistics is, a practical subject. Thank you, and let me now I thank Professor Satish Kumar for actually inviting me for this National Statistics Day. Actually, I kept it on first because on the actual day I was having two other engagements, one in IIT Dhanbad and one at Allahabad University. So one I attended online and one on offline. So let me share my slides now. Is it visible?
Yes, sir.
Okay.
yes, sir. Yes, sir.
Yeah, so I'm going to now talk on a parametric bootstrap likelihood ratio test for two-way ANOVA under heteroscedasticity. So this is actually work of my research scholar Anjana Mandal. Actually, from this we have already published one paper which has been accepted, and one paper is under revision. So this is a continuation of that work, because currently we are working on the ANOVA problems under heteroscedasticity and ordered alternatives. So I will briefly give the introduction to the problem, literature review. And so in this presentation, I am considering the likelihood ratio test, which involves calculation of the maximum likelihood estimators under the null hypothesis space and the maximum likelihood under the full parameter space. And from there, we construct the likelihood ratio. Since the distribution is complicated, we go for the parametric bootstrap likelihood ratio. And we have to prove the existence, uniqueness, and convergence of the algorithm for the likelihood ratio test. We will also talk about the asymptotic accuracy of the bootstrap test, and then we do the size and power studies. We have also looked at that if there is a departure from the normality, then whether the test is robust or not, and we implement it on a real example. So in the traditional two-way analysis of variance model, if we have two factors A and B, then testing the equality of effects of various levels of these factors against their natural alternatives is considered under the assumption of homogeneous error variance. So that is the traditional thing. Like if I consider alpha i's are all equal, that is a null hypothesis. Against that, alpha i's are not all equal. So at least one inequality is there. But we consider the cell variances, that is epsilon ij's, to be following normal 0 sigma square. So that is the homogeneous error variances. That is the standard model, but in the practical situations, many times this assumption fails to hold, and therefore if we apply the direct F test, which is for the homogeneous case, it will lead to some erroneous conclusions. So there are people who have studied this. So Zhang 2012, Zhu et al. In 2013 and 2015. They have investigated effects of on size and power values of the classical F test in a two-way. So classical F test I will call CFT in a two-way ANOVA when error variances are not homogeneous. Their simulation studies showed that these tests are not robust for heterogeneous variances. And of course, as I mentioned, that the alternative hypothesis in the classical ANOVA is at least one inequality in the treatment effects. So sometimes we have experimental setup in which the effects of the treatments, they may follow a natural ordering. For example, when we consider the dose response studies, the doses of the drugs are administered to experimental units, which could be animals, for example, mice, guinea pigs or monkeys, etc., in such a way that each successive batch receives increased amount of drug content. So this leads to the increase in the cure rate, survival times, or decrease in the mortality. So one can look at some of these papers by Greenland and Longacre, Huck et al. So they have given the clinical trials outcomes there. Similarly, many times in the industrial design problems, engineering changes are made in equipment or a system so that at each stage the efficiency of the setup is expected to increase. For example, strength of the material. When we consider, say, for example, the material which is used in the car, so to avoid the damage to the car when accident is there, they increase the strength of the material. Fuel efficiency increases, speed of the vehicle increases, for example, in the high speed trains and so on. And so similarly, the new generation of the aircrafts and so on. Similarly, if we talk about, say, computers, so the new things, they increase the computational speed because you have higher level of RAM, storage capacity in the chips. So you have the new methodology of constructing the chips. So therefore, when there is a prior information about an ordering among mean effects of the different levels of factors, it is more useful to test the hypothesis of equality of mean effects against ordered alternatives. So this is a problem that we will be considering. So the general two-way ANOVA model we are considering with two factors A and B, and here we consider without interaction effect. So there is a model with interaction effect and there is a without interaction effect. So in this particular presentation, I will talk about without interaction effect. It is actually called the additive model. So xijU is mu plus alpha I plus beta j plus epsilon iju. So in each cell we are having nij values. That means in the corresponding to ith row level and jth column level, we have nij terms there. So we consider A row levels and B number of column levels. I is equal to 1 to A and j is equal to 1 to B. So here in this model, mu denotes the general effect, alpha is the effect of the ith level of factor A, beta j is the effect of the jth level of factor B, and the error that is epsilon ij's, they are independent random variables with the normal 0 sigma ij square. That means each cell has a heterogeneous variance. So this is the most important departure from the standard ANOVA model. So here we consider the problem of testing the equality of effects of factor A against their ordered alternatives. So we could consider the column factors also, but it will be similar. So we are considering row only. That means H naught is alpha i's are all equal against alpha 1 less than or equal to alpha 2 less than or equal to alpha k against, where at least one is the strict inequality. So cell sizes are taken to be unequal in general. So that means we are having an unbalanced design here. So we have already mentioned that the classical F tests are not robust when error variances are heteroscedastic. So for natural alternatives in one-way and two-way ANOVA models, Bishop and Ludwig's have proposed one-stage and two-stage procedures. And later on, these procedures were extended by Bishop and Ludwig's to a R-way ANOVA model. Fujikoshi considered two-way ANOVA model with homogeneous variances but unequal sample sizes in each cell. And he proposed tests under three types of constants on main and interaction effect. Then Ananda and Veerahandi, they have pointed out that in the two-way ANOVA model, CFT is not robust for unbalanced data and heteroscedastic error variances. So they have proposed an extension of CFT and they call it generalized F test, which that is I am calling it GFT here, for testing homogeneity of the effects of factors A and B as well as no interaction. and they have done the size and power computations of the GFT. We find that this test is very conservative for all sample sizes. That means the for a nominal, say alpha is equal to 0.05, the test achieves much less, like 0.03, 0.04, etc. So it is very conservative test. Then Bao and Ananta, they carried out a more elaborate simulation study for size and power values of the classical F test as well as for the generalized F test for the hypothesis of no interaction effect. And they show that when heteroscedasticity is present under normal populations, then GFT is very conservative and CFT is sometimes liberal. And when we adjust the size levels to the same value, same level, then GFT is seen to have higher power. And both the tests are shown to be a little bit robust under the non-normality. That means they have actually tested for the gamma populations. There are other papers by Wang and Aketas. They have proposed a modification to the CFT when the number of levels and row and column factors becomes large. And they observed that in this case, classical F test does not work well. And Zhu et al., they have proposed parametric bootstrap tests for testing equality of the main effects and no interaction effects in a two-way ANOVA when we have unequal sample sizes and error variances. So this is closer to the work that we have done, but this is for the inequality hypothesis, where we have considered ordered hypothesis in the alternative. Then a two-way ANOVA model is also considered by them. So without interaction and heteroscedasticity, and they proposed a parametric bootstrap test, and they have shown it to be better than the generalized F test of Ananda and Veerahandi. And recently, Zhang has proposed an appropriate degrees of freedom test for heteroscedastic ANOVA, and it shows that it is slightly better than the CFT in terms of size and power values. So all of them, they are considered against the natural alternatives. Now we consider the ordered alternatives, as we have mentioned that why it is important. And initially for one-way ANOVA model, it has been studied by Bartholomew in 1959. And for the known and unequal and unknown but equal variances case, Bartholomew has proposed likelihood ratio test. These tests has been extended by Sharrock to the two-way ANOVA model. And there are some studies under non-parametric setup also by Mansouri 1991, Calagri and Akritas, and Davidow et al. So they have done the parametric as well as a semi-parametric, a non-parametric as well as a semi-parametric setup here. So now let us come to our presentation here. In our presentation, we consider the total unbalanced and heteroscedastic case, and the alternative hypothesis is of the ordering of alpha i's with at least one strict inequality. Now we know that in the ANOVA models, when we consider the estimability of mu alpha I and beta j's, we need additional constraints. So here we put, for example, sigma alpha I is equal to 0, sigma beta j is equal to 0. These are the standard constraints. However, there are some works where they have considered weighted constants like sigma wi alpha is equal to 0, etc. But we are taking the simpler case here. Now for this testing problem, we will develop the likelihood ratio test. And to calculate the critical values of the test, we use the classical bootstrap procedure. So the full parameter space here is consisting of the parameters mu alpha 1, alpha 2, alpha a, beta 1, beta 2, beta b, and sigma 1, 1 square, sigma 1, 2 square up to sigma ab square, where alpha i's are all ordered, and mu is any positive, mu is any real number, beta j is any real number, sigma j, ij squares are positive, and sigma alpha is equal to 0, sigma beta j is 0. And under H naught, because we will put the alpha i's to be equal and sigma alpha is 0, so that part goes away. You are left with the parameters mu, beta i's, and sigma ij squares. Okay. So in order to, so this we call omega naught, and the full parameter space is omega. So in order to find the likelihood ratio test, we need the maximization of the likelihood function over both omega naught and omega respectively. So under omega naught, alpha i's are all equal to 0. So we reparameterize this and we write it as beta j prime is equal to mu plus beta j. So look at this model here. Yeah, so in this one, when alpha is become 0, this mu plus beta j we put as beta j prime. So the model becomes simplified so that you can actually carry out the analysis. So when we consider the likelihood equations, they are double summation xij u minus beta j prime by sigma ij square is equal to 0 when we differentiate with respect to beta j prime. So u is equal to 1 to nij and I is equal to 1 to a. So even if you take this inside, this remains a sum here, because this term can be combined, but I is equal to 1 to a. With each I, this term will change. So this is a collection of terms. It's not a single term here. And the second one is sigma ij square is equal to summation xij u minus beta j prime whole square by nij. So naturally you can see these are complicated equations and we cannot have an easy solution to this. Okay. So using, suppose I consider the mean of the ijth cell as yij and pij as the mean of the sum of squares as pij, then we can rewrite sigma ij square from 4.2. So this is some algebraic manipulation for simplifying the thing. So it becomes sigma ij square is equal to pij minus 2iij beta j prime plus beta j prime square. So if we substitute this expression for sigma ij square in equation 4.1, we get this. So you can easily see that this is a polynomial in beta j prime of degree 2a minus 1 for j is equal to 1 to b. So this is an odd degree polynomial, so it will have at least one real root. So if there is one real root, then it will give the maximum likelihood estimator, and the corresponding values of sigma ij prime square, when you substitute, you get the MLEs of sigma ij prime squares. Sigma ij squares. Now, if there is more than one real root, then we have to consider that value of beta j prime, which is maximizing this one. So that means it will actually minimize product of sigma ij square for each j. So this method of directly solving the equations is very, very time consuming and complicated. So actually computational complexity is very huge. So for practical implementation, it is a very difficult method. For example, if you see, if the number of factor a is equal to 5 or 6, etc., and nij will be different values, then you can see that it will lead to huge complication, because that many number of times you have to add here and the degree is 2a minus 1. So suppose a is equal to 5, then you will have 9 here. So this is a tough task mathematically as well as computationally. So what we do, we propose a Gauss-Seidel type of method, which is an iterative method. Gauss-Seidel method, you know, it is used for solving the system of linear equations, where we use iterative procedure. So one value is substituted in the next one and we revise at each successive stage. But that is the method for the system of linear equation. Here we have a system of highly nonlinear equations. So we actually create a similar kind of method, but we have to then prove the existence, uniqueness, and the convergence of the method. So that we have successfully done here. So we consider the initial values of beta j prime as yj bar, and sigma ij prime square, the initial value is this one. That is just by substituting this value. And we define uij n minus 1 as nij by sigma ij square n minus 1. This is for convenience of calculation. So the nth iterative point of beta j prime becomes sigma uij n minus 1 yij by uij n minus 1. This is summation here. So this is a weighted average of yij's. So the nth iterative point of sigma ij square then becomes 1 by nij sigma xij u minus beta j prime n square. So we stop at step 3 if the two successive differences are less than 10 to the power some minus m. So if we want accuracy up to m significant digits, then we can actually consider this one. Okay. Then second part is the maximum likelihood estimator for all parameter values. That means under full omega. For this case, when we consider MLEs of the means and variances of k normal populations when they are assumed to be normal ordered, then Shi has given an iterative procedure in 94. And he also established the existence, uniqueness, and convergence. And then Shi and Jiang, they have considered the similar results for the MLEs of K ordered normal means when the variances are also ordered. So we utilized the concept that they have given there, and so we are able to prove for our case now. So let us consider one by one here. So under omega, when we are considering the alpha is to be ordered, so we have this alpha I prime is equal to mu plus alpha I, and we want to find the MLEs of the parameters alpha I prime, beta j, and sigma ij square for I is equal to 1 to a and j is equal to 1 to b under the restrictions alpha 1 prime less than or equal to alpha a prime and sigma beta j is equal to 0. So the log likelihood function we are writing, and well, so basically when we are considering when beta j's and sigma ij square are known, then the maximization of L is equivalent to the minimization of this particular term only, because we are considering with respect to alpha I prime. So again we use the same this uij abbreviation, and wi is equal to sigma uij. Then xi prime becomes sigma uij yij plus sigma uib minus uij beta j by wi. And when we use this condition 5.2 here, that is sigma beta j is equal to 0, then the expression in 5.3 can be modified as sigma wi alpha I prime minus xi prime square. So this is the weighted sum of squares here with weights as wi, and the restrictions are alpha i's are all ordered. Then this becomes nothing but the isotonic regression of xi prime with weights wi. So this thing has been discussed in the pool adjacent violators algorithm by Barlow, Bartholomew, Bremner, and Brunk in 1972. So from that result, we can conclude that the maximization will always occur, or the minimization of this term will always occur. So now we may use this alpha I primes to evaluate the MLEs of beta j. So initially beta j prime and sigma ij square are taken, then alpha I primes are calculated. Now we use alpha I prime and sigma ij square to calculate the MLEs of beta j's. So now let us consider the equation in terms of the derivative with respect to beta j, and we write it as a system of equations here. U dot j beta j plus U dot b sigma beta j is equal to Vj. Well, okay, so these things I need not repeat again. So this becomes a system of linear equations, b minus 1 linear equations, and we put it as q beta tilde is equal to v. Okay, and now you know that the solution means that you have to put q inverse here on the right hand side, and this is a very nice way of writing down the matrix for which the inverse will always exist. Okay, so now once we get the solution of this one, so that means I get the MLE of betas, then I put the MLEs of alpha I prime and beta j to get the MLEs of sigma ij square. So this becomes a nice iterative procedure here. So now we discuss about the existence of the MLEs under the constants 5.1 and 5.2. That is these two constants here. So here we show that the finding MLEs is equivalent to finding the supremum of a continuous function on a compact set. So the existence is established here in the next theorem, that is the MLEs of the parameters do exist. I think I will skip the proofs here because it is slightly complicated here. Yeah, I mean, it's somewhat complicated. So we will skip the proof here. It is using the continuity and so on. And then we give a sufficient condition for the uniqueness of the MLEs of the parameters. So here we have on the sample cell variances, that is Sij squares satisfy a certain inequality, then the MLEs uniquely exist. Of course, one may question that what is the practical use of this kind of condition. Then what happens that in the real life situation, because you will be doing you are having the data there. So once we have the data there, then Sij squares will be traditionally bounded by some lower bound, because you don't have infinite set here. So therefore, here for showing the existence, we just use the Hessian matrix, and then we calculate the term which we are able to show that it is always x transpose hx is always negative. So j becomes a concave function. So therefore, the solution exists uniquely. So now we talk about the iterative procedure, which I just now mentioned. In the iterative procedure, we firstly take the initial points alpha I prime as yi bar and beta j as yj bar minus y bar. And for sigma ij square, we consider 1 by nij sigma xij minus yij square. So now using this, we define the uij, which I have already mentioned here, and we define win minus 1. So the nth iterative point of alpha prime, that is the isotonic regression of x prime n minus 1 with weights wn minus 1. Now using this, we revise the next one for calculating the estimator of beta here, or you can say the solution of q beta is equal to n minus v minus vn, and we get the inverse of this one. And then using this, we calculate the value of sigma ij square. So the following theorem states that the sequence of the solutions in the above proposed algorithm converges to the true MLEs uniquely under the condition 5.6. So if the condition holds, then the proposed algorithm converges to the MLE of this under the restrictions that of ordered restrictions, and sigma beta j is equal to 0. So this we are able to establish. I mean, it uses some sort of mathematical analysis which uses the concept of convergence of sequence and Cauchy sequence here, which we are able to successfully utilize. So I will skip the steps of the proof here. It is slightly lengthy here. We have two lemmas which are used here. Yeah, so this is the final result, that the proposed algorithm converges to the MLE of this under the restriction this. So next, we introduce a parametric bootstrap procedure for implementing the likelihood ratio test, because in order to establish a test procedure, we need the critical points. So since the distribution of likelihood ratio test is very complicated, we cannot directly find out. So therefore, we use this parametric bootstrap procedure. So in the parametric bootstrap procedure, of course, so we generate the initial sample given the sample sizes, which I am denoting by this bold X here. This is the complete sample, that is in each cell we are having nij observations. And we consider the each cell sample mean and the sample variances. Then the parametric bootstrap variables are generated from normal 0 Sij square. Okay, so Xij u star is the bootstrap variables I will be denoting. So we consider the bootstrap likelihood ratio test statistic, that is called lambda star, and we reject H0 at level alpha if lambda is less than C star. So C star is the parametric bootstrap critical value. So we give the algorithm for calculation of the critical point for the likelihood ratio test. So what we do, we have the initial sample and then we generate the bootstrap sample from normal 0 Sij square, and then we calculate the MLEs and apply the procedure to calculate the bootstrap likelihood ratio test lambda star. And we consider this ordering here and take the alpha quantile as the critical value. Now this C star values are actually used for simulation purpose. Using the simulation, we have calculated the size and power values of this likelihood ratio test. So that I will tell later on. First, I will want to tell about the accuracy of this likelihood ratio test, this bootstrap procedure. So we are actually able to show that it is asymptotically accurate, and we have actually established the theorem that the conditional distribution of the bootstrap likelihood ratio statistic given the observations and the original observations, the supremum of this, that is the Kolmogorov distance, converges to 0 as minimum of Nij tends to infinity. In order to establish that, we observe that we can consider that likelihood ratio test statistic is location invariant. So using the location invariance, actually we consider the original and the bootstrap samples, they are multivariate normal, and then we take the Kullback-Leibler distance between them and we show that it converges to 0. And if it converges to 0, that means their distributions are converging to each other. We also consider the distribution of the sample variances, they also converge to 0. So when we consider both of them, then we consider, since the likelihood function ratio is a function of the sufficient statistics, And since we are showing for both of them, therefore, the Kolmogorov-Smirnov distance of the complete sample, actually it goes to 0. And then they are continuous functions, and therefore the continuous mapping theorem can be utilized. Next, we have done the size and power studies, because in the bootstrap procedure, we are able to get the critical value, and then we do the simulations. And from there, we are able to calculate the size and the power values. Very briefly, I will just mention that we have taken large number of configurations of A, B, Nijs, mu, alpha i's, beta j's, and so on for doing the calculation. These are parameters which are chosen for size calculation. So we have taken large number of configurations. The configuration, the values have been calculated. As you can see in the table number 3 here, the size values of the likelihood ratio test, in each of the case you can see at the nominal level 0.05, this is very, very close to 0.05. Okay, in all the cases you can see. And therefore, this parametric bootstrap likelihood ratio test behaves almost like an exact test, actually. So we have taken, you can see the next table also, table number 4. And here also you can see that the values are very, very close. So we have taken large number of configurations here. And then we did the power calculations for different configuration of the alpha I values. And as you can see, as the differences between alpha I increases, very rapidly the power goes to 1. It becomes very close to 1. You can see here. So what we have taken the configurations in the form of alpha 1, alpha 2, alpha 3, and so on. And then C values are that C alpha 1, C alpha 2, C alpha 3. So as C increases, very rapidly the power approaches 1. So the tests are very good, actually. Okay, so I will not be reading these things. I mean, as the sample size increases, the powers increase. As the differences increase, the power increases. If the variances increase, the power value decreases. So these are the expected behaviors that we are having. We have actually prepared the R packages for implementation of this. That means if a user is there, then in GitHub we have posted this one, so somebody can utilize it to actually do the thing. Okay. We also considered the robustness of this under departure from the normality, and we considered 6 non-normal distributions. That is the gamma distribution with shape parameter 2 and scale parameter 1, log normal, Laplace, T distribution with degrees of freedom 3, exponential distribution with scale 1, Weibull distribution with scale 1, and shape parameter 2, and so on. So we have calculated the sizes for all the 6 non-normal distributions. And power values are calculated for T, exponential, and gamma. And we then have some observations here. The observations are that the size of the likelihood ratio test gets inflated when sampling is done from exponential, gamma, and log normal, both for the small and medium sample sizes. However, for T, Weibull, and Laplace, it is close to the 0.05. So that means it is reliable test for symmetric distributions such as T distribution or double exponential distribution, and also for Weibull. But for really skewed distributions like exponential, gamma, and log normal, it is not very good. Then we have actually considered implementation to a real data set, and we got the expected result that the likelihood ratio test rejects the null hypothesis. That means the ordering is there. The data is actually on the math score test, I mean writing score test in the mathematics, actually, from some students in the United States, actually. So I think we have also now proposed some heuristic tests for comparison with the likelihood ratio test. And surprisingly, the findings are nice. Actually, even some heuristic test, which is based on the idea of SN-Roy, that is the union intersection test. So we have actually modified that union intersection test to adapt to our situation. And it turns out that that is also quite good. So maybe I will end at this note, this particular. Thank you. If you have any questions, you can ask.
Sir, in the
Any
table.
questions?
Yes, I'm having. Sir, in the table that N7, N, it means sample size. That is the sample size.
Okay.
N,
I'll just explain.
capital N.
Yeah. Let me explain that. Yeah. Are you able to see the tables?
Yes, sir. Yes. What is the N suffix?
Yeah, let me explain. So actually we have to take a lot of configurations here. So what are the configurations? You have N11, N12, N13, N1, N21. So like if I take A is equal to 3 and B is equal to 2, that means there are 6 cells here. It is a 3 by 2 design, 3 rows and 2 columns. So I need 6 values of N11, N12, N21, N22, N31, N32. So those values we are taking as 5, 6, 5, 6, 8, 8, 8, 15, 5, 6, 10, 18, 20, and so on. So we have taken, you can see, large number of such things. Like for A is equal to 3, B is equal to 4, we need 12 values. So we have taken several configurations. For A is equal to 5, B is equal to 4, we need 20 configurations. And similarly, the sigma ij square, because they are also different, so we need those values also. So those values are also listed as sigma A square, sigma B square, sigma C square, etc. So here we need 6 values, here we need 12 values, here we need 20 values. So so many type of configurations are
sir, I
required.
got it, sir.
Yeah, okay.
Sir, in one place, just after this, actually, it is written the P values 4 point something. Is that a typo or something? P values. Yeah, here. P value.
P value is 0.4. Yeah. So that means
okay.
there is no interaction here.
Yes.
Because we are considering the additive model, so interaction should not be there.
Okay, sir. Thank you, sir.
Chair?
If no questions, then let us thank our speaker, Professor Somesh Kumar sir. Topic, a parametric bootstrap likelihood ratio test for two-way ANOVA under heteroscedasticity. Sir has highlighted on the algorithms related to the topic and on also highlighted on robustness study related to the title. Thank you, sir, for being with us. Thank you.
Yeah. So actually, the next session starts at 10:30. Let me just mention here, Professor Manas Ranjan is already there. But actually what happened that Dr. Lakshmikant Patra requested me because he has certain important institute meeting. So he wants to have his talk first. So we will just permute the order and we will have Lakshmikant Patra first and then Professor Manas Ranjan Tripathi, then Professor Yogesh Tripathi and then Professor Nav Kumar Jana. So we will have it in this order. Lakshmikant Patra is listed as the last. He will come in the first. So he has certain meeting. So we will just change that. But I think let us wait for 5 minutes before we start the next session.
Yeah, bro. So yeah, that's fine.
Yeah.
In fact, this session also concluded in time, and we have some more time, 5 minutes.
Yeah, I just maintained the time here. So
very fine, very good. First of all, let me to thank Professor Somesh Kumar for your nice one talk and very useful talk. In fact, today morning we have a feast of inferences through our Professor Somesh Kumar and his team. Next session, that is what he is mentioning, highlighting the session organized by Professor Somesh Kumar. It's an estimating parametric functions for exponential populations, We can hope it is also a good. What he mentioned about the ordering, that is doesn't matter, Professor. It is left to you. You are the organizer as well as the chair of the session, so that you can manage accordingly. By the time, because there is 5 minutes, that means our time also you can utilize for saying something about SN Roy. If you want,
yeah, maybe I can just share, because actually I gave a talk on Professor PC Malanobis on 29th.
Yeah.
So I went through the complete biography of Professor Malanobis. So Professor Malanobis, I mean, apart from like he did a lot of work, but he was also, I mean, one very good thing about him is that he brought up a lot of young people. And he trained them in statistician, and also made them strong statisticians. I mean, he did not just like ask them to do PhD or something like that, but he actually trained them in the real world. So how to do the sampling, how to actually implement the results, and so on. So Professor R.C. Bose and SN Roy were one of his first set of you can say recruitments that he did. Actually, in 1931, he started the officially Indian Statistical Institute. Actually, he became a faculty member in the Presidency College, a faculty member for physics. Actually, he has done his probably his graduation in physics from Cambridge University. I mean, actually, he did from Presidency College. Then he went to Cambridge and he did his 2-year program there, and he came back and he joined as faculty member in Presidency College. So he was actually a faculty member of physics, but when he was in Cambridge, while coming back, he was introduced to this Biometrica journal there, because it was in the library. So when he is studying in the library, somebody told that you can read this. So he found this to be very interesting, and he purchased the full set of Biometrica volumes. And when he's coming, those days they used to travel by ship only in 1915, 16, and so on. So when he came back on the ship, he had a lot of time. He read all that, and then he found that it is very interesting subject. And so then when he came back, he naturally, when he is discussing in his circle, then people will know that this person knows some statistics. So that time, one committee was formed in Calcutta University to propose the examination reforms, and one Professor Brajendranath Seal became the chairman of that committee. He was actually the vice chancellor of Mysore University at that time. So he asked somebody that who can do this job, like comparison, the frequency distribution, and so on. Because till that time only those things were known, nothing else was known, because only Carl Pearson was the professional statistician till that time. So he had introduced the concept of histogram and chi-square test and so on. So then somebody told that Mahalanobis knows something because he has Biometrica volumes. So he requested Mahalanobis that you please do some analysis. So this is actually the start of the statistics movement in India in 1920s. And by 1927, 1928, actually Mahalanobis established a statistics laboratory in his Presidency College, and he made a committee. And in that committee, they proposed the setting up of the Indian Statistical Institute in 1931. And the first of the people whom he hired was Professor R.C. Bose and Professor S.N. Roy. So, apart from few other people, so in 1930s, these two people were taken, and they were good in mathematics actually, both Professor R.C. Bose and S.N. Roy. And then they got the distribution of the Mahalanobis D square, because Mahalanobis D square distance he had proposed, but the theoretical part, Professor R.C. Bose and S.N. Roy, they did. So S.N. Roy became very, you can say, strong in the multivariate, and slowly he introduced a lot of distributions of the multiple and partial correlation coefficients, and all those things he started doing, especially in the testing of hypothesis. When you have the test, then a lot of distributions you require, the null distributions and so on. So he became strong, and of course, you know the later history. In 1947-48, R.C. Bose and S.N. Roy, they went to USA, and they joined there in the University of North Carolina, and Professor S.N. Roy guided many students, which included Professor Ingram Olkin and so on. That is how I come in the lineage. And all the 4 persons in my session, they are my research scholars. So they are also in the same lineage. So now I introduce my first speaker.
Just a minute, Professor. Before, yeah, in fact, I have not given our thanks to our earlier chair, Professor Jayasri. Hello, Professor Jayasri.
Yes.
Thank you, madam, for chairing the earlier session.
Yes, sir.
I forgot on that.
Hello, sir.
Yeah, thank you so much for your support to our activity. And
thank you, sir. Thank you.
Now let us move to the next session. Professor Somesh Kumar just initiating. Students, whether we need to, in fact, this is a continuous session. Anaka, just to give a small introduction to our Professor Somesh Kumar, because some people probably join in between. Just please, Anaka.
Yes, sir.
Yes, please. Just a brief introduction to our great professor, our beloved Professor Somesh Kumar. Yeah.
Good morning. Now we have an invited session titled Estimating Parametric Functions for Exponential Populations. This session will be organized by Dr. Somesh Kumar, Professor, Department of Mathematics, Indian Institute of Technology, Kharagpur. He has research interests in the area of statistical decision theory and inference. He has published more than 100 research papers in reputed international journals and book chapters. He is associate editor, editorial board member, and reviewer of many national and international journals. He is also an elected member of the International Statistical Institute and National Academy of Sciences. We are truly honored to have you here, sir. I warmly welcome you to chair this session. Sir, please take over.
Yeah. So a very good morning to all the people who are attending this session. So this session we have organized on the estimation of the parametric functions in the exponential populations. So of course, like any traditional statistics person, any student of statistics knows that when we talk about a distribution, we consider estimation of the parameters like mean, variance, or the basic parameters like lambda, or in normal distribution we consider estimation of mu sigma square. But as we move to the advanced statistics, the models become complex. So it means that we may not have only one exponential distribution. We may have several exponential distributions, and when we have several exponential distributions, then a lot of situations arise. Like all the parameters may be different, some parameters may be common, some may be known, some may be unknown, and so on. And then in place of mean and variance, etc., we may also consider other parameters, for example, reliability function, hazard rate, and so on, are the measures of information. So this session is actually devoted to that. So me and my set of research scholars, all of my former scholars now, they are themselves now distinguished faculty members in various institutes. So I invite them now one by one, and since Dr. Patra requested me because he has a meeting in his institute, so I have just permuted my ordering of the talks. I welcome Dr. Lakshmikant Patra to give a talk on the estimation of the entropy. So this is one of the parametric functions of an exponential families with the exponential with a location parameter, unknown location parameter. So Dr. Patra is actually, he did his master's and PhD from IIT Kharagpur, and then he worked briefly at KITS University, then Institute of Petroleum Technology. He was postdoctoral fellow at IIT Kanpur under NPDF scheme, and for last 2 or 3 years he is there at IIT Bhilai, and he has published many papers on. Actually, he is a hardcore theory person, and his specialization is basically Stein estimation, the Kubokawa approach, the shrinkage estimation, and so on. And he has published very strong papers. So I request Professor Patra to deliver his talk on estimation of the entropy of an exponential population with unknown location. Dr. Patra. And I request you please restrict yourself to 25 minutes.
Yes. Okay, thank you, sir, for your nice introduction. And today I am very proud that I am presenting something, and my supervisor, or I can say my ideal, was the chair of that session. And as you mentioned that we have done theory and all these things, and all these things we have learned from you and your motivation. Till your motivation is with us, so that motivates us to do hard work, not only in the research field. He also taught us how to lead a good life, peaceful life, and all these things. He is not for my case, he is not my only PhD supervisor. He is my he supervised in my life also. So now I am going to my talk. So I was sharing my presentation. So it is visible to all of you, I think.
Yeah, that's fine.
Okay. So my talk is today is on estimating entropy of an exponential population with unknown location. So this is the outline of my presentation. First, I will briefly state about my problem, and then we will derive first basic estimators, and then we will basically in a statistical inference problem. One area is when some basic estimator is there, finding improvement over that is a interesting problem, and there are lots of studies going on till now. And then we will actually derive 2-3 types of improved estimators over the basic estimators, like based affine equivariant estimators, and then a numerical study and some conclusion on that. So this work I am presenting here is published in statistical papers in 2020, and the co-authors like me and one of my seniors, Dr. Suchandan Kayal, and as I said, my supervisor, guru, and ideal Professor Somesh Kumar. So this is the model here that we have considered a exponential distributions with location parameter mu and scale parameter sigma, and we have as in the introductions I have told that when we go advanced, that not only we concentrate on the parameter like location parameter or scale parameter, but we also concentrate on some parametric function which actually appears in real life situations. So we take a random sample from an exponential distributions. Now our aim is to study the estimation of entropy. So there is in the literature 2 famous entropies there. One is Rayleigh entropy and another one is Shannon's entropy. So Rayleigh entropy was obtained like this ln sigma minus ln alpha by 1 minus alpha, where this is a constant term, and in case of Shannon's entropy, it is 1 plus ln sigma. So this problem actually we will consider with respect to a general location invariant loss functions. Because of that, this constant is immaterial. So this estimation of entropy is equivalent to estimating the parametric function ln sigma, which we denote as theta. So our aim is to here estimate ln sigma, log sigma, and we will try to propose several improved estimators for this parametric function. So for this case, we have considered a general bowl-shaped loss function in the form L delta minus theta. So in the previous literature, actually, the studies were actually done with respect to specific loss function like square root loss function or entropy loss function like that. But here in this study, we have actually unified, and we have taken a general loss function, so L delta theta, where L is not specific. What is that function? We have not told, but some conditions on that L is given. So under this loss function, we will try to estimate the parametric function ln sigma. So before going to discuss the estimation problem, just I want to mention some important applications. As we know that exponential distributions is a well-studied distributions in like live testing situations. So exponential distribution used to model live testing data. And entropy is also treated as a, we can say that is a important characteristics of a distributions like mean, median, and standard deviations. And also entropy provides information about the uncertainty of a statistical model. And as I mentioned, 2 important entropies are like Shannon's entropy and Rayleigh entropy as used in diverse scientific fields like communications, molecular biology, biological engineering, financial studies, and all these things. So because of this several importance, there are several authors which have considered this estimation problem. So one is Mishra et al. They have considered for the case of normal multivariate normal distributions, and then Koyal and Kumar in 2013 considered the estimation of entropy of a exponential population, but with respect to some specific loss function. And then Kang et al., Koyal et al., Seo et al. Also they have also considered the same type of problems. Okay, so I am not going to in detail about this literature review because we have time limit. So now I want to give what are the conditions we have taken for the loss function LT. So the loss function actually we are taking here is twice differentiable, strictly bowl shaped in R, and it minimized at t equal to 0. And the integral involving the loss function LT are finite, and differentiation under the integral signs are permissible. So these two conditions on the loss function is given. Basically, this integrals involve the loss function is finite, and differentiation under the integral signs are permissible. That. So now, when we do the classical decision theoretic problem, always we try to find the complete sufficient statistics, and then based on the complete sufficient statistics, we will try to do the estimation problem. So complete sufficient statistics for this model is x1, where x1 x suffix 1, which is the first order statistics, and s is this statistics summation I equal to 1 to up to n xi minus x1. And it is well known that first order statistics is a exponential distribution and s is a gamma distribution. So now actually we will try to consider here the invariant estimation problem. So to do that, we have considered a affine group of transformation GAB, which is given by this. And under this affine transformation, the problem is invariant, and we have that mu and sigma, the location and scale parameter, goes to a mu plus b and a sigma, and x and s, x1 and s, this complete sufficient statistics goes to ax1 plus b and as. And a form of affine equivalent estimators is obtained like LNS plus c. So these things are basic decision theory, because decision theory like a routine calculation, so I have not included here. So the first result in this direction is that what is the best, because here we have seen that the form of an affine equivalent estimator is given by delta c is equal to LNS plus s, LNS plus c, where c is a constant. Now in this class we will try to find the best one. So the best one is given by basically in this lemma that delta 0 is equal to LNS plus C0, where C0 is the unique solution of this equation. So now, as I mentioned, we have unified the result. So it is like integration 0 to infinity, and here we have not used any expression for L. So if we substitute the various expression of L, we will get different estimators, which is basically best affine equivalent estimators with respect to different loss functions. So first example, we have taken the square error loss function. For that, the best affine equivalent estimator is given by delta 0, 1, which is LNS minus psi n minus 1. And this psi n minus 1 actually comes from this equation 2.1. And where psi is a digamma function, which is nothing but gamma prime x by gamma. So this is the gamma function, that improper integral gamma. So in case of Linux loss functions, we have obtained this again optimal choice C0, which is given by this, and then our best affine equivalent estimator is given by delta 0. So now it is observed that the UMVUE for this estimation problem is LNS minus psi n minus 1, which is nothing but the best affine equivalent estimators with respect to the square error loss functions. So now, as I mentioned in the beginning, this is a basic estimator. This best affine equivalent estimator is the basic estimators. Now our aim is to improve these estimators. So if we can see these two estimators, this LNS minus psi n minus 1, basically this affine equivalent estimators, which is LNS plus C, it's only depend. So our complete sufficient statistics is x1 and s. But here these estimators only depends on the statistics S, but no information. We have not taken any information which contained in the other part of the complete sufficient statistics, which is first order statistics. So this is the idea of Stein actually. Because of that, we say that is Stein type estimator, that without, so we use whole information contained in the sufficient statistics. That is, we try to propose one estimator which is based on the x1 and s, and that will give you the improvement. So to do that, we have considered a class of estimators which is delta phi, which is nothing but LNS plus phi w, and where w is equal to nothing but x by s, where capital X was n into x1. So this is just a simple scaling to to simplify the calculation that nx1. So now as we see this class of estimator 3.1, if we substitute phi w is equal to C0, then we will get the best affine equivalent estimator. So basically best affine equivalent estimator actually lies in this class. Now if I able to find a improvement over this class, then basically our best affine, we will improve the best affine equivalent estimators. So now a basic decision theory is the basic distribution theory. We have defined that U is equal to X by sigma and V is equal to S by sigma. So for that we have the density functions for U and V is given by H and G. So now the first result in this direction that I told, that Stein type estimators is given by this result, and which is actually unified result because we have not used any expression for it. And what it is given? It gives that if we consider a function phi 0 w, which is given by this 3.1, which is like a minimum of C0 ln1 plus w plus B0 when w greater than 0, and C0 otherwise, where C0 is the solutions of, already I told you, I told solutions of this equation, and B0 is the solution of this equation, unique solution of this equation. Then if I consider the estimator delta phi 0 xs is equal to lns plus phi 0 w, then this estimator improves upon the best affine equivalent estimator provided this 3.5. So the proof I have not included here. If anyone interested to see the proof, they can see our published paper. So it involves actually convexity of the loss functions and then using the MLR property, and all these things are there. So now we will consider as the application of this result, we will consider two special loss function. One is square order loss function. Under this is the best like Stein type estimator, which improves upon the best affine equivalent estimator. And under the Linux loss function, this is the you can improved Stein type estimators. So now as we see in the when w greater than 0, this phi 0 w is not a smooth function because it is a minimum is there, so differentiability is a problem. So now we will move into derive a estimator which is smooth when w greater than 0. So because of that it says smooth improved estimators. So again in this case we have considered the general loss functions, and this approach actually first given by in 1974 Brewster-Zidek, and this was applied for normal distribution.
Yeah, I think he has lost the connection.
Let me call him.
I doubt whether it is.
Yeah, I'll just call him to tell.
Yeah.
I think you lost the connection. Oh, computer has restored. Okay, sure, no problem. Yeah, he will rejoin. He's something happened just there.
Oh, okay, bro. Let us wait 1 or 2.
Yeah, just we'll give 2 minutes. Yeah. So this is actually a very nice statistical phenomena which is happening here.
Yeah.
For throughout the conference, if you note down this failures, so one can work on the distribution of the failures as well as the inter-failure times and so on.
Yeah.
Because earlier in my talk, Professor Jayashree was having the I think we can. No, you are still muted. Yeah, you are muted.
Okay, sorry for the interruption. The suddenly.
Yeah, please.
I'm just give me.
As statistician, we expect all these things.
No, we can explain it actually.
So now it is visible, right?
Yes, yes, we can see. Yeah, yeah.
So I was discussing this smooth improved estimator. So now, as I was mentioning that in the case of W greater than 0, the function is not smooth, so estimator is not smooth. So we will use the techniques of Brewster's deduct to derive a smooth improved estimator. So for that, first we consider a estimator of the form delta D, which is nothing but lns plus D, 0 less than W less or equal to R, and lns plus C0, which is basically in a best affine equivariant estimator. Otherwise, like when W lies outside this region. So now if we denote Q d lambda is this expected value, then based on this Q d lambda, we will try to develop a smooth improved estimators. So I am not again going to give the proofs, I am just giving the results, because proofs was a little bit complicated and it's needed again MLR and convexity and all these things, continuity and differentiability. So first result gives actually the properties of Q d lambda, which is nothing but the function Q d lambda is strictly bowl shaped in D for R greater than 0. And if let D lambda R and D0 are the minimizer of these two functions, like Q d lambda and Q d0 R, and this minimizer exists because of this, already we told that it is strictly bowl shaped. So basically it is a type of convex function. So D lambda R and D0 are the minimizers of these two functions Q d lambda and Q d0 respectively. Then there is a ordering between this D lambda R and D0 R, that is D lambda R is less or equal to D0 R for all lambda, and D0 R is an increasing in R. So now using this lemma, we first prove that the estimator, which is actually called a Brown type, first step was called Brown type estimators, then next step was finally we will get the Brewster's deduct type estimator. So now the first estimator was delta D0R, which is nothing but phi RW plus lns, and where phi RW is given by this function, and this estimators improves upon the best affine equivariant estimator delta 0 is equal to C0 plus lns with respect to the location invariant loss function ln. And then in the next step, what we do, we define another class of another estimators of the form that delta D R prime, which is nothing but in this form, that basically we are taking lns plus D when 0 less than W less than R prime, and from R prime to R, we are taking this D0 R, and then otherwise this. And then we define as if a function of the form that phi R prime, phi R and R prime, then using the same argument, like the proof was not given here in this theorem 3.5, the same argument used, and it can be shown that this delta D0 R prime, nothing but that is lns plus phi R prime, is improved upon the best affine equivariant estimators. So now we repeat this process and we will take a finite partitions of this interval 0 to infinity is like that 0 is equal to Rj0 less equal to R less than Rj1 and so on. And then we define a function phi j like this. And if we assume that like when this j goes to infinity and Rjm, that is the last partition point, goes to infinity, and the distance of this maximum distance of this partition goes to 0, this function phi jw converges pointwise to the function phi star w, which is nothing but this function phi star w is equal to this. And then we propose this Brewster's deduct type estimator, which is nothing but delta bz xs, which is lns plus phi star w. And it was proved that basically it is an application of Fatto's lemma, that it proves that the Brewster's deduct type estimators improves upon the best affine equivariant estimators. And this estimator, you can see that this is a smooth estimators when W greater than 0, because in case of Stein type estimator, there is a minimum function, because of that this is lost, but here nothing is there. So because of that, it says that smooth estimators. So again, we have taken the two examples. One is square error loss function, and then another one is Linux loss function. And for them, the explicit expression for the Brewster's deduct type estimator was given. The one is delta 0 1 double star, and another one is delta 0 2 double star. And it is observed that this Brewster's deduct type estimator is a generalized based estimator with respect to non-informative prior, which is nothing but or generalized prior, like pi mu sigma. 1 by sigma when mu greater than 0 and sigma greater than 0. If we take this is the prior, then under this prior, the Brewster-Zidek type estimator is a generalized Bayes estimator with respect to Linux loss function also and with respect to square error loss function also. So next, we will derive a class of improved estimator. For that, we have used the Kubokawa's IERD approach. So Kubokawa's IERD approach was used. So to do that, we have again considered a class of estimators. In the previous two examples we have taken, we have derived particular estimators for which improves upon the best affine equivalent estimator. But for this case, we will try to derive a class of improved estimator. For that, we have defined again class of estimator delta phi xs, which is nothing but this. And we will try to give some condition on this phi w such that this estimator improves upon the best affine equivalent estimator. So these are basic distribution theory. Already I mentioned that this is the density of H and this is the density of density of U and this is the density of V. And we have defined two distribution functions like this. One is Hx lambda, where lambda is nothing but n mu by sigma is this expression, and Hx is nothing but 0 to x Hu du, and where Hu is this. So now this is the result which gives you the class of improved estimator, and this result says that if this phi z, that is this phi w, here we are just we have changed this argument, it is not a problem. So this phi z satisfies these two conditions. One is phi z is non-decreasing and limit of phi z goes to C0, which is C0. What C0? That C0 is the optimal choice of C0 is the optimal choice in case of best affine equivalent estimator. So now when limit phi z, limit z tends to infinity, phi z goes to C0, and this integral inequality is hold, like integral of L prime of this into HZV and GV dV is greater or equal to 0, then this delta phi xs improves upon the best affine equivalent estimators. So now using these two conditions, we will actually try to derive the conditions on this phi z, and then we will see that from this class actually the Brewster-Zidek type also estimator is derived. So now if I take two special cases, one is square error loss function and another one is Linux loss function. For the square error loss function, we have obtained this phi 0 z. So by this inequality, we have obtained that if phi z is limit z tends to infinity, phi z is equal to this constant, and if phi z is greater or equal to phi 0 z, which is nothing but this phi 0 z is this, then the estimator delta phi dominates delta 0 1, that which is the best affine equivalent estimator with respect to square error loss function. So now if we see carefully this phi 0 z, which is nothing but this function, that is D01 in case of Brewster-Zidek type estimators. So basically the boundary estimators of this class is the Brewster-Zidek type estimator. And in case of Linux loss function also similar thing happens. We have obtained again in this case what is that bound phi 0 z, and the limit of this phi z goes to the optimal choice C0, then this estimator delta phi dominates delta 0.
You may please try to complete in 2 minutes.
Yes. So now we have actually done the numerical study to compare the proposed estimator. So we have compared the percentage risk improvement. So here we have given for the first case is square error loss function, the percentage risk improvement, and it was shown that that there is a sufficient amount of improvement over the best affine equivalent estimators. And in case of Linux loss function also we have done the simulation study to show that numerically there were the proposed estimators are improving upon the best affine equivalent estimators. So this is the conclusion. Conclusion is that we have actually proposed, here we have unified the problem of estimation of entropy with respect to general loss functions, and we have shown the inadmissibility of best affine equivalent estimator, UMVU and MLE, proposing Brewster-Zidek type estimator and Stein type estimators. So these are the some references. So this is the Brewster-Zidek paper which is most important, and then this is the Kubokawa's paper, and this is the paper we have published for this work in statistical papers.
Thank you, Dr. Patra. And if there are questions, we can entertain a couple of questions from the delegates who are attending. If there are any questions. Well, I have one question. So this you have done for the exponential distribution,
Yes.
but if we consider exponential type, like if we consider say Weibull or say other distributions which are used in the lifetime, so like for the lifetime studies like extreme value distributions, like exponentiated exponential distribution and so on. So is there a possibility that one can think of doing some analysis for those distributions?
Is for those distributions we can apply these results, but in case of when we are getting like best affine equivalent estimator in a like simple form like LNS plus C0, but for these distributions this form of the complete sufficient statistics is not easy. So maybe that we can apply Brewster-Zidek technique, but Kobokawa type improved estimator is, I think it is difficult. I have tried actually, but I did not succeed.
And my second question is that if we consider the general, like you have taken a location scale setup. So if we take an abstract form of the density function in the location scale setup, then the conditions.
Just I have come actually a few days back. I have Actually,
Okay.
I got that intuition, and then I have written something, but still in process actually.
Okay, because you will need some sufficient conditions.
Exactly, because that MLR and all these things. Conditions is needed.
Thank you, Dr. Patra. So you have taken time and you have some meetings to attend. So thank you very much. Our next speaker is Dr. Manas Ranjan Tripathi from National Institute of Technology, Rourkela. He is again one of my former research scholars. He completed his PhD in 2009, and then he worked as a postdoctoral fellow at Indian Statistical Institute, and then he worked briefly at the Indian Institute of Information Technology, Bhubaneswar, and then he joined National Institute of Technology, Rourkela, where he is now associate professor, and he has also guided some PhD students, and he has published large number of papers in the area of statistical decision theory. His main research area is estimation of parameters under the restrictions of common parameters. So that is common mean, common location, common scale, and so on. He has done many papers on the quantile estimation, and he has also considered order restrictions. So now I invite Dr. Tripathi to present his work, which is on the improved estimation of quantiles under order restrictions for two exponential populations with common location. Dr. Tripathi.
Thank you very much, sir, for giving me this opportunity to present, to deliver my this study. And in fact, I'm really honored to be a part of this session where basically my guide supervisor is the chairman. So this is basically I'm lucky to be in this session. And today, as you said, this is in the honor of Professor S.N. Roy. So that is also coincidentally is a great part for me. So as it is said by the previous this speaker, Dr. Lakshmikanta Patra, sir, means you have been basically inspiration for all of us. Means it's no need to mention basically, but you have helped not only in research but in other aspects of our life. So particularly me also, there is different parts where you have helped. So this cannot be forgotten in life. So I'm really thankful to you, sir, for giving me this opportunity. Now I try to share my screen where I will present. Sir, is it shared? Sir, is it shared?
It is not
No, you have put some infinity mirror, I think. You have to share your window and then share the window and then.
Okay, sir. Sir, screen, sir, I'm sharing.
No, share the window. Share a window and then click on the your presentation.
Okay, sir. So I think now is it?
No. You please keep your presentation open and then share a window, and in that window you click on your this one, then it will come.
Okay, sir. Yes. Now is it visible, sir?
And are you clicking on the share your? Yeah. Now it is coming. Yeah. Please put it in the full screen mode, then it will come.
Now is it visible, sir?
Yeah. And you can click on the hide button. So.
Okay, sir. Actually, sir, I'm a little bit nervous because first time I'm giving this talk before you.
Please carry on.
Okay, sir.
You may take 20 minutes. Yeah.
Okay, sir. Thank you, sir. So the title of my talk is Improved Estimation of Quantiles under Order Restrictions for Two Exponential Populations with a Common Location. And basically, this is a joint work with my PhD student. He has already completed, Dr. Adarsh Kumar Jena. He is assistant professor in NIT Meghalaya. So the outline of the talk is introduction, then some basic results. Then we have certain inadmissibility results regarding the affine equivariant estimators. Then we have simulation study. Then one example where I can show the improved estimators actually improve upon the old estimators. Then concluding remarks. Let me just discuss the model that I am considering. Suppose x1, x2, xm and y1, y2, yn, they are independent random samples. The exponential, two exponential populations, exponential mu sigma 1 and exponential mu sigma 2. Now this mu is basically common, which is the location parameter. To both these populations it is common, and sigma and sigma 2 are the scale parameters. In real life, you can say in real life situations or in life testing situations, this mu is also known as the common minimum guarantee time, which is basically common here. And sigma and sigma 2 are the residual lifetimes. And the quantile of this ith population, that means first or second, is we denote it by theta I. That is that will come in the form of mu plus eta sigma I. For the first population, it is mu plus eta sigma 1. For the second population, it is mu plus eta sigma 2. Where eta is a positive that is greater than 0, which is minus log of 1 month. It is well known. Now, our target is to estimate this theta is when it is known a priori that theta 1 is less than equal to theta 2. That means the quantiles are ordered. We know in advance, and we will try to estimate this theta is. Okay. Now the loss function we will consider, that is the quadratic loss function, that is di minus theta I by sigma I whole square. And we will evaluate the performance of the estimators using the risk functions. What is the risk? Risk is basically the expected loss, expectation of this loss function. Okay. Now coming back to this estimation problem, when the orderings are assumed, it is basically popular, and it has a very long and rich literature in the statistical inference, particularly when the distribution is exponential or normal. Since I will consider the exponential distribution, so I will basically focus on the literature on exponential distribution here. And it has origin, the problem of estimating ordered parameters has origin in the study of isotonic regression, bioassays, reliability, and it arises in various sectors like agricultural sector, industrial, and biomedical experiments. To introduce the importance of the problem, let me just discuss one example here. Suppose we have two brands of mechanical products, and these products have been produced using two different techniques. One is, say, this brand A is produced by using traditional methodology, and this brand B is produced by using, say, modern technology. And the lifetimes of the products, we assume that they are exponential. And it is quite expected that the minimum guarantee period or minimum guarantee time, that is mu, that is common. Why this is common? Because of the market competition. It is natural. And it is expected that since this A, the brand A uses this traditional methodology, the residual lifetime will be less for this A than the residual life of this B. So similar type of, so under this situation, it is quite interesting to estimate the quantiles or the mean lifetimes as required. So some other examples of such nature can be found in the literature, like Jana and Kumar, Misra and Singh, Kaur and Singh. They have discussed similar type of examples where we can go through and see. Now the problem of estimation of quantiles is quite important for this. As I have already told that it has applications in reliability study, live testing, and survival analysis. So for applications of quantiles in some real life situations, one may refer to Lee et al., Gu and Krishnamurthy. Now the estimation of quantiles has been considered by several researchers in the past, particularly lately, for the exponential distribution. And some decision theoretic results was started by Rukhin, 86, Kumar and Sharma. And you can also refer those papers for a detailed discussion on estimation of quantiles from a decision theoretic point of view. Now some further literature on estimating the parameters, when it is known a priori that the parameters are actually ordered. So I may just go through here a little bit. And one of the fundamental book that actually dealt with all these type of problems, that means problems on order restriction, is by Barlow et al. And Robertson et al. So the basic book, that is the book that actually dealt with all these problems, and most of the results basically that dealt with finding the maximum likelihood estimators and improving upon the maximum likelihood estimator using the isotonic regression technique. Now in recent past also, the problem has got attention by several authors, particularly when the underlying distribution is exponential. So I'm just naming those literatures, you can go through, just I am going quickly. So Vijayasri et al., that is Vijayasri and then Gupta and Sharma, then Kaur and Singh 91, Misra and Singh 94. So I'm not going to the details of this literature because this is related to exponential distributions where either the ordering of the location parameters or the ordering of the scale parameters has been considered, and the estimation for the concerned parameters has been done under that model. And most of the results are actually done from a decision theoretic point of view. Now the problem which I consider here has some importance in the sense that some estimators of the common mean, because the location parameter which is common to both the populations, so some existing results for the estimators for the common location parameter, estimators of the common location parameters are available in the literature, and those results can be utilized to consider the estimation of the quantiles. And moreover, the results of Jana and Kumar can also be extended to the estimation of quantile. And under the same model also, Tripathi et al., that is myself, my guide, and Professor Neeraj Misra has considered this model and estimated the common location parameter. Okay, so this is the brief idea about the background of the problem regarding the estimation of the either the order scale parameters or the estimation of the common location parameter when the scale parameters are ordered, or we can say when the location parameters are also ordered, when the scale parameters are unknown, the location parameters are ordered when the scale estimation of the scale parameters, like that. So various combinations of those parameters have been considered. Now coming back to the topic, that is my presentation. As I told that we will consider the estimation of the quantiles, ordered quantiles. So that means θ1 less than equal to θ2. That is equivalent to say that mu plus eta sigma 1 less than equal to mu plus eta sigma 2. Since eta is positive, so this is basically, it's looking that it's sigma 1 less than equal to sigma 2. But most of the results is not straightforward from the previous result. Okay, so let me just go through the basic ideas. As we know that a complete and sufficient statistics for this model is Z V1 V2, where we define Z as the minimum of xi, where xi is basically the sample values I1 to m from the first population. So we take the minimum of that is x1 basically, the first ordered sample, and this this is the first ordered, the first minimum of the second sample actually. Then we take the minimum of those two, that is Z, and V1 is 1 by m xi minus Z I1 to m. V2 is defined like this. So this Z V1 V2 is a complete and sufficient for this model. Now the distribution of Z is basically exponential, where this P is given by this, and the joint density of V1 V2 is given by this. This result is available, and this V1 V2 are not independent, but Z and V1 V2 they are independent, where V1 V2 are not independent. Okay. Now in order to start the basic theory for any problem in estimation, what I understood still now, either in this basic decision theory, or you can say the basic estimator in the classical way. So you have to first find out the maximum likelihood estimator, which is very common. In fact, that is the baseline estimator. So the maximum likelihood estimator for this model, that means for this mu, sigma 1, sigma 2, we can derive and utilize those MLEs, because, and using the invariance property of these estimators, we can find out the MLE of the quantile, because this is a linear function, the quantile, right? So the MLE of this mu is Z, and the MLEs of sigma 1, sigma 2 are V1, V2 respectively. And using these two, we can find out the MLE of the quantile theta I. So let's denote it by, let's denote it's DIL, that is Z plus eta VI. Now, another approach that has been used by Ghosh and Rajampur, that is, we can modify the MLE of this common location. So if I modify that, I get DIM, that is Z minus V1 V2 by M V1 V2. This is the modified MLE for the common location parameter. So using that, I can actually construct the modified MLE of θ1 and θ2 like this plus eta Vi, because we can use the linearity property. Now the UMVs of theta can easily be derived using the property of this complete and sufficient statistic. So one can easily derive DIU. So we denote it by DIU, I for 1, 2, Z plus eta Vi plus eta minus 1 V star, where V star is defined like this. Now these are basically the this basic estimators under this model. Now since θ1 is less than equal to θ2, one can take the advantage of the result of Barlow et al. And using that result, that is the isotonic regression, we can construct improved estimators under this order restriction for the quantiles. So we have done that. So DIR is basically the, we call it a restricted version of the MLEs. Here we call modified MLEs because we are applying it in the form of modified MLE of the common location, where this sigma I hat R is minimum of V1, V2. This is basically the restricted MLE for sigma 1, sigma 2. Minimum of V1, and this is the average of V1, V2, and this is maximum of this for sigma 2. Okay, so these are basically the basic results under this model. Now I have one interesting result here. We prove this theorem. Suppose or say delta mu sigma 1 is of this form: delta of mu plus eta delta sigma I be an estimator of this quantile. Now the loss function B1, that is the quadratic loss function. Let us consider a new estimator of the form delta star, which is delta star mu plus eta delta star sigma I, where this delta star mu and delta star sigma I are the improved estimators over delta mu, and that means these are the improved estimators over their respective old estimators, so delta mu and delta sigma I, original estimators. Now then the risk of delta star mu sigma I theta I is less than equal to risk of this. That means the improved, if you consider improved estimators for this delta, for this mu and sigma I, we can get the improved estimator for this delta, that is for quantile. So this is this happens under this condition: the estimators delta mu and delta star mu are unbiased for mu and must be free from V1 and V2. The estimators delta sigma I and delta star sigma I are unbiased and for sigma I and must be free from Z. So under these two conditions, we can develop quantile using the improved estimators for the common location and the scale parameters. So the proof I am leaving. So then one remark, just we can write after this general result. Tripathi et al. Obtained an improved estimator for the modified MLE of common mean. So under this model, we have already estimators, improved estimators for this common location. Okay, and we have also improved estimators for the scale parameters. So now we can use this result and construct some plugin type of estimators, okay, to get improved estimators for the quantile. Let us see what happens, whether we will be able to get that or not. So that is my remark to what I told right now. Then this is the construction of those estimators. So under the order restrictions on sigma is, so Tripathi et al. Obtained improved estimators for the common location parameter mu. Now also Jonna and Kumar obtained improved estimators for sigma is when sigma 1 less than or equal to sigma 2. So now using those improved estimators, one can use the improved estimator for the quantile. So in the case of a MLE, we have obtained the improved estimator, that is DIL, that is mu L plus eta sigma L. So this is the improved estimator. So what is this mu L or mu dash? Mu dash is the improved estimator over the MLE mu, and sigma I dash is the improved estimator for the MLE of sigma I as given in this Jonna and Kumar. So we can actually utilize those results. But what happens? Let's see. So similarly for a UMB and for the restricted MLE. Now we observe that none of these improve upon the original estimators uniformly, because see, we can construct as many estimators as we want, just plugging the this corresponding estimators. But the thing is that it should improve. Now these improved estimators or these plugin type of estimators actually do not improve upon the original estimators. And why this is not improving, and this the conditions that we have actually shown there, this theorem, the results whatever we have shown, they are not actually agreeing. That is, the conditions 1 and 2 are not satisfied. So that means there is no flaw, that means the result is actually okay. Means since it is not satisfying the condition, so it is obvious that it will not improve. But if there is an estimator which can be formed by using the conditions of that theorem, then obviously we will get improvement. Fine. Now to move forward, we'll actually introduce another larger class of estimators for the quantile and try to improve that class of estimator using some sort of this convexity result. So that result is due to this Brewster and Zedek. So to improve those type of estimators, one has to use that Brewster Zedek type. So let us see those results first. So now we can introduce a group of transformations, say affine group of transformation to our model. Now with this transformation G A B, that's my notation I'm using. So Z goes to AZ plus B and VI goes to AVI. So similarly, the parameters sigma 1 and mu are also this. So consequently, the quantile, that is theta 1, goes to mu plus eta sigma 1. So first we will consider the estimation of theta 1 under the restriction that theta 1 less than equal to theta 2. Okay, in the next part we will consider the estimation of theta 2. Now this problem remains invariant if we consider the loss function this quadratic and the form of the affine equivariant estimator.
You may try to complete in another 5 minutes.
Okay, sir. Theta 1, that is based on the sufficient statistics Z V1 V2, that is Z plus V1 phi. So this is the form of affine equivariant estimator. Now we define two functions, that is phi lower star and phi upper star, for the class of estimators for various values of this eta, for eta less than some m constant and eta greater than. So we have three different conditions under which the values, the functions are defined. So for these functions, one can define phi naught like this, and we have this result actually. So let d phi be the class of affine equivalent estimator for estimating theta 1. The loss function is taken as this quadratic. Let us define a function phi naught v as given in 7. Then the estimator d phi is inadmissible. That means we can find an improved estimator over this d phi, provided that the probability of phi naught v is not equal to this probability that phi naught not equal to phi is greater than 0. So using that result, we have constructed improved estimator over the MLE, which is given by D1 Li, and the modified MLE for the quantile and the UMB for quantile. And those estimators, improved estimator, will be compared numerically. Now, similarly, we consider the estimator of theta 2. So we apply this again, the group of transformations, and the form of the affine equivalent estimator is d psi, find w by this v1 by v2, and in a very similar manner we define the function psi star, psi lower star, and where this psi of rho plus is defined like this. Then in case 2 also, that is eta greater than 2, we define psi lower star, and psi naught is defined or depending upon this is psi lower star. And the theorem tells that let d psi be the class of affine equivalent estimators for estimate theta 2 as given in this 11. The loss function is taken as this quadratic. Let us define a function phi psi naught like this, and then the estimator d psi, that is the affine equivalent estimator, is inadmissible and is improved by provided this probability that psi naught not equal to psi is greater than 0. So the proofs have been omitted, and using this theorem, we have constructed improved estimator over the MLE for this theta 2, that is d2 Li, then d2 Mi for this modified MLE, and the UMVV. We note that enough, though the restricted MLE belongs to the class of estimators d psi, the condition for improving it is not satisfied. Hence, we are unable to improve the restricted MLE using this theorem. So, however, we carry out a detailed simulation study using all these estimators. Now, just need to explain the simulation study. Now, since we have obtained various estimators, that is D1 Li, D1 UO, all the estimators have been obtained. So it is very difficult actually to compare analytically all those estimators, since in many cases it may not possible to handle this theoretically. So we carry out a simulation study. So for simulation purpose, we have actually D1L, D1M, D1U, D1R, DI, D1 Li. So these 5 estimators will be 5, then D1 UI. So all these estimators will be compared numerically. Okay, now similarly for theta 2, we have also considered in various regions of this eta, D2M, D2L, D2U, all these 5 estimators for this theta 2. Now, it is seen that the risk function, if we consider the risk function, that is with respect to the quadratic loss, is a function of tau that can be proved easily. So we carry out the simulation study considering 20,000 random samples, each from two exponential populations with a common location parameter mu and different scale parameters. That means for taking various sample sizes and parameter choices, we have actually compared the estimators. And moreover, we compare the relative risk performances of the estimators, which we defined by RD. Okay, so let's go to the results actually. So these are the simulation results discussion, the details discussion, which I am omitting here. Now we compare taking various choices of eta. So we have taken eta is equal to 0.01, eta 1.5. So these are basically the percentage of relative risk improvement over your this MLE. So this is the results. So it is seen that in most of the cases we are getting improved. Means the relative risk is actually positive. So it basically improves upon the original estimators as well as the estimators, that is the bench line estimator. Now from this we can, so this is for theta 2, we have compared the results, and these are the behavior of the estimators. Just I want to skip this and see the risk values of all the decreases are tau increases from 0 to 1. That's it's actually decreasing as the sample sizes increases. Also, as the sample sizes increases, the risk values of all the estimators decrease. That means this seems shows the consistency. Now the percentage of risk improvement of all the estimators increase when this eta less than this. The percentage of relative risk improvement of all the estimators decrease when eta is greater than 1/m, except for these two estimators. Now for different regions of this eta, we recommend the this use of the estimators. So the percentage of improvement has been seen in some cases 45%.
You may like to conclude.
Actually, there was interruption, so yes. Now the whole idea basically is to propose estimators and compare those estimators analytically and also numerically, and so that which estimator can be used in certain situations. Okay, so this is one example I have considered to support my simulation study, where I have obtained the improved estimators. Here the estimators have been basically obtained numerically. So for theta 1 and theta 2, one can see those estimators, and we recommend to use those respective estimators based on our simulation study actually. Now the conclusion is like this. So we considered the estimation of quantile theta I of the two exponential function under this order restriction, that is theta 1 less than equal to theta 2, and the loss function is your quadratic loss. Now we have obtained some baseline estimators such as restricted MLE. Now using this Brewster-Zedek technique, that is improving affine equivalent estimate, that technique. So we have also improved some of the estimators in certain regions of this certain values of eta. Now the detailed simulation study has been done and the results have been presented. These are the references, and this paper is basically has been published. So this is a published work that is in communication in statistics theory and methods. So I have skipped a lot of things. Sorry, sir, because I really am nervous. I do not know how I presented. This is the first time I presented before you.
Thank you. Thank you, Dr. Tripathi.
Sir.
So we can entertain. Yeah, you can remove your presentation. So we can have just one or two couple of questions.
Yes, sir. Yes, sir. Sure, sir.
Is there any question?
I think I was very fast, so I don't know things.
Okay, maybe I will just ask one question. I think that nobody else is asking a question.
Sir, it's my honor, sir.
So since you have done for the exponential distribution,
yes,
I just
sir.
want to ask, like, is this method, can it be applied to some other location scale distributions? I mean, location scale model.
Yes, sir. Definitely, sir. We can use this model.
So I mean, like, we will have to put some condition on the density function and so on.
Yes, sir. There will be.
The result is in a real result, like you have actually demonstrated the
yes, sir.
improvement.
Yes,
but
sir.
if we do it in the general form, then some conditions have to be placed.
Yes, sir. Yes.
Okay.
We can do that, sir.
Thank you very much. And now we move over to.
Thank you, sir. Thank you very much, sir.
Dr. Yogesh Mani Tripathi. And Dr. Yogesh Mani Tripathi completed his PhD from IIT Kharagpur in 2006, and he has postdoctoral fellowships at University of Graz, Austria, then in Taipei, and then in Canada. He had 3 years postdoc fellowships, and then since 2008 he has been a faculty member at IIT Patna, where he is now associate professor. He has been very prolific, and he has published more than 100 research papers on various aspects of estimation, especially under the censoring, various kind of censoring like type 2 censoring, progressive censoring, etc. So today he will speak on estimation of quantiles of exponential populations. So I welcome Dr. Tripathi to share his presentation. I think we cannot hear you. Either you are mute or you are not connected to, your speaker is not connected.
No, sir, it is audible, sir, to me. Yes, it's audible. It's audible.
Yeah, we can hear you. Yeah. Yogesh,
yes, it is audible. Audible. Yes, it's audible.
No, I can hear you, but I am not able to hear Yogesh.
Oh, but
I can hear you. I am able to hear Professor Satish Kumar also.
Yes, yes, Yogesh bhai, it's visible, sir. Yes, it's visible.
You can make it full screen.
Sir, you can leave and rejoin, sir.
Yeah, okay. That's better, so that you audible to everyone.
Yeah, okay.
Some technical problems may be there. Professor Somesh.
Yeah, I will leave and rejoin.
Yes, sir. Yes, sir. Please. हाँ दिख रहा है हाँ दिख रहा है हाँ जोगेश भाई बोलिए ना आपका ठीक से सुनाई दे रहा है बट सार को क्यों सुनाई दे रहा है नहीं दे रहा है पता नहीं यहाँ तक तो आ रहा है NIT राउरकेला तक 4 एक्सपोनेंशियल डिस्ट्रीब्यूशन है पूरा खत्म हो जाएगा एक्सपोनेंशियल Sir, you are not audible. Sir, you are not audible.
Yeah. I can hear all of you now.
Okay,
yeah,
sir. Okay,
yeah.
sir. Okay, sir.
Yeah. Please try to finish by 12 o'clock because we have to maintain time. Yeah. Okay. Thank you. Yeah.
We can't hear you, I think. Whether it is a problem.
Yeah. He's audible. Yeah. He's audible, and yeah, you can continue, please. Yeah.
Yeah, continue, please.
with respect to mu equal to 0, sigma equal to 1. So basically what we have done throughout this work, we have tried to improve this estimator delta naught star by proposing a new class of estimators. So so basically if we define, if we take the loss function to be quadratic in nature, that is LT is equal to T square, then this constant A naught is like this, eta minus 1 by n divided by m. So accordingly you get your estimator like y plus A naught z, where A naught is this number, and we denote this estimator like delta naught 1 star. So delta naught 1 star is basically MRE of mu plus eta sigma under the loss function LT equal to T square, which is quadratic in nature. And so this is kind of a symmetric loss function. We have also considered one asymmetric loss function, and it is commonly known as Linux loss function, and it is defined like LT equal to exponential Wt minus Wt minus 1, W not equal to 0. So W is basically loss parameter here. And in this case, we obtain A naught like this, 1 over W1 minus exponential minus W eta by m divided by 1 minus W by n whole power 1 by n. Of course, W less than n. So for this particular choice A naught, we have this MRE estimator of mu plus eta sigma under Linux loss function. So this is our main result. So what we do, we try to improve that estimated delta naught star in terms of its risk behavior. For that, we consider the following class of estimators denoted by delta xi. Delta xi is basically z into xi t, where t is y by z, and then we have this following inadmissibility result under LT loss function. So this is the result under which we are able to improve delta naught star. So the estimated delta xi naught, so we have already defined delta xi as z into xi t. So the estimated delta xi naught with xi naught t given by t plus minimum of A naught t plus 1t when t greater than 0. Otherwise you take the base choice t plus A naught when t less than 0. Improves the estimated delta naught star, which is our benchmark estimator, for estimating mu plus eta sigma under the loss function LT, provided equation 3 holds. Okay, so this equation will give us the condition on eta for which you get the result. Of course, P is evaluated from equation 4, and the variable S is defined like summation I equal to 1 to m Ri plus 1 xi. It has gamma distribution with parameter m comma sigma. So 3 will give the equation 3 will give us the condition on eta for which you get the result, for which the MRE estimator is improved by the proposed estimator delta xi naught. So a proof I will skip. It follows the idea of Stein, 1964, famously known as conditional risk analysis. So using his idea, we are able to prove the result. So I skip the proof, and here is one remark listed, that if you see the main result, so basically if you look at xi naught t, the way it is defined, so basically what we are achieving here, we are better estimating mu plus eta sigma by estimating sigma in a better manner. Okay, so we are not getting any improvement over mu. So whatever improvement is coming, it is coming by estimating sigma in a better manner. So that is what listed in that remark. The estimated delta xi naught in the previous theorem can be written like this: y plus ps when t is between 0 to A naught by p minus 1 over n. Otherwise, we take the base choice y plus A naught z. So here PS is the best scale equivalent estimator of eta sigma under the loss L delta minus eta sigma over sigma when mu is 0. So when we want to improve the MRE of mu plus eta sigma, the improvement is due to the better estimation for eta sigma under the proposed laws. So just for example purpose, if we take here xi, if we evaluate this function xi naught by considering LT equal to t square, when we take quadratic loss function, then we get some explicit result, and that is what listed there. So for quadratic loss, LT equal to t square be from 3. The equation 3, if you recall, that will give you the condition on eta. So for eta greater than, so the 3 gives us the condition that eta is greater than m plus 1 by n. And also we have already observed that the best choice under LT equal to t square for that constant a naught is like this, eta minus 1 by n over m. And from 4 we get p equal to eta over m plus 1. The improving estimator under LT equal to t square over MRE is now listed in this corollary. So it is like the estimator delta naught 1 star is, so delta naught 1 star is basically MRE under LT equal to t square, and it is inadmissible for estimating mu plus eta sigma under the quadratic laws provided eta greater than m plus 1 by n. And the corresponding improving estimator is given by delta xi1, where delta xi1 is listed here. It is y plus eta over m plus 1 z plus ny when t is between that range 0 to m plus 1 eta minus n inverse over eta mn minus 1 by n. So these are classical problem in statistical literature. Many authors have considered such type of inference problem. So the case m equal to n, that is for the complete sample situation, we get the corresponding result of Rukhin and also Petropoulos and Kouroulis 2001. So in this corollary, if we replace m by n, we get the corresponding result of Rukhin 1986 for the complete sample situation. As I told in the beginning that most of the time we take two different types of loss function to illustrate the proved result. So here, if you take this Linux loss function, then the best choice a naught is given by this function under the condition w less than n, and then you also get the value of p from equation 4. And if you want the condition on eta for which you get the improved estimator, then eta is greater than here minus m plus 1 by w ln 1 minus w by n. So w, which is the loss parameter, so this eta greater than part is a function of w. You have to analyze this. So its behavior is like in the range minus infinity to n. It increases from 0 to infinity. Okay, so you have to get one w naught for which you get the improving estimator for any eta greater than u. Here we are not getting any restriction on eta. Eta is greater than h naught w. Basically, it is, eta is. So result holds for any eta greater than 0 here. Only thing we have to fix our w. So for that, what we do, we take help of numerical computations, and we try to solve this equation h naught w naught equal to eta, and accordingly the improving estimator is obtained for the case w less than w naught. Remember, w greater than w naught, hopefully eta will not be greater than h naught w, because the h naught w basically it blow up, it goes up to infinity. Also, this Linux loss function actually it behaves like a quadratic loss function if w is close to 0. So if w is close to 0, basically this result will be like this only, this corollary, because this is for quadratic loss, and here if w is close to 0, then it will be like quadratic loss. So basically this will be like this only. So next, what we have done, we have extended this result, the main result for k greater or equal to 2 exponential populations also. So basically it is like same scale and different location parameters population, and then accordingly you get the sufficient statistics here for mu j and sigma j equal to 1 to k. Again, you will notice that we will notice that yj and zj are independently distributed respectively as exponential and gamma distribution. And in fact, one may also refer to this Balakrishnan et al. And Kramer and Campus for these results. So based on this introductory computations, we can obtain the required result where we get the improving estimator for this case also. So this is the main theorem. I will not read it. It is exactly like the previous theorem. Only thing is that this is proved for k greater or equal to 2 population with same scale and different location parameters. Again, here equation 13 will give you the condition on eta for which you get the improved estimator. So previous result, if you see, it gives improvement for the case when I mean eta is large. Basically, we are saying that eta greater than something, and then we get the improving estimator. What about eta less than 0? So here we are not able to get any general result for LT. So what we do, we try to obtain improving estimators of mu plus eta sigma for small values of eta by separately considering the loss function. So first what we do, we take up quadratic loss function and obtain the following result. So again, same thing, we consider estimation of mu plus eta sigma under the quadratic loss function when data are observed using progressive censoring. And then this particular estimator delta JS defined in the following manner: JS t equal to maximum of t plus e naught, m plus 2 by m plus 1 t, t less or equal to minus 1 by n. Otherwise, you take the MRE estimator. So this estimator delta JS, it is better than the benchmark estimator delta naught 1 star when eta is in this range, 0 less or equal to eta less or equal to 1 over n m plus 1. So here again, if you put the
try to complete, because
yes sir. So similarly, we have obtained the results for Linux loss function also. So this parameter w, it is non-zero. So we have separately considered the cases w greater than 0, w less than 0, w is negative or w is positive, and accordingly we have obtained improving estimators of mu plus eta sigma when eta is basically small. Okay. So this is for w negative, this is for w positive, and so this is in this part what we have done, we have considered estimation of mu plus eta sigma under, you can say, restricted parameter space. So basically now we take up mu to be non-negative. Remember, original range of mu is like it is any real number, but here we take mu to be greater than 0, and then we consider estimator of mu plus eta sigma, and we basically take a estimator of the form delta g, where delta g is delta naught star plus gt comma z, t is y over z, and delta naught star is that benchmark estimator. And we put one condition on the function gt, that when t goes to infinity, gt should be 0. So this is the Bayes. First we discuss the Bayes estimator here. So the form of Bayes estimator is like delta g naught, which is delta naught star plus g naught t into z, where g naught t can be computed from the equation 15. So this is the generalized Bayes estimator with respect to the prior distribution pi mu sigma, which is 1 over sigma, mu greater than 0, sigma greater than, that is the parameter space. And this is the main result here. So basically what we do, we provide some sufficient condition on the function gx, under which we get the improving estimator of mu plus eta sigma. And this is just like you can say an example of this previous result. So this is true for any L satisfying those conditions. L0 is 0, L is strictly increasing for t greater than 0, strictly decreasing for t less than 0. If you consider real t equal to t square, then you get some explicit estimator of mu plus eta sigma, improving the benchmark estimator. And in the remark, we are able to observe that this G condition Gx greater or equal to G naught x. So this boundary estimator delta G naught x, it is actually our generalized Bayes estimator of mu plus eta sigma with respect to the prior pi, which we have defined earlier. So from here we are able to observe that the generalized Bayes estimator of mu plus eta sigma, mu greater or equal to 0, basically dominates the MRE estimator delta naught star under the squared error, under any loss function. Here we have mentioned squared error loss function. So in conclusion, we have obtained inadmissibility of minimum risk equivariant estimator of the quantile of an exponential distribution under an strictly convex loss function in presence of progressive type 2 censoring. And so we develop our main result, which gives improving estimator for large eta. Separately, we have obtained the result for small eta also, and a new class of estimator is also proposed using that unified approach of Kubo-Kawa. And subsequently, we are able to show that generalized Bayes estimator improves the MRE estimator for estimating mu plus eta sigma when mu greater or equal to 0. So these are the some relevant references which we have used in this work. And thank you everyone for your patience listening.
Yeah, thank you, Dr. Tripathi. So if there are any questions, any delegates want to ask any question?
So I have just one question. So
Yeah,
can we extend this result to some other censoring scheme?
I mean, we have tried.
Is there any difficulty? So
for past 6-7 years, I have not worked on this type of problem. So not much literature known to me.
okay.
I mean, at least computationally we can work.
Yes, computational. That's what I'm trying actually, but
theoretically
the problem is, yeah, sufficient statistics.
Thanks to our supervisor, many researchers even do not know the literature on quantile estimation.
Yes.
I was talking to one or two people. He rejected. I even don't.
In fact, I think means with our sir. I have many.
He is working on different problems.
Quantile estimation of quantile. Actually, mostly.
Even if you see in India, if you leave, sir, then how many people you will find?
No.
Quantile estimation. Sir can tell.
Okay. Yeah. Okay. Yeah. So I mean, this is an interesting problem, and there is a lot of current literature I have seen. There is a non-parametric quantile.
Exactly, non-parametric they are doing.
Non-parametric, yes, sir.
But not parametric.
Okay, so I think we will move to the next speaker. Yeah,
okay,
because time is short and there is another session subsequently. Yeah,
sir, I will leave. I have one work, sir. So
okay. Thank you very much. Yeah, you can unshare your screen. Yeah.
Yes, sir. Yes, sir. Stop.
Yeah. So our next speaker is Dr. Navkumar Jana. He is from Indian Institute of Technology, ISM Dhanbad. He completed his PhD in 2017, and then he was faculty member in the National Institute of Technology, Meghalaya, and then after some time he joined IIT ISM Dhanbad. He works on the problem of classification, especially under various kind of restrictions, like restrictions of equality, restrictions of inequality. And recently he has also worked on the directional distributions and also some applied kind of research problems. He has applied his results to some medical problems also. So I request now Dr. Jana to make his presentation on estimation of ordered scale parameters of two exponential distributions. Since we are slightly late, kindly restrict your presentation to just 20 minutes.
Okay, sir. Thank you very much, sir, for introducing me. And I also like to thank to the organizer of the conference for giving the opportunity to present our work on estimation of order scale parameter of two exponential distribution with a common location parameter. This is a joint work with my supervisor, Professor Somesh Kumar. So since already many examples on exponential distribution and related problems has been given, I will directly go to the model. So in these presentations, we will consider two exponential distributions where the associated probability density functions is given by 1. We see that here we have considered the locations parameter mu as a common for both the populations, and the scale parameter sigma 1, sigma 2 are unknown, and they are different. We also assume that the scale parameters followed the ordering sigma 1 less than equals to sigma 2. Now, in reliability and life testing situations, mu represents the minimum guarantee lifetime of an equipment, and sigma inverse represents the failure rate. Let me take one example where these types of restriction arises in the context of exponential distribution. We know that exponential distribution can be used to model the lifetimes of the batteries produced by any manufacturer. Suppose there are two types of batteries and the lifetimes of the batteries follows exponential distribution with a common guarantee time, with minimum common guarantee time. Now, let's say the lifetime of the first type of battery is less than equals to the mean of the populations are ordered. So if you assume mean of the populations are ordered, so that will leads to the condition mu plus sigma 1 less than equals to mu plus sigma 2. Or even if we consider that the failure rates are ordered, here sigma inverse because it is representing the failure rates. So sigma inverse are ordered, it will also essentially lead to the restriction like this. Now, in the restricted space estimations problems, there are many literatures. We will mention a few which are closely related to this work. Paul and Sina and Jean and Paul, they have derived the estimator of the common location parameter mu and compared the risk of the MLE, modified maximum likelihood estimators, uniformly minimum variance unbiased estimator. In terms of treatment closeness criteria, they have compared the estimators. Mohapatra and others, they derived MLE, UMVV of the scale parameters of K exponential distributions. Recently, there has been also many studies on these problems, and Tripathi and others, they have considered this model under the ordering sigma 1 less than equals to sigma 2 and derived the MLE, UMVV and base scale equivalent estimators of mu. However, the estimation of the scale parameter sigma 1 and sigma 2 has not studied under the order restrictions. So we will be considering estimation of sigma 1 and sigma 2 in this presentation. Now, here xi is a random sample from the populations pi I, and based on these random samples, we have defined zi, ti and z. Then the maximum likelihood estimators of mu is x, UMV is delta u, and modified MLE is delta mm, which is derived by Ghosh and Rajmanpur. We note that the statistics z, t1, t2 is a complete and sufficient statistics for the parameters theta, which is mu, and sigma 1, sigma 2. Now the density of the random variable z and t are mentioned here. The basic estimators for the scale parameter sigma 1 and sigma 2 are mentioned here. Now, and when this ordering is present, the maximum likelihood estimator of sigma 1 and sigma 2 are sigma 1 RML and sigma 2 RML respectively. We have derived the uniformly minimum variance unbiased estimator of sigma 1 and sigma 2, and they are sigma 1 u and sigma 2 u respectively. Now, under the loss functions 2, which is an invariant loss function in estimating sigma 1, when this ordering is present, we consider mixed estimator sigma 1 alpha tilde and sigma 2 alpha tilde for the estimate for the parameters sigma 1 and sigma 2. We note that if alpha equals to n1 by n1 plus n2, then sigma 1 alpha tilde is the restricted MLE of sigma 1. Similarly, for alpha equals to this value, sigma 2 alpha tilde is restricted MLE of sigma 2. Now the risk of the maximum likelihood estimator and that of the mixed estimator has been compared, and according to this statement that the risk of the restricted MLE and risk of the mixed estimators delta 1 alpha and that of the second parameters are less than that of their maximum likelihood estimators. We have derived the admissible class of estimators for the scale parameter sigma 1. Now under the scale group of transformation GS, we notice that the problem of estimation is an invariant decisions problem, and we derive that the estimators C star T1 can be improved by the estimator CT1 if C less than C lower star. And within the class of estimators of the form CT1, where C lies between C lower star and C upper star, the estimator CT1 improves the estimators of the forms. This class of estimators, it forms an admissible class of estimator in estimating sigma 1. Similarly, in estimating sigma 2, we have derived similar results. So this is an admissible class of estimators in estimating sigma 2. Now we have derived the affine equivalent estimators for sigma 1. Again, here we notice that under this affine group of transformations, the form of the affine equivalent estimators are of the form T1 phi of V, where V is T2 by T1. And if we define the functions phi in this particular phi 1 in this particular way, then the affine equivalent estimator T1 phi V will be improved by the estimators T1 phi 1 V, provided this condition probability of delta phi 1 not equals to delta phi is positive in some part of the parameter space. As a consequence of the previous theorem, the improved estimators improving over the uniformly minimum variance unbiased estimators is delta 1 AU, and that improving over the restricted MLE is delta 1 ARM. Similarly, in estimating another scale parameter sigma 2, we have derived an inadmissibility result. So this also says that the affine equivalent estimators for the scale parameter sigma 2 can be improved by these estimators T2 phi 2 V. As a consequence of this result, we have written the improved estimators delta 2 AU and delta 2 ARM improving over the UMV and restricted MLE, and this is again an estimator where delta 2 AM is the estimator improving over the MLE. We have also derived admissible class of estimators of the ratio of the scale parameters, that is sigma 1 by sigma 2, and the class of estimator CT, where C lies between C lower star and C upper star, and C lower star and C upper star is defined here. This forms an admissible class of estimators in estimating rho, that is the ratio of sigma 1 by sigma 2, and that is sigma 1 by sigma 2. We have also considered scale equivalent estimations for the parameter sigma 1. So here is an inadmissibility result for estimating sigma 1. The scale equivalent estimators of the form T1 psi of UV would be improved by the estimators T1 psi star, provided probability of psi star not equals to psi is positive for at least some theta. And as a corollary, we have mentioned the improved estimators improving upon the UMVV, MLE, and restricted MLE. Similarly, these are the improved estimators for the estimator of this is a result for estimating sigma 2, and as a consequence of this result, we have mentioned the improving estimators of delta 2. So this is improving over the UMVV. We will see that in case of finding scale equivalent estimators, that we cannot further improve the restricted MLE of sigma 2. Okay, this is the improved estimator improving over the MLE and the restricted MLE. Now, considering the non-informative priors for sigma 1 and sigma 2, we have derived the Bayes and generalized Bayes estimators. The form of these estimators are not in explicit form, but they can be evaluated using simulations procedures. So these are the generalized Bayes estimators, and this is an estimator based considering the inverse gamma prior for sigma. Now here we are considering percentage risk improvement of the estimators delta I ML, delta I RML, all the proposed estimators over the uniformly minimum variance unbiased estimators. Now here we mentions the percentage risk improvement of the estimator of sigma 1 for sample size n1, n2, while n1, n2 both are 4, and mu is 0.5. We can observe from this table that almost all the cases we are getting improvement over the uniformly minimum variance unbiased estimator, that is delta 1U. Now here is the risk comparisons of the estimators of sigma 1. So here we can observe that all the estimators are improving over the uniformly minimum variance unbiased estimators, and among all the estimators delta 1 AU has lowest risk when rho is rho is close to 1. I mean, basically in this region it is improving, delta 1 AU is improving. And we also observe that that the other estimators, for example delta 1 RML, it is also close to this estimator delta 1 AU if sample size is large, but that is not included in this pictures. That was just an observations. If sample size is large, so that was the observation. Now in case of estimators of sigma 2, that is the second scale parameters of the second population. So here the estimators delta 2 RML has uniformly lowest risk as compared to other estimators. So that means the restricted MLE we cannot improve further in this case. So the main findings we have written here that to estimate the scale parameter sigma 1, the restricted MLE delta 1 RML that would be suggested for small values of rho, and the estimated delta 1 AV for moderate and large values of rho. We have observed that the estimated delta 2 RML of the parameters delta 2 sigma 2 uniformly dominates other estimators. So here I will conclude the presentations. These are the important references, and the presentation was based on the last two papers which are co-authors by my guide Professor Somesh Kumar, who is chairing the session today. And thank you.
Yeah, thank you, Dr. Jana. So if any delegates want to ask any questions, they can ask. We have time for one or two questions. Yeah, you can unshare your screen. Yeah. Okay, I think nobody else is asking a question. I will ask one question actually. So is there a possibility, because you have considered basically a location scale setup, so is there a possibility that you can consider extension of this work for a general location scale distribution?
Yes, sir, that is possible.
And then find out certain conditions under which your results, your type of results can be proved. Is it possible?
Yes, sir, it is definitely possible. That will be more general study, which will cover many distributions. We can consider scale as well as location parameter, and for a general family of distributions, study can be possible.
Okay. Thank you, Dr. Navkumar. So we come to a conclusion of this session on estimating the parametric functions of in exponential distributions. And so we have considered various kind of decision theoretic results, as you have seen. I thank all the speakers, Dr. Yogesh Mani Tripathi, Dr. Manas Ranjan Tripathi, Dr. Navkumar Jana, and Dr. Lakshmikant Patra for exploring various aspects of estimating parametric functions when we have one or more exponential populations. I think this kind of session will be helpful to many young researchers who want to take up the research, and especially we have shown that very advanced techniques like Kubokawa approach and other things can be employed to produce improved estimators. So definitely in statistical inference, we are always looking for better quality inference. So this will be helpful. Thank you. With this, I hand over the session to Professor Satish Kumar.
Thank you, Professor Somesh Kumar, for a very excellent session. You organized an excellent session with potential speakers as your ancestors, like I hope, and they are very energetic, very active researchers. I hope these people, these types of your students who are working in the various area, especially in this area of research, in the inference especially, we can utilize these people for further discussions, and there is scope for next conference also this type of deliberations.
Yeah, I request all of them to become maybe life members of Indian Society for Probability and Statistics, if they are not yet. So I request all of them to become members.
Sir, I'm already the life member, sir.
Okay. Yeah. Okay.
I add in the group also, those who are interested can please approach and become a member of ISPS. And on behalf of the Department of Statistics, University of Kerala, we are very much indebted to you, Professor Somesh Kumar, for your nice organization of this session, and also the speakers. One by all the speakers, they did a very wonderful work. I think. Just a minute. Just to name them, Professor Tripati, Manas Ranjan Tripati, Professor Yogesh Mani Tripati, Professor Navakumar Jana, and Professor Lakshmi Kant Patra. All, in fact, thank you so much. Let us give a big clap to these speakers.
Thank you, sir. Thank you very much for invitation, sir.
Okay, thank you. So I think we have finished in time. You have
yes, sir. So very much time, sir.
Yeah. Okay. Thank you very much, sir. Yeah.
Okay. Thank you
sir,
so
namaskar,
much.
Sir. Sir, namaskar.
We expect your continued support. Thank you.
Yeah, sure. Yeah. Okay.
Namaskar.
Now the next session is not in this platform because it's a contributory level session, and in order to avoid the delay in this session, we consider it as a parallel session, and that will start at the other parallel link at 12:30. There is 4 minutes there. Those who are interested, please join that group. And in this session, our the next keynote talk will start at 1:30 in this platform by Professor Carlos Kachashvili, and the team from Georgian Technical University followed the other special invited talks, and thereafter a lot of interesting sessions are there. I request all of you to please join these sessions and get benefit out of this, as well as encourage our youngsters to also join these sessions. Thank you all. Thank you so much for your support. For the time being, let me to join the other session. Please, with your permission, I'm just leaving from this platform and joining the other platform. Those who are interested are also please join the other.
Yeah. It's raining heavily. Yesterday.
Oh, okay.
Yeah, yesterday it was flooding in our city.
Oh. I think today we're very funny. Okay, let us start this session. Okay, Professor Pakala and Professor.
Yes. Shall I introduce?
Yeah. Before introduce Professor, our Ardra, please introduce the chair, and then please help him to do the remaining parts of this session.
Okay, sir. So now we have a keynote address titled Method of Testing of Hypothesis Concerning Normal Distribution with Equal Parameters. This session will be chaired by Dr. T.P.M. Pakala, Professor of Statistics and Dean of Faculty of Science and Technology, Mangalore University. He is a member of Mangalore University Academic Council. He has research interest in the areas include inventory modeling, stochastic modeling, statistical analysis of finance, R and Excel programming, research methodology and data envelopment analysis. He has more than 40 research publications in reputed international journals. We are truly honored to have you, sir. I warmly welcome you to chair this session.
Okay, thank you. Thank you. Actually, I'm retired now.
It's a long, earlier biodata, right? I think.
Yeah. It's like an old CV. It's okay. I think Professor Carlos is present. Yeah. Let me. Is he online?
Yes.
Yeah.
Yes, I'm here.
Now, let me give a brief introduction of Professor Carlos Skivi. Maybe I'm sorry if I pronounce it not correctly because it is a foreign name.
Okay.
Yeah. He's a full professor, having a Doctor of Science degree, and also is an electrical engineer. And he has a postgraduate degree in applied mathematics. So he's a professor of Georgian Technical University, main scientific worker of Wsta Institute of Applied Mathematics of Tbilisi State University, Tbilisi, Georgia. He has his experience in mathematical statistics, data experience and expertise in mathematical statistics, data analysis, mathematical modeling and simulation, computer technologies developments, recent developments, system analysis, computing mathematics, mathematical methods in research. He obtained a scientific degree, candidate of science, in March 1978 in Moscow Power Institute, Technical University, Russia. The next scientific degree he got is a Doctor of Science. He obtained that in October 1990 in the Medellin University of Chemical Technology of Russia in Moscow. He's a postgraduate in applied mathematics. He has experience as a foreign professor of Abu Zalam Social School of Mathematical Sciences of GC University, Lahore. He was a main scientific officer of Wsta Institute of Applied Mathematics of Tbilisi State University, Tbilisi, Georgia. From 1992 to 2001, he was head of National Career Environment Monitoring in Tbilisi, Georgia. Earlier, he was chief of Automated Information Measurement System Department at Tbilisi Scientific and Production Association. He was also consultant along with his position. Simultaneously, he was rendering his services as a scientific consultant of Scientific Research Center of Academy of Agriculture Sciences in development of countries' agroeconomical monitoring. Now, I request him to speak on methods of testing hypotheses concerning normal distribution with the equal parameter. Welcome, Professor.
Thank you. Thank you. Can I share my file?
Yeah.
I cannot share. You allowed me to share file?
Sir, you are able to see
The project, your presentation is not projected.
Grant permission. I have not permission. I have not permission. And therefore, I cannot.
Sir, if it is any difficulty, you can send it to me.
When I to share my file, here is written that I have not the permission from your side. You must grant permission in order to screen here.
You are, yeah, that you have to change it in settings, person. Or otherwise, you can send to me as an email to me.
Yeah, you can.
Okay.
You can email him and he can post it.
Okay. Again, I have not permission. I cannot share.
Yeah, but that is not. That is a technical error. Probably when the settings, have to change some options in the settings.
Options, which options? Who must change options? I or your technical team?
So it is from there, not from here.
What?
It is from the computer, your computer, professor.
My computer?
Yeah. There is some denying options are there, probably. That's why.
I don't know what
Do is go to the settings.
Open the file.
I cannot open the file. My file is open. My file is open.
Okay, then press present now. You know, there is a button called present now with the arrow mark, upper arrow mark.
I'm clicking on present now, and after your entire screen, and when I click this one, here is written, you must grant permission in order to screen share. You must grant. That means I must grant.
So it's better, professor, you please send an email to me. Yeah.
Send it by mail?
Yeah, by PDF copy. Please send a PDF copy.
To you?
Yeah, professor.
Yes, yes.
Okay, Dr. Sashish, I have sent already.
I'm checking the page, but I have not received any.
What?
I have not received. Yeah. Now whenever we receive it, we will do, Professor. CSK. Nikhil will share from here, Professor. My son, he will do.
Sorry for the delay. We'll wait for some time. We'll start. Some technical problems.
Yes, unfortunately, with my computer in the last year was the same.
Okay, now it comes.
Okay.
Now we can.
Okay, can I start?
Yeah.
You can start, Professor, and you can give directions to the whether
you can start whenever it is next slide. You can mention. I think.
Okay. I will say next and so on.
Maybe
of testing hypothesis. My presentation type is method of testing hypothesis concerning normal distribution with equal parameters. Next, please. Next, please. Okay. On this slide, presentation structure is given. The content of the previous, please. Presentation. Oh, okay. It contains by the following items: introduction, statement of the problem, hypothesis testing, two methods of hypothesis testing, maximum ratio test and Staines methods are considered. After there are given two different statements of the method of constrained Bayesian methods, and in next item, application of this CDM constraint to the considered hypothesis is given. In next item, computation results are presented for maximum likelihood method and for Staines method, and finally short conclusion is presented. Please, next item, next slide. Next slide, please. Okay. In many practical situations, normal distribution with equal parameters arise. For example, in many practical situations, random variable x having a Poisson distribution with parameter theta is considered. For making optimal inference in such situation, it is important to estimate theta accurately, especially when theta is believed to be large. But when theta is assumed large in practice, the original Poisson distribution can be changed by normal distribution with identical parameters because it is a known mathematical expectation and variance of Poisson distribution are equal to each other. Thus, to estimate or to test hypothesis concerning this parameter normal distribution is practical, has practical importance. Next, please. Next, please. Next. Okay. This problem has been discussed in different sites. The following publications, basically of the co-author of the present presentation, are devoted to the solution of this problem. In most of these papers, the result of processing both simulated data and real data are given. Next, please. Okay. Without any losses, we consider sample of an independent identical distributed random variables with the following probability distribution function, and 1.1 belongs to a regular one-parameter exponential family, since one can write the following where parameters x and theta are positive. It becomes obvious that a complete and sufficient statistics for the parameter theta is the statistic t, which is function of the observation observation results. In the above mentioned works, which was indicated on the previous slide, the following problem was considered to test basic hypothesis versus alternative one, and both of these are simple hypotheses. Next, please. Okay. Next. There are developed the level in the mentioned works. The level alpha most powerful test on the basis of Neyman-Pearson's approach. Also, the level alpha most powerful test having additionally a pre-assigned type 2 error probability where the sample size is chosen appropriately. The exact and large sample determinations of required sample size associated with most powerful tests having pre-assigned type 1 and type 2 error probabilities is developed, and data analysis with simulated as well as real data are given also. Confidence intervals problems for an unknown parameter theta and the sequential probability ratio test methodology with real data are considered also in these works. In contradistinction to the above considered papers, where determination of sample size n restricted both error rates for large theta 0 and theta 1 is complicated. Below, both type 1 and type 2 error rates are restricted naturally without any complexity. Moreover, that we consider more intricate case when alternative hypotheses are complex. Here, maximum likelihood and Stein's approach are offered applying constrained Bayesian methods, ideology for testing hypotheses concerning set of parameters released. Next, please. Let's give statement of the problem. We consider random variable x distributed by normal law with identical parameters, and probability distribution function density has the following form, and hypotheses which must be tested are presented by formula 2.2. Basic hypothesis is simple and it must be tested versus two alternative hypotheses, left-sided alternative and right-side alternatives, and the interval for the parameter theta for right side alternative is infinite. And we test this hypothesis on the basis of the sample which has the following common probability distribution density. Next, please. Okay. Previous, please. Previous, please. Okay, this one. Oh, this one. Okay. Next, please. Okay, this one. Okay, this one. Basic hypothesis, as I told in this case, is simple and alternative is composite, and below are offered two different methods for testing such hypothesis. One is based on maximum likelihood estimation, and another is based using constrained Bayesian method. Let's consider in the beginning the maximum ratio test. In this case, we test basic hypothesis versus alternative one, where alternative hypothesis suppose that the true value of the parameter is equal to the theta ml, where theta ml is maximum likelihood estimation computed by the following formula. This formula is obtained using the maximum likelihood method. Distribution densities corresponding to these two basic and alternative hypotheses are given by ratio 3.2. And next, please. Okay. It is obvious that the general rule of testing such hypothesis is the following. When alternative hypothesis is accepted and estimated value theta ml is less than theta 0, hypothesis left-sided alternative hypothesis is accepted, and otherwise right-side alternative hypothesis is accepted. This method can be applied according to the following rule. The initial sample with the site M must be divided into two subsets. First subset and second subset, which contains a different number of observations. And on the basis, we find maximum likelihood estimation of the parameter, and on the another subset, we test hypothesis. Next, please. Okay. Stay's method contains in the following. We have to define conditional distribution densities corresponding to the tested hypothesis, and these expressions are given here, where by gamma minus of theta and by gamma plus of theta are designated the densities of the parameter theta at two alternatives, left-sided alternatives and right-sided alternatives. When basic hypothesis is true, expression for this conditional probability is very simple. In this case, they are complicated. Next, please. Next. Okay. It is seen from the expression of maximum likelihood estimation that this statistics is complete and sufficient statistics for theta. And let's find the distribution law of these statistics. For this purpose, let's transform these statistics as follows. Where theta I are independent random variables sharing the standard normal distribution, it is clear that in this case, this random variable has normal distribution with the following parameters. Next, please. Okay. It is known that the sum of squares of an independent normally distributed random variables is distributed according to the non-central chi-square distribution with n degrees of freedom and non-central parameter, which is computed by this ratio. That means this statistics has the following distribution. Next, please. Next, please. As a prior density of theta in the expression for conditional probabilities at alternative hypothesis, we choose non-central chi-square distributions truncated to the intervals, finite and infinite intervals, and we introduce the following designations for this distribution function and density is the interval AB. When this interval is infinite, we use the following designations, and these functions can be defined by this following formula. Next, please. Next, please. These components are computed by the following formula, and the next, please. Next slide, please. Okay, next slide. Show me, please, this one. Okay, okay. It is well known that non-central chi-square distribution can be approximated distribution when the parameter of non-centrality is great, and for this purpose we need two moments, mathematical expectation and variance of the statistics, which are computed by these following ratios. Next, please. Next, please. Next, please. Okay, and after making such approximation for the distribution densities for the finite and infinite intervals, we obtained the following formula. Unfortunately, to use this formula for our final aim to test a hypothesis is quite difficult, and for this purpose, we make the following suppositions. Next, please. Next, please. We change infinite interval. Okay. In this case, these conditional probabilities have the following form, and from here it is seen that they are for alternative hypothesis very complicated. Next slide, please. Next. Next. Okay. Next, please. Okay. And for simplification of the problem, we decided to transfer from infinite interval to the finite interval, where k is some integer number, and it takes value 2, 3, 4, and so on. And in this case, as a priori distribution of the parameter theta, we can use the uniform distributions intervals, and they are given, these densities of the distributions are given here. Next, please. Next, please. Next. Okay. Okay. This transformation of infinite interval to the finite interval changes the view of hypothesis which we have to test, and this hypothesis has the following form, and when k is great enough, the accuracy of such case is quite high. In this case, conditional probabilities take the following forms, and from here it is seen that now our problem is simplified in comparison of the previous case. Next, please. Next, please. Okay. Now here in this item is given the statement of the constrained constraint Bayesian method for testing hypotheses, we have introduced the following designations. AJ is hypothesis AJ acceptance region. L1, L2 are the losses of incorrectly accepted and incorrectly rejected hypotheses. Next, please. Next. Next, please. Next page, please. Next. Next page, please. Okay. Next page. Next. This is previous.
Yeah, there is a problem.
Okay. For this reason, there are different opportunities of statement of CBM. In one case, we minimize type 1 error rate and restrict type 2 error rate. In another case, vice versa. In this work, we use two different statements, which shortly are designated as task 7 and task 2. In task 7, we maximize the following expression, which is power of this criteria. It's the following restriction. Next, please. Next. Next, please. Next page, please.
He's trying. There is a technical problem. It's not moving. That's why he will move closer. Please try.
Okay.
More otherwise, start from second.
You cannot show next page.
Next page.
Next page, please.
He will stop and sharing it again because some technical problems that denies moving. He is not able to move.
Okay.
That is why.
What I can to do now?
Maybe you can summarize what is remaining.
Finally, I can say the following. We applied method CBM and for two cases using the maximum likelihood method and the Staines approach and obtaining final expressions for the concrete expressions for hypothesis acceptance regions after we simulated the concrete situations for testing hypotheses which we have to test and okay for this one, next please, next after this next page. Okay. Oh, this, let's see, we consider it stepwise loss function. Loss functions, they are restriction functions as the restriction conditions. Next, please. Next. And by this formula are given hypothesis acceptance regions. We are undetermined Lagrange multipliers. Lambda are determined so that in the appropriate restriction conditions, which was on the previous slide, was taken equality. Okay. Next, please. Next. And for estimation of quality of testing hypothesis, final quality, at asymmetric hypothesis, there are used two different criteria, such as poor directional path discovery rate and mixed directional path discovery rate, which can be expressed in the determined by the following formula, and among them is the following: if the equality takes place. Next, please. And on the next slide is shown that these two criteria can be expressed in the terms of type 3 error rate. Next, please. Next, please. And these two theorems which we have proven in our previous work, these two theorems is in force for the considered case 2. In particular, in this theorem is proven the following: CBM 7 with the appropriate restriction level at satisfying the following condition where Q is some probability and P is minimum retrieval probability, issue a decision rule with the following condition. And next, please. Next. And in the next theorem proves the same fact for the CBM, not the same, but in the same conditions for CBM 7, the following inequality takes place. Let's see, next, please. Next.
Yeah, Professor, you have 4 minutes. Professor, you have 4 minutes. So try to summarize in 4 minutes.
Okay. Okay. Make conclusion. Final. Okay. Next, please. Okay. Here is given the statement of task 2, and for this case, 2 following theorems are proven. In this case, this type 1 and type 2 error rates are restricted by the following ratios. And next, please. The next theorem is proven the similar condition also. That means that at appropriate, next, please. At appropriate next, choosing the restriction levels, we can restrict the type 1 and type 2 errors on the desired levels. They are hypothesis acceptance regions. Next, please. Finally, I want to show you, next, please. Here are given formulae for computation of Lagrange multipliers for the method of maximum likelihood, and these formulae are given on the next slides. Show, please, next slides. Next, please, next, next, and next, please, next. Okay. By this formula is defined lambda A, and by similar formula which is given on the previous slide is defined lambda 0. Next, please. Next, please. And computation results are given here, and the computations we are realized for maximum likelihood method. Then a number of observations for computing parameters estimation, we used 5 observations, and for computation of probability of made decisions, we used 3,000 observation results, and a priori probabilities of the hypothesis are equal to each other, and accuracy Lagrange multipliers is equal to 0.01. Next, please. Next, please. Okay, next, let's omit these tables, and I explain the result of the figures which are presented after these tables. Next, please, next, until API, this one. Let's see, this figure is given the dependencies of probabilities of correct and incorrect decisions on the difference between parameters values determined by basic and alternative hypotheses. This curves correspond to the CBM, and these correspond to the bias method. And these are probabilities of correct decision, they are probabilities of incorrect decision, and from here it is in the CBM so-called bias method. Next, please. The same effect is seen from the next graph also. Next, please. Next, please. Okay. In this item are given, are given results for Stein's method, for Stein's approach using CBM. Next, please. Let's scroll until graphs, until appearing graphs. Okay, let's see. In this figure and on next two slides are shown probabilities of acceptance and the rejections of tested hypothesis. In the first case was shown for when basic hypothesis is true. In this figure, when alternative left side it is true, and on the next one, alternative right side is true. And for that, CBM gives better results and in general gives better results than bias method. Next, please. Okay. Next, please. Next, please. Okay. Next. Okay. On these graphs are given dependencies of type 1 error and type 2 error rates on the value of the parameter theta 0 in Stein method. And from here it is seen that this one blue corresponds to the CBM, this corresponds to the bias rule, and this is restricted level which we introduce, we choose depending on the final aim which to which solution is devoted this main method. And on these slides are in details explained superiority of the CBM of the superiority of CBM in comparison with bias. And the next, please.
Excuse me. Could you summarize in 1 or 2 minutes? Okay. Yeah, okay.
I can speak about conclusion, but in conclusion I repeated the same which was said above. And here are given some conclusion. Okay, let's show conclusion. Let's read briefly. To approach of comparison of composite hypothesis testing such as Stein's methods are considered using CBM and bias methodologies. Algorithm CBM for specific case when tested hypotheses are formulated concerning normal distribution with equal parameters are developed and investigated. Opportunities to restrict different characteristics of optimality of made decisions such as type 1, type 2 error rates, maximum mixed direction of fast discovery rates, summary types 3 error rates are theoretically proven and shown by computation of concrete examples. Superiority of CBM over bias method is clearly demonstrated by computation results. On the next slides, the literature which we used in the process of working on this presentation are given on the next slides. Thank you very much, and I am sorry for my computer which didn't allow to make my presentation more accurate and more convenient for me and for you also. Thank you very much.
Okay, thank you, Professor. Maybe if there is any quick question or there are questions. Okay, I don't see any questions, so I thank the speaker, Professor Carlos, a very elaborate topic. So let me thank him and thank the organizers. Okay.
Thank you.
Thank you, Professor Kacheshvili, for your nice presentation. And thank you, Professor Pakala, for chairing the session on behalf of the organizers of this conference. We would like to extend our gratitude to both of you.
Okay.
Thank you.
Okay, thank you. Thank you. Thank you.
Now let us move to the next session. Because, Professor Kachashvili is our, in fact, we have the Georgian Technical University and our department academic collaboration, and we are very much thankful, Professor Kachashvili, for regular support, sincere support. Academic. Thank you, Professor. Thank you so much.
Thank you very much.
Now let us move to the next session. Yeah. Here, Professor Banu is here to chair this session, and the professors from the Georgian Technical University are there to present their. Before starting the session, my students, Lakshmi or Harvard, Sophia, please introduce the chair and do the.
Okay, sir. So good afternoon, everyone. Now we have a special invited session chaired by Dr. K.S. Bhanu, Professor and Head of the Department of Statistics, Institute of Science, Nagpur. She is an academician with 36 years of experience and with research mainly focused in areas of reliability theory and built as a member of their academic bodies. I gladly welcome you, ma'am, to chair this session.
Welcome, Professor Banu.
Thank you very much, sir. Professor Satish Kumar. Let me at the outset thank the organizers for inviting me to chair this session. I'm happy to be here. And in this session, there are two speakers, Professor Wathang Quartas Khilia and Professor George Gigobiani. I take pleasure in introducing the first speaker, Professor Wathang. I welcome you, sir, for this technical session. Professor Wathang holds the coveted post of the director at the Muskhelishvili Institute of Computational Mathematics at the Georgian Technical Institute. He has been holding this post since 2008. He was also the leading researcher in the same institute. Before that, he held the post of he was heading the mathematical lab at the Tbilisi State University from 2007 to 13. He has been involved in research for a long time, starting as a junior and senior researcher from 1975 to 2005, and then leading researcher, scientific secretary at the Muskhelishvili Institute of Computational Mathematics till from 2006 to 2010. His research area includes functional analysis and probability theory. As a leading researcher, he has been instrumental in handling various research projects and has been invited to deliver talks on various leading universities. He is a member of the board of the Georgian Mathematical Union and also a member of the GMU Council. Apart from being a member of the editorial board of scientific journals like Bulletin of TICMI, Computer Sciences and Telecommunications, etc. He is also a member of the Georgian Statistical Society and the American Mathematical Society. With this wonderful biodata, I invite Professor Wathang to deliver his lecture, invited talk on the connection between the movements of random variables. Professor Wathang, sir, the floor is yours.
Hello, Professor Banu. I'm George Giorgobiani. I'm the co-author of this paper, of this work. So let me present this work to you.
Okay, then, sir, I'll have to, should I introduce you first then? I thought maybe Professor will, okay, sir. I'll just take 2 more minutes and introduce the speaker for this session, Professor George Gigobiani. He has graduated from Tbilisi State University from the Faculty of Mechanics and Mathematics, Department of Probability Theory and Mathematical Statistics in 1983. He obtained his doctorate degree in 1990 from the Tbilisi State University. He is the Deputy Director at the Mushkelishvili Institute of Computational Mathematics of the Georgian Technical University and a principal researcher at the Department of Probability and Statistical Methods. As the author and co-author, he has, to his credit, 29 research papers published in various reputed research journals. His field of specialization also includes function analysis and probability theory. Sir, Professor George, sir, I invite you now for your lecture.
Thank you very much. Thank you.
You will be sir, will the other speaker also join us, Professor Vatan?
Yes, he's here. I see
him.
This
session is about maybe 30-35 minutes. So you will be getting around 20 minutes, 15 to 20 minutes.
I hope so. Yes.
Okay, sir.
I'll make it shorter. Yes.
Okay, sir. Please.
So can I share it now?
Yeah.
Okay, just a minute, please. Do you see my screen?
Yes, sir.
Okay, that's good. Just a moment, please. Okay, is it okay with the presentation?
Yeah,
it is good,
sir. It's clear.
Okay. Nice. Good afternoon. It's my pleasure to participate already for the third time at the conference organized by Kerala University. And together with my co-author, Vakhtang Paratshelia, Professor Paratshelia, I would like to say many thanks to the organizers for inviting us again. So now I'll try to make it shorter and make it explicit. What have we done and what do we want to present here? This is about one inequality, which is establishing a relation between the moments of the random variable. This inequality was proved first by Ryoji Fukuda in 1990. And in this work, this was one of the basic works about sub-Gaussian vector random variables with the various Banach spaces. In this paper, the Banach space is LP space. And this inequality, which you see now on the screen, plays an important role there. So what do we have here? We have two numbers, positive numbers, P and Q, and for some C is a constant greater other than 1, we have the following expression. Now let's look at this inequality closer. If E were less than Q, then this inequality is known as the Hilder inequality, and C equals 1. But we have it vice versa. P is greater than Q, and thus this requirement of existence of such a constant greater than 1 is required for this inequality to be fulfilled. Now let's imagine that we have this condition for some psi, or a random variable psi, and next let's consider some other numbers, also positive numbers R and S, between 0 and P. Then there exists a constant K, which depends only on these given numbers. It doesn't depend on the random variable. Okay, and so that the last inequality on the screen holds. This is Fukuda's inequality. It was proved first by him. And what is our contribution now? That proof by Fukuda is elaborated and did some advanced technique which was developed by him. by the author himself. But we made an attempt to prove this inequality in a much simpler way. It is almost elementary if you know Hilbert's inequality, of course, and it is based upon one guess. So I will tell about this later. But before we move to our inequality, let me tell some related history in brief, which comes from functional analysis, to say so. So this result is by Banach in 1933, and it tells us this theorem, this result, that if you are given any orthonormal system by n, then you can always extract a subsystem which is p-lacunary. It means that the series alpha k, phi n k converge in LP for any p whenever the square alpha k square the series converges. This was a celebrated result for that time, and there are several other interpretations of this theorem, like we can say that this theorem implies that there exists an isomorphism of the Hilbert space L2 onto the closed linear manifold, some closed linear manifold L in LP, spanned by these functions, by this subsystem. And the natural basis of L2 is equivalent to our system, our subsystem, via this isomorphism. And we can say, in other terms, in the terms of the norm of the isomorphism, we have the inequality which you see in the end of the slide here. Okay, here once more I will get back to the issue that if P here is less than Q, then by the Hilbert inequality, C equals 1. We do not need any additional constant. But it becomes more interesting and profound when P is greater than 2. Okay. Later in 1962, Kadets and Pelchinsky, inspired by this result of Banach, investigated more general version of the theorem. They obtained the necessary sufficient condition on any sequence X n in LP in order to contain the basic sequence equivalent to the natural basis in L2. So this is a brief history which was evidently known by Ryoji Fukuda, and studying the sub-Gaussian random elements with values in Banach spaces, basing himself on these results cited above, Fukuda came to a result which is improved in our theorem 2.1, which I will show next. So at last we go to our inequality. So the conditions are the same as in Fukuda's theorem. So once again, we have two numbers, positive numbers, P greater than Q. And let we have the same condition here with some constant C. This is a relation between the moments, P and Q moments of the random variable. And again, we have two more numbers, R and S, which are between 0 and P. And then we have this expression, this inequality, like Fukuda had, but we have a constant here, C power beta. And most interesting is that we can express beta explicitly. Now let us have a closer look to these cases. Beta equals 0, as we said several times today, in case when R is less than S, and this is trivial. Just Hilbert's inequality. Again, in the case when we have that Q is less than S and R, then we have beta equals 1. So we have C here, like in this initial inequality. This is not hard to obtain this result using this condition. The last two cases need some additional effort to be proved. So the first case is that when Q is in the middle, not in the middle, but between S and R. In this case, we get this kind of expression for beta, and the similar expression is for beta in the case when S is less than R, and they are both less than Q. So I would like to repeat once more that Buddha's proof was very elaborated, and I will show the constant, Buddha's constant, in the end of the presentation. And we think that our expression, our version of the Buddha's inequality is maybe better than the initial. Maybe I say. So the proof is quite elementary. I have talked about this already. Well, where can this inequality be applied? First of all, of course, in probability theory, there are many problems related with moments. It could be, it was, and it can be applied in functional analysis by all means, and maybe in mathematical statistics. So the proof is, I would say, almost elementary. We only use the Hilbert's inequality, and our guess was crucial here. So the first two cases are very easy, but to prove the last two cases, we introduce the numbers. This is our guess. I'll repeat once more. Two numbers, U and V, in this manner, using our given numbers S, Q, R, and P. And we find here easily that they sum up to 1. Then we use the Hilbert's inequality, and we get our result after some simplification of the expression. So I skip I don't present the proof because it is rather technical, but in case of your interest, at your request, we can send the whole proof and you can see this yourself. Now, in the end, let us look at the constant in Buddha's original inequality. First of all, he proved his inequality for a little bit, for a partial case when R equals E and S is 1. And he obtained this kind of constant on the right-hand side, where B is a beta function. Beta function is related with the gamma function. You know about it. And this is not an easy function to handle, but we have made some calculations in some partial cases, and we found out that our constant C to power beta is not greater than Buddha's constant in most of the cases. So I think this was all. We have here is a list of references. This is a paper by Banat. So this is Kadets, Kolchinsky, and Ryoji Fukuda. That's all I think so. Thank you very much for your attention.
Thank you very much, Professor George. You finished exactly on time, and the proof that you said showed us is quite interesting and very easy also. I think all the
Thank you
students
very
must
much.
have easily understood. Any questions from the audience?
Thank you.
Are there any questions or comments? If not, then we thank you very much, sir,
Thank you
for
very
your
much.
excellent
Thank you for doing
presentation.
this. Thank you.
We invite now Professor Wathang to deliver his lecture.
No, this was our joint presentation, Professor Banu.
I see.
This
Okay,
this was our joint presentation, so
Joint
that's all in this regard.
I thought
Thank
one
you.
after the other, that's why.
Yeah, this was one
Okay,
presentation.
sir.
It's concluded, isn't it, madam?
Yeah, this is over, but I think we have to conclude this session.
Whether anyone, other
Professor, is there another presentation, Professor George?
whether he is speaking, it's a joint presentation, isn't it?
It's a joint presentation.
It's a joint paper.
I'm a co-author of Professor Paratselio last time.
Okay.
So,
whether he has to say anything in this group?
Yeah.
Where he has to add anything or anything, any comments with regard to the.
If he is there, he can join us and present his views, Professor Wathang.
Well, I saw him on the screen, but right now I don't see him. Maybe something wrong with.
He was there. I think he joined when we started. I also saw him there.
He was here in the group.
He was here just a few minutes
he was
ago.
Here.
I see. He delegated all the everything.
Yeah, he is here in the group.
Yeah, he's here.
Anyway, he can
Probably
address.
the network issue. Oh yeah.
Okay, then should we conclude, sir?
Okay.
Okay, sir. Thank you very much, Professor George and Professor Satish Kumar, for inviting me to chair this session. Thank you all.
Thank you.
all for your time. Thank you.
Thank you, Professor George and Professor Bhaktang, for your article and Professor George for your nice presentation. And also, we would like to extend our gratitude to you, Professor K.S. Banu, for your support and chair of this session. And you have nicely chaired the session in a nice way, and we just have a further continued support from you each of these matters. Thank you so much. Thank you. Now let us in the next session we will start at 50. By the time we have a few minutes, 5 minutes, 10 minutes, 12 minutes. I would like to know whether Professor Ismail joined in this group. He needs to chair this next session. Okay, let us wait a few minutes. Professor Banu?
are starting the next session just now?
Yeah, no, the next session I have to wait some time.
Okay.
By the time I would like to know whether you have instituted some awards in the ISPS.
Yeah, we have
in honor of
award in the memory of Professor Deshpande. That is to be given to the best young researcher.
Okay. You can give something you can talk about that.
Yeah, we actually Professor Deshpande was always interested in research throughout his life, and he always tried to inspire and motivate young researchers. That's why some of our research students, all his students and some well-wishers, we got together and we have donated some amount to ISPS in his honor from next year onwards, I think. Maybe from the January conference of Kerala conference. I think it's going to be held there only. So maybe that year they may give to the best young researcher. The guidelines are yet to be framed. Professor Reddy will help me out in that, I think, and then we'll be instituting giving this award from next year onwards.
Very good.
Professor Deshpande was writing a book also while he was not well. When he was not well, he was writing a book on Diophantine triples. Unfortunately, he could not. Actually, he fell sick, and he was actually recovering, but then he suffered a cardiac arrest. So we rushed and we got the book published just to show it to him. And he could see the book. But now we have held a function on his birthday and we have released the book. I would like to present one book to your library also, sir. That's on Diophantine triples, but you have known Professor Deshpande for a long time. So his work will be there in your library. I will send it to you, sir.
Thank you, madam. Thank you so much.
And you can donate one to the Department of Mathematics.
Surely. Sure,
sir.
Great. Thank you.
Till the last breath, he was doing research only. So that's very commendable.
Very sincere and and he, I think you visited our 2015 conference or 16.
Yes, and we had all come once. Organized a session.
I remember.
That was a memorable conference. Nice. And I have to congratulate you. You keep on conducting organizing so many conferences.
Thank you, madam.
Your capability, sir, and your interest for the subject. Very nice.
Thank you so much. Your support, with your support, all we are doing. What about the family? Professor Deshpande?
His wife passed away a few years back. Sir has two sons, and both of them are in US. Sir used to stay alone only here.
In fact, he built a department. The department is built.
Institute.
Professor, I think we have to check whether the next session
speaker is there.
Professor Ismail, the chair, joined. Others also joining by Professor D.K. Hosh has been informed whether he is in the group.
Good afternoon, Satish.
Good afternoon, Professor. Good afternoon. Good afternoon.
Yes, thank you.
How is your?
It is raining heavily here.
Oh, heavily. Okay.
Yes. Last 2 days. Yesterday it was started. Continuously.
Okay.
Otherwise things are okay, normal.
Last time your students achieved the.
Yes, professor. They secured second position in the ISPS project competition.
That's right.
Now you are with that university.
Yeah. After the superannuation from Mangalore University, I joined Yenepoya deemed to be university.
Oh, okay.
I'm working here for the last 3 years.
Yeah.
So we are having MSc Biostatistics and MSc Statistics, both programs.
Which university, sir?
It is Yenepoya deemed to be university, Mangalore.
Mangalore, okay.
Yeah. Good afternoon, madam.
Good afternoon, sir. I'm from Nagpur, Institute of Science.
Okay, Nagpur, right. Yeah.
We are talking about Professor M.N. Deshpande. Yeah.
I was just listening to that, and how is any?
He was no more, Professor.
He's no more. He lost him 6 months back. But so we have instituted an award in his name.
Okay.
In ISPS for the best young researcher. Sir used to do his research and he was involved in research till the very end.
Yeah, I know.
That's why to honor him, all his students have got together.
Even after his retirement, also he is very active.
Very
I know. Deshpande sir, he has visited Mangalore also. I know him. We had several interactions. We used to go to their Pune. We used to have the interaction with him. Speakers are ready, or are we waiting for?
I think the speakers are ready. They given a message to me, but they have not joined the group.
Okay. Right. Yeah. First speaker is Professor P.R. Vittal. If he is there, he can start up.
Vittal has not given a message to me. Professor Ghosh joining.
Okay. And Biradar will be there, right?
Biradar also, I think, in the group probably.
Okay.
And Biradar is not in the group, he will join.
Okay.
By the time, let me to contact Professor Vittal.
Okay.
Sir is joined, I think.
Yeah.
Namaskar. Go, sir. His mic is muted.
Yeah. Good afternoon, Ghosh sir. His mic is. Please unmute your.
Professor Ghosh, hi, Professor. Professor Ghosh, there is some darkness.
And mic is muted.
Okay. Professor Ghosh, the mic is muted. So we are talking something, but we can't able to hear you. We are not able to hear you. Yeah, now it is.
Actually, here we have raining, heavy raining. So I'm just putting light to see.
You are not in India? Presently you are outside?
Is it okay now?
Yeah, now it's slightly. Yeah, Professor, you are not in India now? You are from outside?
Now it is not visible?
Yeah, now a little bit we can see you. There is not enough light.
Because there is heavy rain and it is complete black. Sky is complete black.
Okay, Professor.
So whole surrounding is black.
Okay, that's why.
That's why this is problem.
So I think now we are 2:14 a.m. Our session starts at 2:50, and let us move to the session by the time. Sophia or Jeshna?
Sir.
Jeshna, ready? Are you ready?
Am I audible, sir?
Okay, audible. Jeshna, please introduce the chair and do the needful for the smooth running of this session, please.
Okay, sir. Good afternoon, everyone. Now we have a specially invited session chaired by Dr. B. Ismail. He serves as a professor and head of the Department of Statistics of Yenapoya University, Mangalore. Dr. Ismail is now specializing in econometrics and his main research area includes non-parametric regression, financial time series, regression analysis, and generalized linear model. He is a life member of various academic bodies such as Indian Society for Probability and Statistics, International Indian Statistical Association, Kerala Statistical Association, and Association of British Scholars. So warmly welcome you, sir, to chair this session.
Thank you. Shall we go according to the order? Professor P.R. Vittal is present, no?
Yeah.
So first, at the outset, thank you, Professor Satish, for giving me this chance to chair the session, and also congratulate you for organizing this international conference on webinar. Okay. So we have 3 speakers, and we have 1 hour 45 minutes. So each speaker will have 30 minutes, and maybe 5 minutes they can take for discussion. The first speaker is Professor P.R. Vittal. One minute. Yeah. Yes. Professor Vittal will be speaking on stochastic finance in a business company associated with the ruin, bankruptcy, restricted reserve dividends, and dividend strategy. Professor P.R. Vittal is from Chennai. His research interest is differential equations, probability and statistics, stochastic process. Did his PhD from Math Science, Chennai, on probability and stochastic process. And academic positions, he was a professor and head mathematics department, Vivekananda College, Evening, Chennai, and has many academic positions at present. He is a visiting faculty, Institute of Chartered Accountants, visiting faculty at Institute of Financial Analysis, visiting faculty at Madras School of Management Science, Chennai, visiting faculty at University of Madras, Chennai, and he has more than 20 papers in the national and international journals and presented about 38 conference papers. And his research papers can be found in Journal of Theoretical Neurobics and Scandinavian Journal of Actuarials and many more international journals. And at present, he is a professional activity, statistical analyst in a World Bank project on water and sanitation improvement project of Karnataka State, India. And he is a fellow of Tamil Nadu Academy of Sciences and authored nearly 18 books and guided MPhil and PhD students, 6 students, presently advisor to a student for PhD at the University of Madras Statistics. On behalf of the organizers, I extend a warm welcome you to sir, and I request you to present your work to the audience. You will be talking on stochastic finance in a business company associated with ruin, bankruptcy, and restricted reserve dividends and dividend strategy. Welcome you, sir. Please proceed. Over to you.
Thank you. Thank you very much. Organizers and the people who have taken interest in giving me an opportunity to come to virtual talk to our international conference, and thank you to you, gratitude to you all. And Satish Kumar phone I immediately accepted because he's one of my very good friends, and now I am in position to give my talk to you. Now the talk is going to be on stochastic finance. It is very similar to insurance problem. There are a lot of applications of this type in various results like neurobiology, queuing theory, game problems, and insurance problem. Now, I'm going to give the topic with bankruptcy and restricted river. Therefore, basically, mathematically speaking, it is going to be a two-barrier problem. Praveen, can you move this next one? Praveen. Can we move this slide to the next one? Yeah. Now you see, stochastic models are considered to analyze the risk involved in ruin and restricted reserve as barrier. One barrier is the ruin barrier, the other barrier is the reserve barrier. Now, the finance of the company always fluctuates between these two barriers, going up and down. Our questions of interest is that whether there is a possibility of the ruin to the company or the possibility of overflow of the risk reserve so that the excess over the barrier could be distributed as dividend to the stakeholder. Now, this is mathematically analyzed through Kolmogor's forward equations and backward equation and derive this model with inputs and outputs both. Inputs are coming in terms of the premium and the export goes out of the claims of the insurance company. So also in a dual way in any business. Now the risk is involved in the ruin. Restricted level risks are derived using Kilson's compensation function. This is basically a two-barrier problem, one with ruin, the other with reserve. Now fluctuation between these two barriers is now discussed with the help of Kilson compensation function. We are also going to do this with Richard Bellman's embedding approach. The philosophy of the Kilson compensation technique is that this bounded process is expressed in terms of the green function of the unbounded process. As if we are going to remove the barrier and discuss about the probability of ruin or the probability of the risk crossing the barrier. That is called the Green's function for the unbounded process. Various characteristics of this process through the Green's function are analyzed. Not only that, we have a suitable limiting procedure. We are going to convert this jump process into a diffusion process. With a suitable limiting procedure, this process is also converted into diffusion process of the Wiener Chaik slip. With the same limiting procedure, the first passage time for ruin or the risk level reaching a constant barrier or analyzed. Why I say the constant barrier is the upper barrier is fixed. It can be possible also the upper barrier can be moving in time deterministically and also it will be stochastic. The barriers could also be stochastic. This model is also extended the model with the exponential drift. The linear decay could be converted to the exponential decay and also made time dependent. These types of models are analyzed. The analysis of the above problem is also done using Richard Bellman's embedding approach. Both Lindbergh model and dual models are analyzed. Originally, the Lindbergh model was introduced to study the insurance problem somewhere in 1903. And then the dual problems are analyzed in terms of the business, where the risk reserve is going to be in the opposite direction of the input and output process. The expected, apart from that, the expected discount value of the dividend are derived. Whenever the dividends are given, the value of the reserve is going to be down and it is written in terms of the discounted value. We are also considered risk level, wherein there are two components of income with restricted reserve. One is the deterministic income, namely the fixed deposit revenue income. Other comes in terms of the premium. Hence, these two are considered two components of time-dependent reserve. We also study the optimal dividend. What should be the upper barrier? We also study the optimal dividend problem to determine the dividend payment strategy that maximizes the expected discounted value of the dividend problem. These are the analyses that we are going to consider. Who are the persons who contributed to this? Especially a conference of this type, it might not be possible to completely put in all the work of ours, but it might be possible that who are the persons who contributed to this level of the topic. Now, Richard Abraham Wald introduced in sequential analysis in 1942. Unfortunately, Abraham Wald died in India when he plane crash when he got to Ooty and his whole family. He introduced sequential analysis, and through sequential analysis, he studied various statistical problems. Later, when stochastic process developed in 1957, these sequential analysis problems are converted into the stochastic barrier problem, and the same Wald identity is derived. Kilson is another important person who is a professor in Rochester University, and he introduced the technique of compensation function when the barriers were introduced. Temperament is another person who inserted Markov process with barrier, both for discrete and time-dependable barrier. Dual is another three-dimensional problem converted with a two-dimensional problem. Sekerval is a Scandinavian professor who introduced this embedding technique for solving this problem. Krayakov is a Russian who introduced the concept of the barrier crossing both for jump process as well as the diffusion process with the help of a moving barrier. He made the barrier to be good. Richard Bellman converted the whole problem in terms of embedding technique. Gerber introduced a loss of, now Gerber has introduced more than few hundred papers in insurance through the forward method as well as the backward method. What are the techniques that you are going to analyze in studying this two-barrier problem, either the insurance or risk business? The Markov process is the well-known process. It is associated with risk. Ruin and restricted reserve are considered here. Kolmogor's forward equations we derive. Kolmogor's backward equations we are going to derive. Forward equation, we are going to use the compensation function. In the backward equation, we are going to use the embedding technique. Now we are going to use the two types of barriers. When you say the barriers are either the ruin or the risk level, the barrier could be considered as an absorbing barrier and a reflecting barrier. In the case of ruin, it cannot be a reflecting barrier when the company is ruined. In the case of the risk across the level K, the excess is gone out in terms of the dividend or in terms of bonus share, but the risk level remains at the uppermost barrier level and then once again fluctuate. That is called the reflecting barrier. The compensation function technique to be applied to convert both absorbing and reflecting barrier problem in terms of unbounded process. That means the solution can be given in terms of the Green's function for the problem. Green's function is a function which studies the probability of motion of the process when the boundaries are there. Generally, the technique that we are going to adopt in studying this boundary property problem are the Laplace transform technique or the Fourier transform technique. Now, once you get them, you invert it back to study the probability mass function in stochastic process. We go into also the limiting procedure for the diffusion process. In the case of the limiting procedure, we have to take the limiting procedure to the dynamics of the process and also the limiting procedure to the first passage time, and thereby there is a one-to-one mapping of the two limiting procedure, and hence we arrive at the barrier crossing problem there. The barrier could also be considered deterministic or moving in time or stochastic in time. Now we consider the very simplest model. This model could be extended to complicated levels, but we have to motivate the people who are going to attend this conference. I thought that I can present them in terms of the simplest model. Now we consider a stochastic model wherein the inputs and output into the reserve of an insurance company follows a Markov additive process. Note that is the Markov process with a linear drift in negative direction. See, the drift comes in the case negative. This is called the dual of the insurance problem. They take a business, they spend amount month by month, they go drifting the reserve. Therefore, the expenses go linearly down. The royalty comes to the company. The royalty comes as a jump. This is a random jump. This is called the dual of the original insurance problem. Now, what are the ZI? ZI are the jumps due to the royalties. They are random variable with commonly associated density function. The problem of interest in this model is to study the first passage time either for the ruin or to the risk level to cross the constant barrier x equal to k. I said that the compensation function is going to be introduced into study the philosophy of this problem. Now, what is the stochastic dynamics of this process? We consider fxt, that means at time t the process is a level x and the transition density at time t is denoted by x. When you go into the forward equation is the process wherein what is going to happen to the dynamics of the process within time and t plus dt and proceed to the limit as delta t tends to 0 and arrive at a stochastic differential equation as an integral differential equation. Now, fxt is the density of the process and a is the density of the jump and alpha is the drift. Now, the initial condition is the process is not starting from x equal to 0, the process starts from x equal to x naught. Now, this is a free motion process. We have not introduced, see, the jump goes from minus infinity to plus infinity, no boundary. Now I am going to introduce boundary. How I am going to introduce boundary? I am going to introduce a compensation function into the integral differential equation. The compensation function of Keelson is denoted by CXT. CXT is called the compensation function. Now, I must define what the compensation function. It cannot cross the barrier k, or it cannot go down the barrier x equal to 0, and therefore the compensation function is written in terms of for the first jump it is going to make outside the barrier is the compensation function. So this is the Heaviside function. This takes the value 1 when x greater than k, and the jump is crossing the k, and the density b is a plus the positive jump, and the CXT is called the compensation function. Now, we define the Fourier transform as well as Laplace transform because there are two variables x and t. F bar, g bar, and a bar are they transform this function. Once I take the Laplace and Fourier transform as defined above to this stochastic differential integral equation, we arrive at an algebraical equation. Now, you see, the algebraical equation is now in the form of the last one. Now, the left-hand side and a homogeneous process I am going to consider. The left-hand side can be proved as Keelson proved that is the root of the equation S equal to sigma L exists, and therefore he now says there is the root of the equation S is equal to sigma L. When S is equal to sigma L is substituted, since the root left-hand side vanishes, and therefore is substitute S equal to sigma L, e to the power sigma L x naught is nothing but minus C bar. Now, therefore, the compensation function is expressed. Now, the question is, how are you going to calculate this? Now, Keelson has given a technique of calculation T for defining the first passage time. The first passage time is denoted by M of T. It is going to jump over the barrier. Now, since according to the definition, this is a negative value, M of T is a probability, and therefore we introduce a minus sign there. Now take the transform, and if you take the transform and adopt the procedure of solving this through the complex analysis, you get M bar L is equal to 1 minus sigma L by eta, e to the power of sigma L x naught minus k. What is this eta? Eta is nothing but the frequency of the jump set. Now it can be inverted, and we got in terms of the Green's function in this form. See, the Laplace transform of the Green's function is given by this equation. Now go for the inversion. If I go for the inversion, my first passage time by crossing the barrier, it could be given in this form. The moment I put k equal to 0, I get analogously the first passage time by crossing the barrier x equal to 0. Now the Green's function is given a drift alpha. Any Green's function with a drift alpha could also be converted into a Green's function without drift by incorporating the alpha into the initial position of the jump. Now you see, I can write G alpha in terms of this is now hidden, G alpha in terms of G0 by introducing alpha t here. Now we go into the diffusion. Now we got the first passage time. We are now going into the diffusion problem. This is purely jump. Jump could be taken either the positive way or in the negative way, increasing the level of the risk reserve. Now I impose certain condition in going to converting this into a diffusion process. What I do that, in order the diffusion condition is going to give us an analogous good result, I play upon the density AX, I change the density AX into gamma AX, and then change the frequency nu into gamma square nu, and take the mean jump is 0, necessary condition for diffusion, and the variance of the jump is not 0, this is d, the diffusion of the jump is this is equal to d. And then proceed to the limit as gamma tending to infinity. Now you see that this converted into a diffusion equation in the transform space. The jump process takes the diffusion equation into this form. It is possible to invert now. If it is inverted, this takes in the very simple equation that you come across in heat conduction, heat conduction, whose solution is given to be in terms of the density function fxt. Now this fxt is a Green's function of the process, and since we know the fxt, the first passage time can be got by proceeding to the same limit on the right hand side of the first passage time already we have time. Now for example, see we are already the first passage time here. So proceed to the limit in the same way you get in terms of the Gaussian function t power minus 3 by 2 into the exponential of this. Now the first passage time for a moving barrier, what we introduce is the constant barrier. Now I am going to introduce a moving barrier. The simplest type of moving barrier that I'm going to consider, introduce to technique only, I get the A plus BT. Now it moves linearly. We can make the barrier also moving in exponentially. We introduce such problem in country neurobiology of the functioning of neurons to crossing at the show level, how the brain's functions work. For that, we have done a problem which appeared in Neurobiology Journal, the American Biology Research Journal. Now, we consider a simple process. In fact, I even omit alpha, the linear drift. It can be because once you go for a compensation function with the drift or without drift, one can be expressed in terms of the other by the transformation technique. Therefore, for the sake of simplicity, I am not introducing the drift there. Even if the drift there, the solution exists. The forward equation for this process is now as I have given. Earlier, you have noted that k is the barrier, so the Heaviside function is written in terms of x minus k. Now, a plus bt is the barrier. If it crosses the a plus bt, that means the barrier is crossed. Then the first passage time is going to be obtained. Such a boundary condition is defined as the compensation function cxt, and the jump should be in the forward direction. Now, we define the first passage time for crossing the barrier. This is a plus bt. See, it has crossed as a plus bt for the first time. And we can proceed analogously the same way as we have found in the constant barrier. And therefore, you got the Laplace transform as the first passage time, where in this form, where e to the power sigma l into x naught minus a is in the transform space, it is possible to invert it. And s is equal to sigma l is the root of the algebraic equation that you got when converting the diffusion equation into the integral differential algebraic equation. Now you see, we introduce a drift B with downward direction. You can study the same process by converting gxt in terms of gbt. Earlier we see that the Green's function could be converted in terms of the Green's function with a linear drift, alpha being the coefficient of linear drift. Now you see, B is the slope of the barrier. The barrier is moving a plus bt, and b is the slope of the barrier. This could have also been brought in terms of the Green's function. So gbxt are written. Hence, we can write down the first passage time proceeding where the barrier k to the kt is a function of t, time dependent. Now we can proceed to the first passage, the diffusion equation. We adopt the same procedure to the diffusion equation, and when we proceed to the diffusion equation, we arrive an equation similar to what we have arrived already, but b factor comes into play. Now we can go for the inversion as we have seen already, and hence for the moving barrier problem, the first passage time of crossing the barrier is given by this. Instead of k, you have a plus bt. The procedure more or less comes to in the same way. Your Green's function cooperates with that to get an analogous solution. Now we consider another process. This is a process called x equal to a is reached. Now when jump takes place, x equal to k is crossed. Mathematically, reaching a barrier is different from the crossing the barrier. When you reach the barrier, it is going to be at k. When it creates the barrier, it is going to be k plus dk. Now, jump is going to create a crossing of the barrier. Now, if you introduce a drift, it would be exactly reached. So, I introduce the condition x equal to k is reached. For that, I consider a model xt is equal to x naught plus alpha t minus sigma zi. But zi are all the jumps in the downward direction. Alpha is the drift in the positive direction. The compensation function for reaching the barrier is not an integral, not that. The compensation function for reaching the barrier is the product of Ct into Dirac delta function of delta of x minus a plus bt. Delta of x minus a plus bt this is equal to 1 when x equal to a plus bt is 0 otherwise. Now the Ct compensation function could also be arrived at, but now in order to proceed, I introduce the jump density in a fashionable way, taking the Pareto distribution. Pareto distribution plays a dominant role in insurance problem as well as in finance problem. More amount you put into your business, there is a possibility of getting more reward. Less amount is going to produce a less reward. Therefore, the Pareto distribution now said. Now the Pareto distribution say that the barrier and the jet density is going to be exponential. Now what we now do that, we find out the level of the risk. Now with alpha is the parameter of the Pareto distribution, and then there is an exponential decay belong to it. Now what I do that, I will write the forward equation for such a process, and the forward equation for such a process, the forward equation for such a process is given in this form. Now, since I introduced an exponential jump, ax minus x star, to derive a solution algebraically find it difficult, and therefore I give a transformation so that an exponential drift could be converted into a linear drift problem. Then what I now consider, now my transition density ax x star is converted into byy dash, where byy dash is now connected by x equal to exponential e to the power y. The exponential drift is converted into linear drift, and thereby you get a linear drift problem in the same way. This h function is nothing but the density function, the first passage for Ramsey. It is very similar to the ordinary density is going to be exponential form by this transformation, and we can introduce the compensation function to this technique, and hence we can solve this problem as we did in the case of other. Now, I want to introduce the embedding method. Now, embedding method and the compensation function are dual methods of studying barrier problems. Now, whenever you go for time-dependent barrier, it is much easier if you go to the Kolmogor's forward equation. Whenever you go for the time-embedding method, the time-dependent method, we go for the compensation function. When you go for the constant barrier method, it is easy to apply the solution, whatever be the type of the barrier and whatever be the type of the density, whether it is linear or exponential, embedding technique is now is introduced into the integral differential equation. You will see the elegance of the embedding method when you go into this. The classical model of Philip Lindbergh and in the dual model we considered calculate the expected discounted value of the dividend and an optimal. See, the procedure being said, we now jumped into the expected discount instead of the first passage there because they are analogous procedure. And further, the barrier is considered to be, even though the barrier is a constant, it is an arbitrary constant. We are going to introduce an optimal constant, So optimal barrier strategy could be introduced. The optimal barrier strategy was first introduced to Finati somewhere in 1953 or so. You look into Statistical Journal, you can see this paper is quoted in the very first paper for introducing the optimal strategy. Now, the dual model, the expenses are taken as proportional to the risk. The expenses are going down, and the reward comes in terms of the jumps, which are what we are going to say as random variable. Now, the solution so nicely turned in terms of convolutional divergeometric function, and the optimal barrier strategy is also discussed here. Now, lastly, we are going to consider, first we now consider the Lindbergh model, xt equal to initial input, and alpha tt is the premium that you get going up. St is the claim, therefore it reduces your risk level. So this is the total risk level, and this should be positive in order that your company survive. Now, the total jumps are now given by total premium amount that you spend is sigma zi. Zi are random variable. They are associated with a given density function. The density function should be chosen in such a way that you can arrive at an explicit scope form solution to your problem. Now, this problem of interest in this model is to determine the ultimate ruin. Yeah. The problem of interest in this model is to determine the ultimate probability of ruin. See, that means embedding technique. Similar types of problems are studied for storage model. That means that the dam becomes empty and the dam becomes overflow. We have seen that the Kilson techniques could be applied. In storage problem, Prabhu, we have done a lot of problems for barrier, and also Puri and Centuria. Lurie was in Chicago, Centuria was in Cornell. They did a lot of problems on barrier. Now, treating the model as two barrier problem, one at x equal to 0, the other x equal to t, we are going to calculate the expected amount of overflow, not the first passage. What is the total loss in the dam? What amount of water has been wasted because of the overflow? Likewise, in insurance company, what amount of in a business company, what amount of money you have distributed as dividends or bonuses, which cannot be recorded because it is above your upper barrier problem. Now, in general, these problems form a class of first passage problem, and the contrast to the dam problem are passage time to the emptiness of overflow. In neurobiology also, sequence of neuronal firing refers to as a spike rise arrive from the so-called spontaneous activity of response of neuron to external stimuli. The membrane potential changes due to random jump in both the direction. In between the jumps, there is a deterministic decay. The detailed version about this work has been done by myself and Professor Vasudevan when we were in Institute of Mathematical Science, Chennai. And we have done also several papers on Scandinavian Journal, appeared on Storage. Applied Mathematics United Journals appeared on Insurance and so on. Scandinavian Journal also produced one such paper. In model, given 1 and the dual model of interest, we are now going to study how this optimal barrier could be introduced. How? Now, we obtain the expected discounted dividend. Expected discounted dividend, that means e to the power minus delta t is going to come into play until ruin takes place. We consider also the ruin model to calculate the expected discounted optimal barrier to maximize the discount. It is to maximize the ordinary dividend. And then we introduce distributed random variables upon an optimal dividend strategy. What could be the strategy? Therefore, the optimal dividend could be obtained. Then we experiment the two components of income model we introduce. One is deterministic, other is time dependent. Now, I consider a simple optimal barrier problem. The simple optimal barrier problem is x of t equal to x minus alpha t plus s of t. Now see the jumps are st forward. Alpha t, it is now the business problem. You are constantly spending the money and you are going to get randomly input in terms of your pattern recognition or royalty and so on. This is the business problem. Now where s of t is the sum of the rewards that you are going to get. Alpha, it is the linear expenses, you see, linear drift. Initially, the particle, you have invested some money, initially is x equal to x naught. Now we can calculate the n of t is the number of Poisson jump. Claims are all Poisson. N of t is undertook, the jumps are Poisson process, is the Markov process. Now expected n of t is going to be deterministic function of t. It's always seen that mu is nothing but the expected value of this integral minus alpha and is assumed to be positive. Mu will always be assumed to be positive, rate of income. The process is a Levy process with skip free in negative direction. This process, a model research component where the gain due to setting up their pattern is the random variable. Is a random variable. The other one is determinate. In such problem, it is necessary to determine the expected value of the discount dividend. Now I define, instead of f function, I come to v function. Instead of f function, I come to v function. V of xkt is the expected value of the discount dividend at time t. How much time I have? Might be about rest 10 minutes.
Yeah, you have 5 minutes more. Professor, try to wind up in 5 minutes. Yeah.
My experience, at least I can manage in 5 minutes. Satish, definitely I will see that I finish in 5 minutes.
Yeah.
So vxt is the attempted discount. At the initial time, there is going to be a jump. The jump, there may not be any jump at all. There may be a jump that, therefore, it will be within the barrier. Mathematically, there may be a jump, it can be outside the barrier. Therefore, going to write down the backward equation of Kolmogorov, we can write v of xt t plus dt, initial time between t plus t. There is no jump, and there is a dem. E to the power of delta t, say that discounted down, and the jump is such a big size that it has crossed the barrier. So your reward is so great, you see, and therefore you have got all the amounts expected and the barrier is crossed mathematically, and then after resetting and the barrier is crossed, above the barrier amount you have disperses to dividend and other such thing. Therefore the resettle the process, not that. But initially we can vxkt, now it is resettled at vkt. This is called the embedding technique. And we write down the Taylor expansion per day and arrive at the integral differential equation. And there are two integrals. One is that within the barrier, the other one is outside the barrier crossing. The boundary condition is embedded into this equation. Now you see that let's say s function, the Heaviside function, takes a value 1 greater than 0, 0 otherwise. In terms of the Heaviside function, I transform the variable y to y plus x plus z and get the integral differential equation. Finally, we get, and then you see you differentiate with respect to x. X is not the integrating variable, x is a constant. So we are going to differentiate with respect to x, convert this integral into a differential equation. I converted an ordinary differential equation. This is the simplest form present in a component. We say we have now neglected all the intricacies of the problem, which gives the composite result. Now, we can, this being a linear second order differential equation, we get the two solutions and the general solution is there. How are you going to solve the boundary condition? One boundary condition is the greatness of the embedding condition is that once you get the general solution, feed into the general solution, you are ordinarily you are going to say the boundary condition is solved there, and then you can determine A and B are given by A, and then the solution is got. Now, Avanti has given a problem of that. Recently appeared in 2016 or so, when I was in ISI Bangalore. I gone into the solution. I thought that there is some error or so. I worked out in such a way that I got a result. That the result is now different, and then I was able to proceed to the limit as t tending to infinity or s tending to 0 in the Laplace transform language, and therefore I was able to get the solution for ultimate probability, ultimate gain, the ultimate level of the amount that has crossed the barrier, and which has could be dividend and other such things declared. Now, our solution finally in one form, we see that is obliged with the Gerber's solution. And we also see that the optimal barrier is purely a calculus problem. Once you solve it, then differentiate with respect equal to 0 and find the parameter, and therefore I can get K star as the optimal barrier. Optimal barrier could be extended in terms of the parameter alpha and delta, or it can have mu and alpha. In different decomposition, we write down the optimal barrier, and hence the solution for finally optimal barrier is cast in this form. Now, similarly, we can consider a barrier with proceeding in the same way for the dual problem. Yeah, I'm going to proceed.
Can you summarize in another 2 minutes?
And now we see that how neatly we get the solution to this problem, and hence ultimately I see that my solution is arrived in terms of what is called the 1f1 functions, hypergeometric function. You slightly impose. The more complicated results do also arrive. You play with the jump densities in different form, you get the solution in different form. Dual process is also considered, and there also we can get the solution, and thereby I hope in the last process of completing, and hence I conclude that embedding technique and Kielsen technique are the two-way process of obtaining boundary value problem which appear any language or any branch of discipline, the social sciences, including mathematics. So this is the problem in stochastic processor, which includes the real application in many different directions. It is possible to also see that the embedding approach is equivalent to the Kielsen's approach by establishing the solutions are one-to-one and thereby matching the solution in the transform space. Now there is still a lot of problems in the rope, and I'm already 85 flat. I saw the students take it. Unfortunately, present generation students, they are there, but they don't come with good enthusiasm to proceed with the problem. I hope at least, if I not done best here, I hope some of this reason could have gone through the details of this and how to apply the embedding technique as well as the compensation function. Matching these two is more important. We have not seen the solution of matching. It should be possible, I hope. I formed some frame of mind about that. I hope I should be able to solve it with the help of some of my students. Thank you very much for giving me the opportunity. If any question I'm able to answer.
Thank you. Quick questions, if any audience want to clarify, please. It is open now.
Which one?
Any specific questions if the audience will have, they will. We are open now.
Yes. Any questions to be answered?
Yes. And,
yeah. In the absence of no question.
Yeah.
If you can also correspond to me through my mail.
Yes. Yeah. Professor
Vital's email. I will be able to answer that question, and at least I will be able to give the direction to proceed. I thank you very much, especially Mr. Satish Kumar and his team, for giving me an opportunity at this age to come before you for virtual lecturing. And then once again, I thank everybody who cooperated with me. Thank you very much.
Thank you, Professor.
Thank you, Professor.
So let us move on to the next speaker. The next speaker will be Professor D.K. Ghosh. D.K. Ghosh did his BSc and MSc from Bhagalpur University, Bihar, and PhD in statistics, specialized in designs of experiment from ISI Delhi Center under Professor M.N. Das. Ghosh was professor and head of the department, Saurashtra University, Rajkot, since 1986. And presently he is assigned as a UGC BSR faculty fellow after his retirement. He is a fellow of Royal Statistical Society and also he is a fellow of Gujarat Science Academy. Several positions held during his tenure in a service as a professor, and he retired, I think, as a professor, Department of Statistics, Wsta University, Rajkot, from 1994 to October 2013. He has got an academic and administrative experience of 44 years, research paper published more than 150, and PhD supervised 43, and 3 books he has published on distribution theory, published by Saurashtra University, Rajkot, Gujarat. Factorial experiments published by Saurashtra University, Gujarat. Biostatistics published by Saurashtra University, Gujarat. He has 4 chapters in 4 books, and he has several awards, CSIR, JRF, and SRF, and he is the best awarded paper by Gujarat Science Congress in 2004. Visited nearly 16 visits he has made abroad, and presentation abroad he has 11. Reviewed papers for more than 20 national and international journals, and editorial board in more than 10 journals, including journals of ISPS, Designs of Experiment section, and Indian Journal of Statistics and Applications, International Journal of Agriculture and Statistical Sciences. He's an associate editor. And he has professional membership in several bodies, and he is in several committees, and also he had a major project, UGC major project, preparation of table for PBIB design with the 2 associate class sanctioned to be, during 1992. He has chaired more than 150 sessions, delivered more than 50 invited talks, and he was in several several selection committee as a scholar. And it is very nice to have such a personality for the presentation here. On behalf of the organizers and on behalf of Kerala University, I welcome Professor D.K. Ghosh for this international webinar, and I request him to present his paper.
Thank you. First of all, thanks to Professor Satish Kumar, who is organizing such conference on National Statistical Day since existing of the National Statistical Day. I am also thankful to the chairman who gave me this opportunity. Diagonal cross is generally used in the biological field, that is for plant breeding and animal husbandry. Diagonal cross is an experiment in which 2 treatments are crossed each other to have a new treatment, which will be considered to be a promising variety of crop. If we are interested to find a new variety of best crop, we will go for an experimentation by crossing the 2 new cross of different types and then testing the experiment which cross yields best and promising varieties of crop. Griffith was the first person who introduced the concept of diagonal cross experiment by crossing 2 treatments together from all possible combination of B treatments, and finally the V square crosses from B treatments are following. So you can see in one we have all possible crosses, 1, 2, etc. The diagonal elements are self crosses, and off diagonal experiment are non-self crosses. So in the upper of diagonal element, it is I is less than J, but in the lower diagonal matrix, the I is greater than J. So accordingly, the Griffith classified the diagonal crosses. So we can see that there are V crosses in the diagonal, which are called self-cross experiment. There are V into V minus 1 by 2 crosses of I into J, where I is less than J. These crosses are called F1 crosses. Again, there are V into V minus 1 by 2 crosses of I into J, where I is greater than J, and these crosses are called reciprocals of F1. Hence, the total number of crosses are V self plus b into b minus y2 f1 plus b into b minus y2 is the reciprocal of f1. If you add it, we'll get the b square treatment crosses. But however, Carnot, he discussed the construction of parallel cross using the randomized block design. While he thought the RVD is a large number of crosses, so later on various other authors discussed the construction of use of parallel cross experiment using balanced incomplete block design, partially balanced incomplete block, and so on. And also mutually orthogonal lattice square design, which I will explain here. Now, how many types of parallel crosses we have? There are two types of parallel crosses plan. One is called complete parallel cross plan, and the second is called partial parallel cross plan. What is complete parallel cross plan? A parallel cross experiment is said to be complete parallel cross plan if all the crosses occur an equal number of times in the experiments. Further, the variances of all the lines of the parallel cross are same. That is, all the lines are estimated with the same variances. What is partial parallel cross plan? A parallel cross experiment is said to be partial complete parallel cross plan if some of the crosses occur n1 times while the remaining cross occur n2 times. In case of partial parallel cross plan, the variance the same. Instead, variances of some of the treatment contrast is same, while the variances of remaining treatment contrasts are different. Hence, the line effect will be estimated the two types of variances. And then after that, they define a very terminology which we want to estimate. That is called general combining ability effects. The general combining ability effect is an effect of combining ith and jth two lines to give the best yield. This effect is estimated using least square method of estimation from the linear model. Now, what happens? The Griffin again explained the four types of system of CDC plan, and they call it is system 1, system 2, system 3, system 4. In system 1, what he did, he said, let there are P lines in a complete parallel cross plan of system 1, which contains the following crosses: P cell crosses, P into P minus 1 by 2 F1 crosses, and P into P minus 1 by 2 reciprocal of F1 crosses. If we add all those things, then we'll again get the P square crosses. What is system 2? System 2, he add only P cell crosses and P into P minus 1 by 2 F1 crosses. So total cross will be here P into P minus 1 by 2. Then the system 3 is nothing but the total of F1 crosses and the reciprocal of F1 crosses. If you add it, you are getting P times P minus 1 crosses. And finally, it is a system 4, where we take only the F1 crosses. And F1 crosses is number of times P into P minus 1 by 2. See, in this investigation, we deal only the system 4, where the P into P minus 1 by 2 crosses will be taken, where I will be less than J. So there are several methods of construction of complete parallel crosses plan. First, I am discussing one simple, and I will skip to the last where, because of time, where I will explain the detail about the example, analysis, and the efficiency factor. I just want first explain method 1, then I will skip it for other methods. So this method is used by using resolvable balanced incomplete block design where K is even. Why? If K is odd, then the crosses is not possible. So we will take only K as even. So you have a resolvable BIBD with parameters B, B, R, K, and lambda. So you construct this thing, and you have the B blocks. In each block, we have the K plots. It means and K is even. So what we take each block, we take two treatments and cross it. Since we have the K plots, treatment in a block, so there will be K by 2 crosses in each block. And total number of blocks are B. So total number of crosses will be into K by 2. And where each crosses will be repeated 1 time. So what is the, let us take a simple example of resolvable balanced incomplete block design, where B is 4, B is 6, R is 3, K is 2, and lambda 1. So the blocks are 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 2, 4. So if I cross in 6 block, 1 cross 2, 1 cross 3, 1 cross 4, 2 cross 3, 2 cross 4, 2 cross 4. We got the, how many crosses? 6 crosses. P is 4, so 4 into 3 by 2, the 6 crosses, I got it. But what is the drawback of here? You are getting only 1 cross in 1 block. If it is 1 cross in a block, then there is a problem of the error variances. Got its precision will be less. So what I did, I made it as a resolvable BIBD. So what I did, the 6 blocks are grouped into 3 blocks, and each block contains the 2 crosses, such that not a single block is containing more than 1 line. I call it lines, not treatment, we call lines. You can see every block has the 1 and only 1 lines. Now, I earlier explained that Arnold told that it is very easy to construct the diagonal cross plan using the randomized block design. If you see this thing, it is also a type of randomized block design. The experiment here, CDC, is obtained as a randomized block design. So I think I have only 15 minutes time. I am jumping to the what's called variance. This I want, it's a very, very interesting problem. I used the construction of CDC plan using double balanced incomplete block design with parameter B is equal to 4 lambda plus 3, R is equal to K is equal to 2 lambda plus 1 and a lambda. So what you do, you construct a balanced incomplete block design, which this parameter, I have taken lambda is equal to 2. So then the parameters become B7, R3, K3 lambda 1. And this is constructed by using the Gauss field 4 lambda plus 3. Here 7 is a Gauss field, because 4 lambda plus 3 is 7. So we have to first find out the primitive element of the Gauss field 7. The primitive element of Gauss field 7 is 7, as the 3 is the primitive element of GF7. So I took all the powers of the primitive element 3, and then after that, I took the odd power of the primitive element one side and even power of the primitive element the other side. And using this thing, I got the 2 BIBD, D1. This is a block of one BIBD, and this is a block of other BIBD. And hence we call that double BIBD, because the B is same, B is same, R is same, K is same, and lambda is same. Now what I take a block from the D1 and take the first block of design D2 and cross respective lines. So after crossing respective line, we will get the 21 crosses. Our B is 7, so B into B minus 1 by 2 is nothing but 21 crosses. So I have total 21 crosses arranged in 7 blocks, and each crosses is occurring 1 time, whereas each line is occurring 2 to 4 to 6 times. And if find out the incident matrix, we can find out the sum of square of Nij square is 6, and all the product of the Nij into Mj for all the blocks is 5 times. Hence, we can say it is also a some CDC plan. This was due to me and my friend. And now I come to the analysis. So this is, let us have a P lines for the CDC plan, which is arranged in the B blocks. And each block size is K. So the linear model for the CDC system is defined as Yij is mu plus Gi plus Gj plus Sij plus Eij. See here, Gi and Gj are called general effect or in other way you call general combining ability effects. And SIJ is called the specific combining ability effect, but it is very complicated. The time constraint, so I will not discuss the estimation of the specific combining ability effect. We only go for the general combining ability effects. If I want to write this matrix model in the matrix form, I may get is y is equal to mu times 1n plus delta 1g plus delta 2b plus e. And y is nothing but n cross 1 a observational vector, mu is a general mean vector, 1 is denoted n component, and g is also a vector of p lines, beta is a block effect of the b blocks. And a quality is that delta 1, delta 2 are corresponding design matrices of n cross w and b, n cross b. And these are the so many things that I will escape it here. But when I want to form C matrix of this linear model of the CDC plan, I make it as a C matrix of design D as a GD minus the ND prime by K. K is scalar here. And it was defined by some Sudhir Gupta and others. The GD can be explained in the term of a matrix of a P by P matrix, with GD is equal to a diagonal matrix WDI and WDI prime, and the off-diagonal elements of the matrix are symmetrical, so GII dash and GII dash. And one column that they say the product of the two delta 1 prime and delta 2 is always ND, whereas the product of delta 1 prime and delta 1 is a GD. And after solving, I can use this as a normal equation, and this normal equation will give the CD matrix into G estimate is equal to Q, where Q is equal to total. And I estimate if this thing, though this is a CD is a generalized inverse matrix, but after solving all these things, I may get as the estimate of Gij 1 by theta Qi by using some other matrix techniques. So variance of Gi estimate 1 and Gi is equal to 2 by theta sigma square. And efficiency factor of any series plan compared to the randomized block design can explain as efficiency is equal to ratio of the two variances, one variance under the randomized block design, other variances under the complete diagonal crosses plan. I think how much time I have? How much time I have?
Hello. Yeah, you have another 12 minutes, professor. Hello.
12 minutes. Okay.
Yeah. So 12 minutes you have.
This I want to explain in detail. This is a complete diagonal cross using Latin square design. Actually, Bose was a pioneer for introducing virtually orthogonal Latin square designs, and I have used this design for the construction of CDC plan, where what I did, I will take a mutually orthogonal class by taking P is equal to 40 plus 2 with T greater than or equal to 1. This I will all completely left it. That I will go to the theorem. If there exists a standard Latin square design of sign P, where P is an odd number, and by deleting a column, we always construct CDC plan with B into K minus 1 by 2 crosses, where each block contains K minus 1 by 2 crosses, and each line is repeated P minus 1 times, where crosses are arranged in B blocks. But let us not be, just come to the, so this is actually the incident matrix of a CDC plan if I construct from the standard Latin square design. And if I take the product of n into transpose of n, then it gives in this form, where P is a number of lines. So you can see the diagonal elements are P minus 2, and all the of the elements are P minus 2. So that NNS matrix is symmetric. When it is symmetric, it is very easy to find the inverse. No need of going for G inverse. The ordinary inverse, I can also get it. See, the analysis parts I discussed a little bit, but go to the later on. See, on the basis of CD matrix, I explained you, it is a GD matrix minus n into n prime by k. So what was the GD? GD was defined that diagonal elements or WDI means a number of times each line occurs in the entire CDC plan, and that was p minus 1 time. And of diagonal elements was there number of times each cross occurs, and in this plan each cross occurs a 1 time. So all the diagonal elements are 1, all the diagonal elements are p minus 1. And I have already showed you earlier that n into n prime matrix will be nothing but this matrix whose diagonal elements are p minus 1 and off diagonal elements are p minus 2. And number of crosses per block, it was k minus 1 by 2 or p minus 1 by 2. So we have to solve it by using the diagonal elements for both matrix and the off diagonal elements for both matrix. So this I have solved, and after solving so many things, I got this answer. This is the matrix for the diagonal elements. Similarly, after solving off diagonal elements, I got this matrix. Finally, the C matrix of the CDC plan can be written in this form. And this matrix, I want to write out in the form of theta times IP minus 1 by PPP. Because if I can write down any matrix in this form, then I can say, obtain the non-zero eigenvalue theta. And that's why theta, which is non-zero eigenvalue, is nothing but this value with the multiplicity b minus 1. Because of this, using this theta, I can find out the estimate of general compounding probability effect lines and its variances. So this is the line, GI line, some GI lines. I can get the variance. This I got the variances. And after getting variances, I want to find out the efficiency factor. And efficiency factor are often corresponding to the complete randomized block design. So in case of complete randomized block design, the CD matrix can be written in the form of R times P minus 2. If it is not the diagonal cross plan, it will be 1 by R this plan, where R is nothing, not the reflection side, where R is the number of crosses occurs. So here R is only 1. So this part will be this much, and variance of the CD plan ratio. I can get this is the ratio of variance of plan, and we got this is the, this is the efficiency factor of the CDC plan. I think I'm completely exhausting my time. Within 2 minutes, I'm completing.
Okay, Professor.
This is a just example of standard lattice square design, because if each row and each column is the same, then it is called standard lattice square design. You can see each row is column, etc., etc. So I have to delete any columns. This is called the trial and error method. I delete the 6th column and shifted 1 to column here and there, and taking the 2 lines and crossing them. After crosses, I got this CDC plan in 7 lines, and each cross is occurring only 1 time, and we have the 21 crosses, and each block contains 3 crosses. And this is the all CD matrix, etc. And finally, I got the efficiency factor, which type experiment P is 5, 7, 9, 11, and 13 with this much block sizes. And since each cross occurred 1 time, so R is 1. This is variances of corresponding randomized block design. This is the variance of the line effect using CDC plan. This is so you can just conclusion what I made it. You can say as the P value, this number of line increases, or the number of block increases, the efficiency factor also increases. As the number of lines is higher, we are nearing approaching to the efficiency as 1. And these are the references. This is all references we made. I hope I completed it in my time. Thank you very much.
Thank you, Professor. Now, some quick observations if you want to have. Professor Victor Babu is here along with us.
Yeah, please ask me.
Yeah. Nice to see you, Professor Victor Babu. And Victor Babu is also works on designs of experiment. Yeah. If you have any quick comments on the talk.
No, I don't have, but I have appreciation.
Yes,
Sir, your presentation is good. Your work is so nice.
Yes.
Hello, sir.
Thank you. Thank you.
Only one doubt I have.
Yes, sir.
You are using the standard lattice square design and you are deleting one column.
Yeah.
And it will become Newton squares.
I can do that also. I have not shown here. I have did that part also. Even I have done using the orthogonal lattice square design also I have done. And if you have the even number of lines, then there is no problem of deleting any columns. Because if even number of size of that is orthogonal line, then you can cross 2 by 2, there is no problem. But when you have the odd number of lines, then we have to delete any column so that no cross is repeated. There I have to use a trial and error method. Unit square also I have used. The advantage of unit square will be there and disadvantage also. Since unit square is not incomplete lattice square design, so we may not get the total number of crosses, that is b into b minus 1 by 2. Instead of that, I will get the less than that part, and that will be the partial diagonal cross plan, which I have already shown in some other papers. This we have already published that part.
Okay.
But diagonal cross is not possible because you're not getting the b into b minus 1 by 2 cross. But PDC is always possible.
Okay, sir. Okay, thank you. Thank you for the clarification.
So if there were no other clarifications required, let us thank the speaker, Dilip Ghosh, sir. Thank you very much, sir. Yeah. Shall we move on to the next speaker?
Yes. Thank you, Professor Ghosh, for very nice presentation.
Thank you, Professor Satish, and also our chairman, Professor Ismail.
Yeah. Thank you, Professor G.K. sir. Very interesting talk on designs of experiment, and so we enjoyed your presentation and new work. Thank you very much. We have the next speaker, Professor B.S. Biradhar from University of Mysore. He is a professor of statistics in the Department of Postgraduate Studies in Statistics at the University of Mysore. He has been working in the department for the last 15 years, and earlier he was working at Karnataka University, Dharwad. And his research interest includes the non-parametric inference, statistical inference based on rank set sample, where a lot of work has been taken place in University of Kerala also. Statistical inference based on information theory, goodness of fit test, reliability and survival analysis. He has more than 20 invited sessions. He has presented his interest, his talk, and he has contributory talks for 11 conferences. In 11 conferences, he was a resource person in 5 workshops or refresher courses. He has participated more than 15 conferences and organized more than 7 workshops or conferences. Has conducted many seminars also, and he has taken a lot of. He has many administrative positions in the university, and he was a member of PGBOS in many universities, as well as he was a BOE member in many universities. He is a member in scientific societies. He is associate editor, International Journal of Agricultural and Statistical Sciences, and he was executive member of Indian Society for Probability and Statistics, life member of Indian Society of Probability and Statistics, and he has more than 12 publications in the reputed journals. He worked under the well-known scholar of probability, Professor Chikkagowda, and he has 2 chapters in 2 books, and he has a book on mathematical statistics prepared for the Karnataka State Open University, and guided 2 PhD and now guiding 3 PhD scholars. On behalf of the organizers of this international webinar, I extend a warm welcome to Professor B.S. Biredar. Professor B.S. Biredar is speaking on generalized median test for 2 sample location problem using multiple type 2 censored data. So I welcome you, sir, for this webinar, and the session is open to you now for the presentation.
Thank you, sir. Thank you very much. Thank you for the nice words. First, I'd like to thank Professor Satish Kumar for giving me an opportunity to present my talk here. So every year he used to, invite me. So thank you, Professor, for giving me an opportunity.
Slides are not seen.
No, thank you, Professor. Thank you. I'm getting.
Yeah, okay, so Professor, you are busy. Okay, you are busy, very much busy with your.
In between some other
schedule. I think I start on time actually. I think I thank Ghosh also because he.
Yeah, we have time. No problem.
Yeah. You are the last speaker and you have sufficient time in this session. You can go up to 4:40. Yeah. Yeah, 4:30. You can
something.
Yeah, you can go up to 4:30 and 5 minutes we can have discussion.
Yeah, my talk is as I am recently interested in rank search SAM theory, but this is the paper I wrote. Now what I am doing here is so you know that median test is a competitor to the well-known Mann-Whitney-Wilcoxon test for testing and median number of in the combined sample. It counts the number of IJ observable median. But in this article, I generalized this median test to the case of multiple sensor data. So what is multiple sensoring data is multiple sensoring means observations within certain intervals are not available, or observation within certain sample quantiles are not available, or you can exclude because of to increase the efficiency also. So because of several reasons, the data, only some subsets of the outer statistics are available. So this type of censoring or this type of data, we call it multiple type 2 sensor data. In this paper, we assume that observations on some subsets of outer statistics are not available. Censoring in such a censoring we call multiple type 2 censoring. So we generalize the usual median, generalized median test to the this type of data, and we develop locally more probable rank test. And here there is a problem. The problem is usually the scores generative function. I will define it later. The scores generative function associated this. So to find the asymptotic distribution, it requires the score generative function must be continuous in the interval 0 to 1. But here in this case, it has finite number of discontinuities. Therefore, the usual, the standard result of Chernoff-Savage or Hayek theorem and 1961 theorem cannot be employed to find the asymptotic distribution. So what we have done is we have modified a Tupac-Hayek theorem to establish the asymptotic normality for the location and scale alternatives, and this is applied here to obtain the asymptotic distribution. And also, once we obtain the asymptotic distribution, we study the effect of censoring on the asymptotic efficiency. It is found that as long as the median is available, the data within the combined sample, the median data is available, there is no effect on the censoring. That is the tests based on this multiple sensor and that is complete data almost So again, there is a gain in efficiency due to middle censoring when the underlying distribution is normal, logistic, and extreme value. So in fact, usually expect that there is a loss, but here there is a gain in efficiency by removing some portion of the data. So this suggests that it is possible to improve the efficiency of GM test by discarding suitable portion of the data. So this is another finding. So order data arises naturally in many branches of applied statistics, including survival analysis, life testing, biomedical sciences, duration analysis in economics, reliability theory in engineering. Sometimes even recorded observation may be lost by accident or by negligence, or even they are available, we may discard it if they are not found reliable actually. In many of these situations, this multiple sensor situation arises. Here we consider multiple type 2 sensor data where some sets of observations, some ordered sets of observations, including extremely small or extremely large observations from the combined order samples are removed from the data. So of course there is a lot of work has been done in the parametric estimation. David and Nagaraj 2003, Fernandez 2006, but not much work has been done in the case of non-parametric, except the Mehrotra, Johnson, and Bhattacharya in 1977. So they have derived LMP rank test in the case of triple censoring, where the data are left censored, right censored, and censored once in the middle. And except this, they have not studied any other properties. And Chikkaudra and me, actually, Chikkaudra was my 2010, published a paper in Communications in Statistics, where we obtained LMP rank test and studied the asymptotic distribution. That is, obtained asymptotic distribution of LMP rank test and studied the effect of censoring on the asymptotic efficiency of the two sample test for location, scale, when the combined order sample from different underlying distributions are censored, using triple and lower order type 2 sensor. The main objective here in this paper is we adopt this that is procedure developed by Chikkaudra and Birada to the median test for above testing problem for multiple type 2 sensor data, and then to study the external censoring. So we derive here. So we consider the standard, of course, this is the good old problem, but this is applicable to the sensor data, that is multiple type 2 sensor data. It is even though we share multiple type 2 sensor data, but this is applicable in many senses. Even you can say that group of data is not available or not suitable, or that contains more Fisher information. In such situations, you can use it. So we have the two independent random samples from absolutely continuous distribution, fx and gx respectively, with the corresponding density functions fx and gx. And we used to test the hypothesis fx equals to gx for all x against the location alternative gx equals to f of x minus theta. So gx and fx are the same, only with respect to theta location parameter they differ, otherwise the form of the distribution is the same. That is, here we can say that x is stochastically smaller than y. And theta larger than 0. For other alternatives, you can suitably modify the critical regions for theta less than 0 or theta not equal to 0. Of course, LMP test applicable for only one-sided. So towards this, what we do is we combine the x and y observations and order them. So these W1, W2, Wn, these are the ordered observations of the combined sample. W1 is the smallest among x and y observations. And like W2 is the second smallest among x and y observation, and then is the Wn is the largest among x and y observations in the combined sample. N is the combined sample size, and these ZIs are indicate random variables in this order. They identify whether which one is y, whether it is y or whether it is x. It can be identified from these ZI observations. That ZI is one, whether it is an x observations or x y observations. Once we have these ordered, then what we assume here is that is there are two R minus groups in all, and we assume that only R minus blocks of consecutive, I mean, R blocks of orders, consecutive order statistics are not available. Yeah, but still, here this MJ is the number of X observations, and here we assume that the X's and Y's in the number of Y's in the two random variables. Now NJs are random variables, and this NJ is the MJ plus NJ, J equals to 1 censored or observed depending on which group it falls in. To develop the rank test, I consider the location parameter fx theta equal to f of x minus theta. This is the score generative function 5f, which depends on the underlying distribution f, and it is what is the score generative function is this is a function defined on 0 to 1, which is which doesn't depend on n, which can be written as difference of two non-decreasing functions. Therefore, it's not constant, and it is square integrable. So even some authors call it a square integrable score function. And this can be obtained from the expectation of this. Actually, this is, and these UIs are the order statistics. It is some 0 to 1. Yeah, to obtain straight away, I write the LMP rank test with critical reason. Is this is the test for the test. This is general, I mean, location test for location problem based on type 2, multiple type 2 sensor data. This first term of this first portion, this portion is the some of the scores of the Y observations associated with this observed data, and whereas the second portion, is associated with observation censored, actually proportion of Y observation censored in each group. And this is actually average of the scores associated with the Y observation associated with the censored group. This indicates censored group. So for this is the for each, whereas this takes the actual score here, whereas this scores for censored data. So this is the LMP rank test for the type 2 multiple type 2 sensor data. Of course, usual type right censoring, left censoring, middle censoring, all are particular cases of this multiple type 2 sensor data. Yeah, I'm not. Of course, this has been proved by Mehrotra and even me and Professor Chikauder. But Mehrotra has proved this is for general alternatives. That is fx theta. Theta could be is any parameter, but we have proved this can be this by the location parameter. Then simplifying after some simplification. Now this is the location. Test for location problem. This is the location problem. Now, so we confine to the generalized median test. So we know that it's well known that generalized median test is asymptotically most powerful for against double exponential distribution. Therefore, we consider a double exponential distribution here, fx1 standard double exponential distribution, and this is the score. That is 5f, obtained from this expression. So this expression. So this is sine 2u minus 1 for u lying from 0 to 1. And here f is actually this, density of double exponential. And this is the expected value of this actually. And now these are the scores for uncensored data actually. So scores for uncensored data. Now scores, these are replaced by the median scores. Actually, these are called, you can say this is the median score and median score generative function. Now T star Zn, this is of course n is also random variable here. This is the test statistics generalized median rank test statistics for multiple type 2 sensor data. Again, the first portion of this statistics on the right hand side, this represents the test statistics for observed data, observed portion. This is for the censored portion, and this is the greater than or equal to constant, then you reject the hypothesis. This is generalized median test based on the multiple type 2 sensor. This test is asymptotically optimum in the case of density f of the double exponential type. Of course, for more for this censored group. So therefore, from this, you can go back to the this particular test minus n plus 1 by 2. Asymptotic properties to limit k by n tends to, and p naught. These are the censoring for is k is npi if n5 is an integer. Otherwise, it is largest integer plus 1 if npi is not an integer. So therefore, this SGF corresponding to the censored portion is obtained as sin 2i minus 1. This portion related to the observed portion, and this is average of these pi phi. That is, this equals actual pi bar pu is integral 1 over p2i minus 1 minus p2i integral 5 du in this interval. This is the pi pu or this integral. Well, uncensored pi pu. And of course, where what is pi pu, that is by that integral you will get this. If you recall the scores generative function for the median test, and this is minus 1 for u less than half, and 1 by 2 for u equals to half, and this is 1 for u larger 1 by 2 to 1. Actually, this is modified. Pi bar is minus 1 for these censoring points are less than half. And the censoring portion, and this is again observed portion associated with the score generative function associated with the multiple type 2 sensor data. The SGF 5PU defined by 4 points is here is multiple type 2 sensor version of the SGF. So here you just see here this is here at each p0 p1 p2, that is p2 r minus 1, the standard procedure distribution of is not applicable. So therefore we developed a sufficient condition using Tupac and Hayek theorem and obtained asymptotic normality. So under the conditions of I'll just condition on 5, that is pi p, we can this is the condition. This is called Hoeffding condition. Usually we say that these are square integrable, but here we assume that it is a little more than square integrable actually. I hope. And P, that is obtained by either this equations or this equation. Okay, so under the conditions A and B theorem, that is the GM test just I mentioned in the previous section, is asymptotic normal with mean mu n p theta n tau square np theta, where mu np theta divided by n into 1 minus lambda. 1 minus lambda n is limit mn divided by small mn divided by capital N. So I equals to 1 to r minus 1, this integral, plus this is again censored portion. This is uncensored portion. For uncensored portion, yeah, if it is a complete data, then we will get exactly this expression. This expression would not be there actually. So this pi q bar is as defined earlier, but this is not the correct equation number. Yeah, this is your variance. But still for under null hypothesis, this is much easier. I put theta equal to 0, then you will get mn prime equals to 1 and these things. Yeah, since the original the condition A and B says that we have provided a sufficient condition. What it says that that is the scores and score generative function, those conditions satisfy for uncensored data, then they satisfy for censored data also. Therefore, since the original SJ and scores for uncensored data satisfy those conditions, therefore they also satisfy for censored data. Hence, under the null hypothesis, the proof is obtained by. So here, what we do is this mn and ln equals to, and this is very much required actually. This one under null hypothesis is required to find the asymptotic efficiency of the test procedure. Whereas this is this is as it is required. You have to find the derivative of this with respect to theta, and theta equals to theta naught r under the null hypothesis. So this is the proof of the theorem. And now, the application of this asymptotic normality is asymptotic relative efficiency. The asymptotic relative efficiency is that is ratio of efficacy squares of the efficacies of the test procedures under comparison. But the condition is that both should converge to the under the for the same distributions under the sequence of Pitman alternatives. What is Pitman alternatives? That is theta I tends to theta naught as a constant over the square root of ni actually. So that is under the Pitman alternatives we obtain this. So this is the efficacy of our test procedure, and which we obtain this one. Now efficacy of the other test procedure, that is the test procedure based on the complete sample. This is replaced by 5q, replaced by the original, uncensored 5q. That is simply you write 5 bar, they will get the efficacy of the test for uncensored data. That is, this is the test for uncensored data, and this is related to the ANI related to the uncensored scores actually. And this efficacy can be obtained by replacing 5p and 5p in the last expression here. Okay. So therefore, here of this generalized median test related to the median test for the complete data. So it was given by efficacy of TMZN square divided by efficacy of SMN square or whole square. Okay. Now, of course, when we remove the data, then natural question would arise naturally whether there is any loss of efficiency or so. While doing this, we found that actually in fact there is a gain in efficiency. Maybe it is because of the fact that we take the average of the scores, that is second portion of the data. If you recall, the tested six for the second portion for all these uncensored data, it has gain in efficiency in fact actually. So loss of efficiency is 1 minus area of that for any kind. One thing we assume here, for any kind of multiple type 2 censored data, one of the observed portion contains median of the data. That is median. So median of the data is available within this. If that is the case, then efficiency of the multiple type 2 sensor data is coincides with the efficacy of the that is f0 is 1 by 2, that is corresponding distribution function. The expression 5 and 6 coincides with the efficacy of the median test for uncensored data. This one. So therefore, of course, for efficacy of uncensored data, one can refer Reynolds and Wolf for any other like Hayek and Sidek and other books. Thus, what we do is, therefore, so there is no loss of efficiency. If median is, as long as median is available, there is no loss of efficiency because it contains all the information that is required. Thus, in the case of GM test, unless the censored block contains the median of the combined sample, any kind of multiple censoring considered here has no effect on the area of this test. This is because, according to our assumption, required for the construction of the median test is available, irrespective of whether the rest of middle sensor data or that contains the median again can be obtained using, of course, that is, what is this 4.7? 4.7 related to the that is score generative function for multiple type 2 sensor data. If I recall what exactly, if you want, I'll show you. Yeah, this is what exactly the 4.7. So this one, and this 5.2 is, yeah, this expression. Using this expression, so I have obtained the efficacy of TMZN, and which is this, and Q2 is in fact 1 minus P2. And this is what exactly. So what is this P1, P2, MPCs? What is P1 is lower, that is up to 0.5, that is 45% of the data below, before P1 are observed, in fact, actually. This is the observed, that is both extremes are observed. On the middle portion, that is 10%, between the P1 and P2, those are censored actually. And this is between, that is 20% of the observations in the middle portion is censored. So middle portion of the data here. And for normal, you just see here, as censoring portion increases, actually this efficiency increases actually up to as long as up to 70%. But for logistic distribution, again, it increases here. Then when it crosses 70%, as it goes towards extreme, then it decreases. And of course, this double exponential is actually 1 minus 2 P1. This is a linear function of P1 actually. Therefore, it decreases as P1 this decreases. And of course, you just see here, there is heavy loss of efficiency for Cauchy distribution, because if you censor the tail portion of the data, naturally this is expected. Therefore, because the Cauchy is the heavier tail distribution, therefore because of that there is a loss of efficiency for Cauchy distribution. On the other hand, normal is light tailed and this is a medium tailed, and you just see as we cross 70, then there is a loss of efficiency here. Otherwise, in this case, when you censor in the middle portion, so there is not much loss here. So this is for one thing. Then this is for symmetric distribution, and for there is another extreme. Different combinations here, and here also there is a gain in efficiency here. There is we have taken different combinations, even though total proportion would be same, but we have varied P1 and P2 actually here. Total proportion would be same, but there is a variation in P1 and P2. Total proportion is same, but you just see here, this is here. It depends on the what portion you censor. So it depends on that. Even though the total proportion is same, but as you go, towards if you do not towards the middle, there is no much loss of efficiency. The same thing will continue. The same table will continue here. So these are some of the observations. The area of GM test related to median test are computed for normal, logistic, Cauchy, double exponential, and extreme value distribution in the case of middle censoring. Of course, I already given the explanation for what those table values indicate. In the case of two medium tail distribution, the normal and logistic, the area first increases, then decreases as the MPC increases, middle portion of the data. Actually, middle portion of the data increases towards, if you censored more in the tail, then it decreases actually. There's a gain in efficiency when the samples from these two distributions are subject to middle censoring. Even there is a degree of censoring as heavy as 70 and 60% respectively. For the first two values actually, distribution. The double exponential. So actually for the double exponential distribution, ARE values, of course, we can find it is 2p1. Analytically, you can say. Hence, the decline in ARE is quite smooth actually. So if you see here, you just see here it is proportional to this 2p1. 2p, hence the decline in ARE is quite smooth and is linear in p1. However, in the case of Cauchy, the drop in efficiency is quite drastic for heavy middle portion of the data with MPC larger than 0.5. The ARE for MC tends to 0 as p1 tends to 0 actually. So these are my presentation. I think, the results of table 2 shows that when the underlying distribution is extreme value, there is a gain in efficiency due to MC for a very combination of P1 and P2. With P2 is 0.95, and this was increased as P. The 80% of the data is 0.15 and P2 is 0.16. What we have done is to conclude this. So we have generalized median test, usual median test, or the median test for complete data to the multiple type 2 sensor data. Multiple type 2 sensor data means it is not necessarily sensoring, it is the data for that is some subsets of order statistics are not available. Even they are not available, they are not suitable. So, or they may not contain much information. Therefore, in that case, even this can be recommended because that will improve the efficiency of the test procedure. We obtained LMP rank test for generalized, for multiple type 2 sensor data, and obtained asymptotic distribution and studied the effect of sensoring. Of course, the one result is as long as the median of the data is available, actually there is no loss of information. Therefore, the asymptotic efficiency of the sensor data, generalized median test is almost, same as the efficiency of the usual median test. So therefore, we have studied middle portion of the data, but still for some distributions, you saw that there is a gain in efficiency even when you chop it off more than 50% of the data. So these are my conclusions, and these are my references. These are the references on parametric, inference, parametric estimation mainly. This is our paper appeared in 2010. And this is a standard, well-known book. Everybody knows that this is a normality of simple rank statistics. And this is again actually estimator based on incomplete data. Actually, this is again standard reference for undergraduates by Gibbons and Check. And this is my talk. I hope I have completed within the allotted time. Yes. So thank you, Professor.
Thank you.
Any questions?
Thank you, Professor Biradar. And very nicely presented your talk and very clear. Now the session is open for taking any clarification from Professor. If anybody want to ask any clarification or suggestions, you are welcome now. Go, sir. You have any?
Yes.
Please, sir, Professor, please.
Shall I present? It is over, and now Professor Ghosh is asking some.
No, I'm not asking.
Okay. Then it seems there is no.
There is time, sir. In fact, by the time 4:30, we will.
It is 4:33 now.
Other session will start at the time.
The allotted time is 4:35. So we are 1 minute there. So thank you very much, Professor Biradar, sir, for the nice presentation of your work. And I thank the organizers also.
So, sir, if you need time, you can take 5 or 10 minutes.
No, we are through with this session, and all three have presented, and they have clarified also. If there is any doubts, they can contact them through their email. Okay. Thank you. Thank you all the three. I thank all the three speakers. Professor D.K. Ghosh sir, Professor P.R. Vittu sir, and Professor Biradar sir. Thank you very much for the kind presentation and participating in this webinar. Thank you very much.
Thank you, sir. Thank you once again. Thank you, Professor Satish Kumar, for giving me an opportunity.
Thank you, Professor.
Once again.
Thank you.
Thank you for giving an opportunity again. Once again, I'm happy to participate in your conferences.
Yeah, thank you all. Yeah, I can. Yes. Satish, you can proceed with the next session. Thank you.
Yeah, I think there is one message. I don't know what is this. Thank you all the speakers for adding so value. Okay.
Okay. Right.
Hello, can you hear me?
Okay.
No, sir, it's me.
Yeah, okay. We can hear you. Yeah.
Okay, just a technical network issue.
Yeah. Okay.
In fact, we would like to, on behalf of the Department of Statistics, University of Kerala, we would like to extend our gratitude to you, professors. Professor Vittal talks, very useful talks to our youngsters, and also we wish to extend our gratitude to you, Professor Ismail, for chairing the session and concluding the same in the timely manner. Thank you so much.
Thank you. Yeah, thank you very much.
Thank you, professors. You can. We need your support and blessings in future also for our continuing further events.
Thank you, Professor Biradar, and thank you all. Yeah.
Thank you, Professor Satish Kumar.
Thank you. Thank you, Professor. Thank you, Professor. Yeah. In fact, we have some time here in this platform because in this platform, our next session will start at 5 p.m. So we have the other platform. There is a session is already started. Just 4:30 by 4:30 it started. So I think if you can interact, this time you can utilize for interactions. Or those who are interested in the contributory presentations can join there and return back by 5. It's better to. At 5, the session is Professor Debashis Kundus, okay, which will talk on. And Professor K.S. Rao will chair the session. By the time, I hope you can utilize the time. Professor Ismail and Professor Ghosh is here or left? There is rainy and very heavy rain.
Yes.
Isn't it?
Yes. Yeah. Yes. It is raining from yesterday onwards, but all over India it seems. Yeah, even north also there is rain.
Oh, yeah.
In Mangalore it is a little bit more this time.
Okay.
Yeah, damages are more compared to the earlier years. Otherwise we used to get heavy rains, but this time little more damage.
Okay.
Yeah.
Professor Vitturbabu is here in the group.
I'm here.
Yeah. Hi, Professor.
Hi.
You can also give some inputs to our researchers. If you
Oh, sure.
Professor Ismail, do you wish? Professor Ismail?
Yes.
You can share your experiences, research experiences, etc. by the time.
Yeah. Of course, there are now 2 directions in the research. One will be mainly concentrating on developing the theory and things like that. Other one will be in the say hybrid type of discussion, developing the theories and computing. So computing also has become one of the important component in the research. So we combine the things quite often, and we consider the hybrid type of models. Particularly, I worked on say non-parametric regression and parametric and non-parametric combined semi-parametric models, and even in time series also, financial time series arch models with so you are modeling separately for variance, you are modeling separately for mean. So why don't you have both the effect in the time sequence? It may be there. So what happens in that case? So a lot of theoretical work need to be taken in that direction, but empirically we can show that that gives a better predictor, or with a predictor with more accuracy if you consider a hybrid type of models. So little theoretical work is seen in this direction. When you combine the two things, you are modeling with the mean as well as with the variance, what happens? And empirically, we have seen that it gives a better, more accurate, accuracy will be increased in terms of prediction is considered. So that is the one point. And the second one will be, say there are, when you model it, whether it is regression or time series or whatever kind of modeling you are doing, even in the designs also. So when you have the spatial effects, how you bring in that in the analysis. So for example, if you consider any block design, you have, say RBD, if I take, you have the blocks. And if you look into the plots in the first block and plot in the second block, adjacent plots, so they have some interaction effect. How you incorporate that? So we'll look into some spatial effects and you measure that non-parametrically. This is what you do, add in this regression model. You can see one of my paper in the Indian Journal of Indian Agricultural Statistics. You can see that. So that actually improves the efficiency of the design if you incorporate such additional things. So these are all the innovative things that we have to look into instead of moving with the routine type of analysis. So something innovative we can bring in. What happens if that is a thing? And certain variables you cannot measure. And the thing is how we can include the effect of such things in the model. So you bring in some non-parametric type of function in the semi-parametric model you consider. So in fact, in the non-parametric regression or non-parametric smoothing, so it is a data-driven approach. When we look into data-driven approach, we estimate the function itself by considering a kind of, averaging the responses. So what you call it the kernel smoothing or spline smoothing, or these are the different types of smoothing techniques or averaging techniques used for estimating the response, mean response. And a lot of openings are there in that direction also to work out. Mainly what I suggest is why can't we look into the hybrid type of things? That means combining two or more directions together in modeling the response or mean response. Okay, that's what my suggestion. And if there are some factors which you cannot measure, or there will be some problem in identifying the effect of that, then why don't we bring in some non-parametric function to represent the effect of that? And first you remove the effect of that, and then you write the modeling for the say corrected response, corrected from the effect of non-observed factors. It is not the errors I am talking about, which you cannot measure it. Such factors you can summarize under the non-parametric function. Then you have an estimate for that and you subtract that from the response and you model it in the routine way. That is another type of approach one can use. There are ample of opportunities to think innovatively because the computing facility we can empirically visualize how good it is, our proposed method. So more of practical we need to think now than looking into, of course, theoretical justification is very much important because the mathematical or applied statisticians, whatever we develop, must have the support from statistics. So it should be statistically important. Those properties has to be made, those studies has to be taken. And of course, empirically also one has to verify with the applications. Thank you, Satish.
Thank you, Professor. Thank you so much
yeah.
for your useful comments. Thank you. and it is useful to our young researchers, especially, or those who are working in that area. Anyone can ask, please, students, do you want to ask anything related to these things? Or otherwise, you can ask anything. Don't worry about it.
Yeah. You can see some of these works in my communications and the Journal of Non-Parametric Statistics, where I have done this work. And also, you can see that. Even in the hybrid type of models, you can see in the ISPS journal.
Okay.
Yeah, it's come in that journal. Thank you, Satish. And
thank you, Professor. Thank you so much. Thank you. Thank you, in fact.
Thanks.
Muralidharan sir is in the group, isn't it? Murli sir? Hi, Professor. Hi. Hello, Professor.
Hello?
Hello, Professor.
Yeah, can you hear me?
Yeah, yeah.
Okay, okay, good. Yeah. So can I just share my screen and check?
Yeah, Professor. Can check.
Yeah, just 1 minute. Yeah, let me just. Yeah, let me just share.
Yeah, please, Professor. It is not come.
Yeah, can you see now?
No, not yet. Yeah, now it is coming. It is coming.
No, can you see?
Yeah. Now it is fine. Yeah, I can make it full screen if we. Yeah.
Okay.
Okay, Professor. Okay. Now it is fine. You please check it whether it is moving also, Professor. Please check whether it is moving also. Just if needed.
What are you saying?
Whether you need to check. Yeah, now it's okay. It's okay. Whether to move.
Can you see?
Yeah, Professor. Now it is visible.
Okay. Okay. Thank you.
Sir?
Very good evening, Professor Debashish and Satish
hello,
Kumar.
how are you?
I'm fine, fine. After a long time, I could see you.
Yes. So nice to see you. Okay.
Thank you, thank you.
Yeah. All waiting for you to attend your birthday.
Thank you.
Yes.
Yeah.
So is this on 31st July or 1st of August?
It is 1st of August.
I see. It's the first.
But usually people thought that there will be a superannuation, but our Vice Chancellor told I will be extended another term. Yeah. And our government is also shortly releasing a GO extending 3 more years, 65 years. In fact, now it is 62 years. They are extending it to 65 years shortly.
I see.
Yeah.
I see.
Yeah.
Okay. So he'll be there for another 3 years at least.
Maybe. Most probably.
Okay. Very nice.
Yeah.
How are things going? How are things?
Everything is fine. Everything is going smooth. First of all, congratulations. The SPF journal has got some revenue. It is all because of you.
Oh, no, it is. I think it is the whole team as well as I think Bala is also helping me a lot. Yes. So,
of course, but it's a good amount. We got. Yeah.
Okay. How much you got?
We got ISPS got 1,80,000. I think. Reddy has told it. Yeah, 1,80,000.
Okay. Good.
Yeah, good amount.
Okay.
Yeah. Satish, shall we start? Or still 1 more minute?
Yeah, 1 more minute.
1 more minute, we have to wait. Our speaker is available already. Because somehow my net is not working with my computer. That's why I am joining with my laptop.
Okay.
If it connects, I will go for that.
Let us start, no problem. The students will. Hello.
Yeah. Shall we start? Yeah. Shall we start with?
Yeah. They introduce and then without wasting time, let us.
Yeah. Sure.
Go this slide time. Students, please introduce the player. Yeah. Please, Ardra, you please introduce the player. And then be grateful for the further proceedings of this session. Please.
Okay, sir. So now we have a plenary session titled Bivariate Semi-Parametric Singular Family of Distributions and its Applications. This session will be chaired by K.S. Rao, former President of Indian Society for Probability and Statistics and Regional Coordinator of AP Academy of Sciences, Visakhapatnam Chapter. He pioneered several new concepts such as interdependent communication network models with dynamic bandwidth allocation, generalized Laplace distribution, generalized Gaussian distribution, and their application in image segmentation, face recognition system, and skin color segmentation. He also served as lead consultant for TCS Bangalore. He published 223 research papers in national and international journals of high repute and delivered 53 endowment lectures in conferences and seminars. He published 3 patents in image segmentation and skin color identification. We are truly honored to have you, sir. I warmly welcome you to chair this session.
Welcome, Professor.
Yeah. Good evening, friends. It's a pleasure for me and to chair the session. Particularly, the speaker is a very, very well-known statistician. Every one of you knows Professor Debashish Kundu from IIT Kanpur, and is a legendary figure. At present, if I say on working people, he is almost top of the statisticians of India. In fact, I am very proud to introduce a few words about him. He is got several awards, and he published more than 300 papers in high reputed journals, and He is the chief editor of our journal for ISPS, and not only that, he worked with Professor C.R. Rao. He got doctorate working with Professor C.R. Rao, and he is well versed in several areas, not one or two. Of course, his passion is more on distribution theory and applications, but he has started with signal processing and several of the other areas he has done. And I can say one word, he is a legendary figure in statistics. And thank you, Professor Debashis, for accepting to present your talk in this conference. And without taking much time, now I request Debashis Kundu to give his talk on this single component bivariate distribution. Thank you. Over to Debashis. Yeah.
Professor Kundu.
You're on mute.
Can you hear now?
Yeah, please.
Okay. Yeah. First of all, thank you, Professor Srinivas Rao, for giving such kind words. I don't know whether I really deserve it or not, but he is always very, very generous about that. I know it. And thank you, Professor Satish, also for inviting me for this conference. So anyway, let me start my talk. I'll be talking today about this parametric and the semi-parametric bivariate distribution with singular component. Can you see my slide?
Yeah.
Okay. So this is basically the outline of my talk. I mean, I will give the motivations at the beginning with 3 examples. Okay, that how did it come? Then I'll be talking about one of the fundamental models for this kind of areas, which is known as this Marshall-Olkin bivariate exponential. There are lots of this the parametric one which has been done recently also, and for the last maybe 30-40 years along this line. But I'm not going to talk about those things because I do not have much time on that. But I'll be mainly talking about some of the semi-parametric one which we have recently introduced. Okay, so let's look at the motivation. The first data set, I'm looking at this one, which is the first number. You can see that there are 2 columns. The first column indicate the time in minutes in which the home team scored the first goal. So these are all basically the soccer data, and these data are obtained actually some of the standard websites which are there in the European Soccer League. Okay, and so these are the data which has been collected from there. So the first column which indicates about this the number, the minutes, the time in minutes at which the home team scored the first goal, and the second number indicates the time in minutes at which the opponent scored the first goal. Okay, so this is the first data set. The second data set, which is slightly different but similar, and here it indicates actually the number or the time at which the home team scored the first goal, so which is same as the previous one, but the second column, if you look at it, which is slightly different, and the second column basically indicates the time in minutes at which the first kick goal took place. Now, the kick goal basically means that those goals which has been scored directly, like the free kick or the penalty kick, or sometimes by the corner kick, which goes straight to the goal, those can be called as a kick goal. And the reason actually it has drawn some attention because this kind of goal is kind of quite spectacular, and people are interested about these things. Okay, so you can see that that is the first column which gives the the time in minutes at which the home team scored the first goal, and the second number indicates the time at which the kick goal took place. Now, this kick goal can be scored by any one of the team, either by the home team or by the opponent. Okay. And the third data set, which is a completely different one, and this is one of the famous data set. I just took just few of the observations, and which basically indicate in minutes. This is one of the famous experiment which was done on the patients of the glaucoma patient which has this problem with the eyes. Okay, these are basically all these patients are diabetic and they have glaucoma, and so these are the data. And this experiment is that actually these patients, those who have the glaucoma, so for them there is a laser treatment which has been given. Okay, so now one of the eyes has been chosen at random, and the laser treatment has been given in that eye, and the other eye it has been given the usual treatment. So now the time basically indicates at which time that a particular eye becomes blind. Okay, so basically you can see that the first column which shows the 46.23, which basically means that after that many weeks that particular eye becomes blind, which has been given the laser. Okay, the second one also indicates about the other eye which has not been given the laser treatment, and that is also become blind at the same time. And similarly, the second one and third and fourth one. Okay, so these are the three data sets which are there. So now let's look at what are the similarities and what are the differences. Okay, so now let me go back first one again. So if you look at the first one, so clearly in all the cases, each of the column they are continuous distribution. I mean, that's what we are assuming. They are not discrete. They are all continuous distribution. That's a reasonable assumption. On the other hand, if you look at the first data set, where it indicates the time at which the home team scored the first goal, and the second one indicates the opponent scored the first goal, clearly the 2 time points have to be different. Okay, because the 2 goals cannot be scored at the same time. So clearly the 2 time points have to be different. On the other hand, if you're looking at the second data set, which it says this one that the home team scored the first goal, that is the first column, and the second column indicates that at least the kick goal took place, which is very clear that if the home team, the first goal becomes a kick goal, though that becomes also the same thing. So there is a positive probability that the first the first element becomes equal to the second element. Okay, so for example, the 5.35, the first element, and the second element is also 5.35, which basically means that the home team scored the first goal, and that was a skip goal also. Similarly, if you're looking at the second row, which is 23.65, that means the home team scored the first goal, which is at the time point 23.65, and the second row and the second one is 12.24, which is clearly has to be by the opponent, because it cannot be the first goal which is scored by the home team, because it is smaller than that, and it has to be by the opponent, and that was a kick goal. Similarly, the third one is 18.18, so which basically means that the home team scored the first goal, which is a kick goal. Similarly, the third one, which is 56.87 and 9.56, clearly the home team scored the first goal at the 56.87, whereas the opponent scored the first goal, which is a first kick goal, at the point 9.56. Okay, so this is the interpretations you can give. Same thing in the third data set also, that you can see this one that there is a positive probability that the first element becomes equal to the second element. Okay, so what we can see that is precisely what I'm trying to put it here, that there is a positive probability that your x can be equal to y. Okay, which is quite unusual than the usual bivariate distributions what we know about. Okay, so for example, if you're looking at the standard absolutely continuous bivariate distribution, where your x equal to y, probability x is equal to y is 0. One of the standard one is bivariate normal distributions, bivariate normal distributions, bivariate inverse Gaussian distributions, or the bivariate Barnum-Saunders distribution. These are all bivariate distribution with singular, with absolutely continuous distribution. So in that all these cases, your probability x is equal to y equal to 0. Okay, fine. So now let's look at how do we introduce this probability x is equal to y greater than 0, and it has been done in a very, very clever way. The first time it was by Marshall and Wilkin in 1967. That was a famous paper where they introduced this kind of a bivariate distribution with a singular component. And see, one thing I would like to mention that we'll see that, I mean, when we find out the joint density function, that there is a singularity on the line x is equal to x1 is equal to on the line x is equal to y. So the singular distribution comes out quite naturally in the bivariate or the multivariate case. So let's look at that. Okay. So suppose there are three independent random variables x1, x2, x3 with parameters lambda 1, lambda 2, lambda 3. And these are the probability density function, or the probability or the cumulative distribution function of the exponential distribution with parameter lambda, which means that it has the mean or 1 by lambda. So now we are defining it that x is equal to the minimum of x1 and x3, and y is equal to the minimum of x2 and x3. So that's the way this Marshall-Wilkin bivariate exponential distribution has been defined, that x and y. So now we can see that although x1, x2, x3, they are independent, but x and y, they are clearly dependent because of the presence of this x3. Okay, so they are dependent on the variable. But it has a very, very interesting physical interpretation also. Okay, and it is known as a shock model, and it comes from the what is called as a Poisson process. I mean, many of you know what is a Poisson process. Let me just briefly mention a collection of not necessarily a sequence of random variables. Okay, the reason actually I'm trying to emphasize that, because whenever we are talking about a sequence, that means I'm talking about a countable number of random variables. But whenever I'm talking about a collection, it is not necessarily has to be a countable number. It can be uncountable, and that is precisely if you're looking at this NT. Okay, NT where t greater than or equal to 0. So it's an uncountable collection of random variables, and it is called a stochastic process. A collection of random variables is called a stochastic process, and a stochastic process NT is called a counting process if it represents the total number of events till the time point. Okay, so that's a way a counting process, which is a special kind of a stochastic process, we have been defined. Now, a counting process, you can see that means NT can be only discrete values. Okay, NT can take 0, 1, 2, because that is a number of events. So clearly, NT can take the discrete values. Okay, so a counting process NT satisfies these following properties. Clearly, because it's a discrete value, it can be non-negative. So NT has to be greater than or equal to 0. It is integer valued. And since it is the number of events till the time point t, so clearly it is a non-decreasing function. So your ns has to be less than or equal to nt. And if we are looking at two different time points, s and t, so nt minus ns denotes the number of events that occurred between s and t. Now, a Poisson process is simply nothing but a counting process where your n0 is equal to 0. That's a very, very simple basic assumption that means when you're starting the process, there is no event has taken place at that point. The process has independent increment, which basically means that if you're looking at the two distinct intervals, the number of events in the two distinct intervals are independently distributed, and your number of events between s and t plus s, which is nothing but a Poisson random variable with parameter lambda t. Okay, it has to be. There is a mistake. There is Poisson lambda. Okay, so this is a Poisson process. Now, the interpretation what we have about this Marshall-Wilkin bivariate exponential distribution is that suppose a system has two components and there are three shocks which can affect the system. Okay, the shocks comes and it comes according to the Poisson process, and that is precisely what I had mentioned. Okay, and the first shocks affects the component 1, the second shocks affects the component 2, and the third shocks affects both the component. And a component fails as soon as it receives a shock. Okay, so you can see that. So that means the first component can fail due to the first shock or due to the third shock. Similarly, the second component can fail due to the second shock or due to the third shock. Okay, so now if I denote this x1, x2, x3, the time at which the first shock, second shock, and the third shocks arrive. Okay, if we denote that, then of course I know this one, that the lifetime of the first component, which is nothing but the minimum of x1 and x3, and similarly the lifetime of the second component, which is the minimum of x2 and x3. So that is the interpretation what we had about this Marshall-Olkin bivariate exponential distribution, which has a nice connection with the Poisson process. Okay, because the shocks arrive according to the independent Poisson process, it affects the component and it makes it fail, and that's the way the lifetime of those components, that is. Okay, some of the basic observations, that your x1 which simply follows exponential with lambda 1 plus lambda 3, because that is the minimum of x1 and x3, so it is very simple, exponential lambda 1 plus lambda 3. Similarly, your y, which is exponential also, which is lambda 2 plus lambda 3, that is there, and the minimum of xy, which is exponential with lambda 1 plus lambda 2 plus lambda 3. And that is becoming quite useful, particularly when you try to test the hypothesis and things like that, or the goodness of fit. These results becomes quite useful. But what is more important is that let's look at what is the probability that x is equal to y. If you're looking at the probability x is equal to y, how it can happen? Well, x is equal to y can happen if x3 is less than both x1 and x2. And that is precisely what we are trying to compute. What is the probability that x3 is less than x1 and x3 is less than x2? And that simply turns out to be lambda 3 divided by lambda 1 plus lambda 2 plus lambda 3. So now we can see that if my lambdas are positive, and which has to be, because that is an exponential distribution what we are talking about, since if the lambdas are positive, so probability x is equal to y is a positive quantity. Okay, so you can see that unlike the usual bivariate normal distribution, bivariate log-normal distribution, bivariate Bernoulli-Saunders distribution, this particular one, that probability x is equal to y is positive. Okay, so now let's look at what is the survival function, joint survival function, as well as the joint probability density function. Okay, and here we'll see there are slight differences what we have observed in case of the usual absolute continuous distribution function. Okay. I'll just pause it here. I hope everybody can hear me, isn't it?
We are able to hear you.
Okay. Okay, that's fine. Okay, so now let's look at the joint survival function s of xy, which is simply nothing but probability x greater than x and y greater than y. And by simple calculations, it can be seen that it has two components. One component is y greater than x, another component is y less than or equal to x. Okay, and which turns out to be in this form. And of course, I have a nice relation between the joint survival function and the joint distribution function, so which can be put it in that form. Okay. So now let's recall. Let's think about that. What do you mean by an absolute continuous cumulative distribution function or an absolute continuous survival function? We know that a distribution function is called an absolute continuous distribution function, or the associated survival function is called the absolute continuous survival function if there exists a function f of uv, which is supposed to be the density function, such that I should be able to obtain the joint distribution function f of xy, simply nothing but the area below the curve up to the point xy. Okay, and similarly, the joint survival function at the point xy is simply nothing but the area below the curve beyond the point xy. Okay, so that is precisely that is the definition. And of course, we know that if a distribution function is absolutely continuous and associated survival function is absolutely continuous, and because that's an if and only if, then I can easily recover the joint density function, and that is simply nothing but the double derivative. Okay, so now let's try to recover the same way in case of this Marshall-Ricklin bivariate exponential distribution. So what I do, I just do the double derivative of the survival function, okay, with respect to x and y, and because the survival function has two components, for x less than y and for x greater than y, and I'll be getting exactly the similar form in this particular case. Actually, in this particular case, your f is nothing but the exponential with parameter lambda 1 plus lambda 3, the density function. So that's all right. Okay. So now let's see whether this particular density function, whether this one is a proper density function or not, which basically means that if I integrate it out over the entire range 0 to infinity, I should get 1. So let's try to do this integration, this f of xy dx dy over the entire range minus infinity to infinity minus infinity to infinity. What I'm getting it by simple integration, it is lambda 1 plus lambda 2 divided by lambda 1 plus lambda 2 plus lambda 3, which is clearly less than 1. So therefore, it is clear that this f of xy is not a proper density function, which basically means that your capital F of xy or the Sxy, this is not an absolutely continuous distribution function or not absolutely continuous survival function. Okay, so this is very, not a very the standard one what we usually observe. Okay, so now let's try to see what is happening. Okay, so let's look at what is the probability x greater than or equal to 0 and y greater than or equal to 0. So I can decompose at probability x less than y plus probability x greater than y plus actually probability x equal to y. So that is the whole difference between the three, and we have already seen the probability x is equal to y is lambda 3 divided by lambda 1 plus lambda 2 plus lambda 3. So you can see that because of these things, I am not getting, if I add the first two as the proper density function. So now let's try to recover how do you get this joint density function. So I'm trying to look at probability x greater than or equal to a and y greater than or equal to a. Again, it can be written by the three components, and I have these decompositions that one is the range at x is less than y, but they are greater than a. X is greater than y greater than a plus probability x is equal to y is equal to a, and these are simply by these simple integrations, and therefore probability x is equal to y greater than a, which can be obtained simply by this difference from there. Okay, so therefore by simple thing we obtain that probability x greater than or equal to a and y greater than or equal to a, which has this form from the joint survival function. You can get it, and the second two components, second and the third component also we can get it by simple integrations. Okay, and therefore what you observe that the probability x is equal to y greater than a, which can be obtained in this integral form, and that actually gives us a very interesting way to write down that the joint survival function. You can see that I write down in this integral form. Okay, so this is precisely, you can see that I have the first component, which is that area below the curve beyond the point xy, plus there is an area below a particular function on the line x is equal to y. That is precisely what is happening, and that is the reason that I have the joint probability density function, which is in this particular form, that I have three components. One is the component where my 0 is less than y less than x. Another is the component 0 is less than x less than y. That means that if I look at the line x is equal to y, the one is the upper part, one is the lower part, and another is the line x is equal to y, which is the third one, f0x. And that is what we call as a singular component, and which is that is different than all the things whatever we have seen before. Okay, and so this is basically the form. You can see that for x less than y, for x greater than y, and for x equal to y, which is simply the exponential form. Okay, so this is the graph of the absolute continuous part of the bivariate Marshall-Olkin bivariate exponential distribution. That's what it is. Now, if you're looking at the joint, the survival function, okay, the joint survival function, we know this from the basic theorem of the probability that any distribution function or any survival function, it can be decomposed as the absolute continuous part and the singular part, okay, and that is precisely what we have done it here, what we have seen it here, that well, the joint survival function has a decomposition with the p times the singular component and 1 minus p times the absolute continuous component, okay, and the singular component comes on the line x is equal to y, and the absolute continuous part comes on the area x less than y and x greater than y, okay, and therefore the singular component has this particular form, which is nothing but e to the power negative lambda 1 plus lambda 2 plus lambda 3, the maximum of xy, and therefore the absolute continuous part I can obtain by differencing, by making the difference. I can easily obtain the absolute continuous part. Okay, so that's what we have. I mean, that's what we have, and also my probability density function along the same line, it can be decomposed into two components. Okay, one is the absolute continuous part, and another the singular. Okay, so that's the way I have the nice decompositions about the probability density function also. Okay. There are certain interesting thing that if you are trying to look at how much is the maximum correlation or the minimum correlation I can get, what we can see that if you're looking at the probability x is equal to y, which is lambda 3 divided by lambda 1 plus lambda 2 plus lambda 3, and that goes to 0 as lambda 3 goes to 0. And from the previous equation, that s of xy, which is converging to e to the power negative lambda 1x minus lambda 2y as lambda 3 goes to 0, which basically means that as my lambda 3 goes to 0, your x and y becomes independent. Okay, so as my they're becoming independent, and on the other hand, if your lambda 3 goes to infinity, okay, so probability x is equal to y, which is lambda 3 divided by lambda 1 plus lambda 2 plus lambda 3, which goes to 1. That means all the mass are become concentrated on the line x is equal to y. So there is no mass left on the rest of the area where x is less than y or x is greater than y. So all the mass become concentrated on the line x is equal to y, and then of course in that case the correlation becomes 1. So you can see that once it becomes independent, when my lambda 3 goes to 0, then x and y becomes independent, so the correlation becomes 0. And on the other case, as my lambda 3 goes to infinity, because lambda 3 can vary between 0 to infinity, as lambda 3 becomes infinity, it goes to 1. Okay, so the correlation varies between 0 to 1 in this particular case. Let me introduce another interesting concept, what is known as the copula, and this is becoming a very, very useful concept nowadays because of its wide scale applicability. And the copula basically tells me that, well, it's a bivariate distribution function which is defined on 0, 1 cross 0, 1. Okay, that's called the copula function or the copula distribution function. And what is the unique property about the for any distribution function is that for any bivariate or the multivariate distribution has an unique copula, and this is the representation, or that is the relation between a joint distribution function and a copula, that the joint distribution function of x and y, which can be represented as a copula function at the point fx and fx at x and fy at y. What is fx at x? That is the distribution function of x, and fy at y, which is simply nothing but the distribution function of y. Okay, so that is the copula function. Okay, and that is the relation the inverse way. That means that if I have the copula function, I can obtain my copula function from the distribution. But now, why it is so important? It is becoming so important because it helps me in many ways actually. And I'll just come to that. But before that, let me just give the two examples. I mean, you can simply looking at CUV, where the U times V. which is called the uniform copula, and the second one is CUV is UV divided by 1 minus theta times 1 minus U 1 minus V, where theta is between 0 and 1. So actually both of them are distribution functions on 0, 1 cross 0, 1, and those are some of the standard example of the copula. And this is what is known as a survival copula, which is exactly the same thing, just like the distribution functions. We can talk about the survival function also, that the survival function can be represented what you know as survival copula. The form is exactly the same, and we have a nice relation between the survival copula and the original copula. Okay, so that is the relation what we have. And these are the main reasons the copula becoming very, very popular, because we can generate infinitely many distribution functions from a given copula, provided we just put the different marginal distributions. Okay, so but just by putting different marginal distributions, I can obtain a copula. I can obtain a bivariate distribution, and that's the reason that the copula becomes very, very important nowadays. Another thing is that many properties remain invariant of the distribution function. Okay, so it basically depends on the copula. So that means, as we can see from the definition of the copula, that this copula definition basically that means that for a given copula, I can have many bivariate distributions. Okay, so but all of them has certain common characteristics because the copula is same. That's what I said, that the many properties remain invariant, and that is becoming important because I do not need to develop the properties of the different distribution function, bivariate distribution functions, provided I can find out the properties of the particular copula. Okay, so many properties remains invariant. Okay, that is an important thing. And another important one, which actually I think the main reason about the introduction of the copula is that estimation becomes easier. What does it mean? It basically means that, well, if we have this copula, we can have a two-stage estimators. One-step estimator is that first I can estimate the parameters of the marginals, which are much easier, and then based on the marginal estimator, I can estimate the copula parameters also. So that's the way I can reduce the multidimensional optimization problem. So these are the reasons that it becomes extremely popular. Okay, interesting part is that the Marshall-Olkin bivariate exponential distribution. If I look at the survival function, so this the copula turns out to be what I have put it here, the C of UV, which is this quantity. Okay, and if I just replace this alpha as this and beta as this, then the copula becomes this quantity. Okay? And as a special case, when alpha is equal to beta, okay, that means when lambda 1 is equal to lambda 2, then the copula becomes a simple copula. And this is known as the Marshall-Olkin copula, and that becomes that I can use these things for generate several bivariate distributions with singular components. Okay. Now let's talk about what I had mentioned about the semi-parametric bivariate distribution. I go in a little bit general framework. So instead of looking at a specific distribution, then let's look at any general survival function, which is of the form of S of x theta, which is S naught x to the power theta. And this is basically known as a proportional hazard class. Okay, so I'll denote this one as the proportional hazard class as S naught and theta. As you can see, I can do exactly the same thing what I have done before. I take three independent proportional hazard class with parameter theta 1, theta 2, theta 3 with the base distribution S naught as the same, and I define x1 is equal to the minimum of E1 and E3 and x2 is equal to the minimum of E2 and E3. Okay? If I do this one, I can actually do exactly the same thing, whatever I have done it before. I can develop the whole process about the bivariate distributions. I can develop the properties, all these things I can develop. But what is important here, that I have not taken any specific form of S naught. Okay? I am keeping my S naught to be in an arbitrary manner. For any S naught, I can develop the many properties. Okay, so now this Marshall-Olkin bivariate exponential distribution is an exponential. What we have suggested now, we are taking a much more general one. What we have taken a class of distribution whose hazard function, baseline hazard function, has a piecewise constant. Okay, so that makes it a very, very flexible bivariate distribution, and I am calling this one as a semi-parametric because I do not use any parametric form of the baseline one. I am keeping it as an arbitrary manner in that respect. I am keeping it as a piecewise constant hazard function. One natural question comes that, well, why do you need to even assume that? Why not trying to have this the baseline hazard, baseline distribution, F naught or S naught, as a completely non-parametric? Unfortunately, if I keep it completely non-parametric, then the parameters lambda 1, lambda 2, lambda 3, or theta 1, theta 2, theta 3, they are not identifiable. Okay, so that is the whole problem about this one. So that's the reason that I put this minimum restriction where I have this the baseline hazard function has a piecewise constant. Interestingly, well, these are some of the pictures. If you're looking at the absolute continuous PDF with a certain form of this baseline hazard, it can take different shapes. Okay, so that is the nice part. And of course, one thing is clear that if I take this baseline hazard as a constant throughout, then it becomes a Marshall-Olkin bivariate exponential. So it's a more generalized version of the Marshall-Olkin exponential. Interesting part is that it has the same copula as the Marshall-Olkin bivariate exponential distribution. Therefore, many properties what we know about the Marshall-Olkin bivariate exponential, which can be extended even for this model also. Okay. Now let's look at some of the things what we have developed. We have developed the EM algorithm to estimate the unknown parameters and to construct the confidence intervals naturally, because that is unless you develop an efficient estimation procedure, it cannot be used further. Okay, so that has been done. It has been also used to analyze competing risk data. Okay, so this dependent competing risk, which is also a very, very I would say recent topic. People are trying to do this dependent competing risk. So this particular model, which can be used to analyze to dependent competing risk. Okay. Of course, we have not developed any Bayesian inference, so that will be an interesting work to work with. So those, if you have somebody is interested, can work into this one. That will be interesting to look at it. Not only that, the bivariate semi-parametric proportional reverse hazard model also can be developed along the same line. I mean, many things which I should be able to borrow it, whatever we have done, even for this bivariate semi-parametric proportional reverse hazard model. Okay, I think with this, my time is also up, and I close my session. Thank you very much for your patience. Okay, all right. So any questions or comments, I really appreciate it. Okay.
Thank you, Debashish Kundu, for your nice lecture. And any clarifications quickly from the participants, or any part of the other thing, one or two? Yeah, it's a very nice bivariate distribution, particularly Markov-Olcott, and bivariate exponential is usually used in reliability studies and other things. Now, this is a wonderful distribution. In fact, I can see from your lecture that it has a lot of applications. And the bivariate, not only in reliability, I can connect them even with respect to the signal processing also, which is your favorite area, in fact.
Yes.
Yeah, a lot of applications are there, this has, and it's very interesting, in fact. And also you have taken the coupler distribution. That is a very interesting part, and which is very useful even estimation theory also for the many of the distributions, and it makes it easy. And a very nice lecture, and thank you very much for your nice lecture. Anything, Dilip? Anybody else who wants to say?
Yeah, I have a question. So, clarification, not question. Now, may I know how this copula is useful in estimation?
Copula is useful. Let me just explain briefly. See, it is like this. See, this, for example, suppose let's look at a trivariate distributions. Okay, so which might be having say maybe 8 parameters, where each of the marginals has maybe say 2 parameters each, and the copula also has 2 parameters. Okay, so now if you want to estimate all of them, suppose you try to estimate the maximum likelihood estimator, so it's a 8-dimensional optimization problem. Okay, so that is, I think, one of the very, very difficult things to do, because doesn't really matter what kind of software you use, you have to be always careful whether you are actually getting the maximum or not, whether you are getting stuck with the local optimum and things like that. On the other hand, suppose we go to the copula one, so what we can do, you can first estimate the marginals. Okay, so that's the reason that the fx, fy, and say maybe fz, you can estimate the 3 marginals and the associated parameters there. So each one of them has only 2 parameters. So estimating 2 parameters is much easier compared to estimation of the 8 parameters. So now you estimate the 2 parameters, which you got already 6 parameters, and then you put those values in those copula functions, and then you estimate the copula parameters. That's the way it has been done. It's 2 stages. You lose some efficiency. Those theoretical properties can be done, but still you have the same kind of mode of convergence, in the sense the same rate of convergence like the maximum likelihood estimators. Okay, so that's the way it has been done in 2 stages. First, you estimate the marginals, and then you put it in the copula, and then try to estimate the copula parameters. Okay, that's the way it has been done.
Yeah, can you tell me the reference? Using the copula.
You just There are a lot actually. Actually, we have also done. You just send me an email. I'll just reply back to you. I just send you the complete.
Fine. Sure, definitely. Thank you.
All right.
Sure. Thank you, sir.
Sure.
Hello, sir. Hello, sir. I want to know that there are many copulas are there. So, is there any technique that modified to choose copula? Which copula will
No, I did not choose the copula here, because I see, because the Marshall-Wilkin copula, you got it from this inverse function, no? That the copula has the if you have the distribution function, you have a unique copula. So because the Marshall-Wilkin bivariate exponential has already been developed. Okay, so that particular bivariate distribution has that particular copula. Okay, so in this particular case, we got the copula because and since it is unique, that has to be the copula here. But what you said, that's a slightly different one. I mean, what you said, this one, that suppose you pick up a copula, okay, and then you can, of course, you can have these different bivariate distributions, but you have to be careful to generate any bivariate singular distribution, but not too many copulas which can generate a singular distributions, bivariate singular distributions. Are you clear? Is it clear? I mean, so there are not too many copulas which can have this singular component. That is very, very restricted. Okay? So, well, I mean, you can choose one of those copulas which has a, I mean, that's the only thing I can say. Does it answer your question?
Yes, I think I understand, sir.
Okay.
Thank you, sir.
Yeah. If no more questions, then let us all thank Professor Debashish Kundu for his very, very nice lecture. And
thank you.
Thank you. Yeah. Now over to the organizers. The session is over. Yeah. Thank you.
Really wonderful, Professor. Really.
Thank you, Satish. Yeah. Thank you for inviting me. Yeah.
Thank you so much, Professor, for your deliberation. Your talk.
Devashish, hi.
Yeah.
Hello.
Hi. And thank you, Professor Srinivas Rao, for chairing this session and supporting our activities. Thank you. Thank you.
Yeah. Thank you. Yeah. I am off. Yeah.
Now let us move to the next session. We are in the right time. 1 minute over. Professor Muralidharan is here in the group, and Professor D.K. Ghosh is to chair this session. Sedulakshmi, please introduce the chair and do the needful for further discussions.
Yes, sir. Greetings to all. On to the next session, which is a special invited session in honor of Professor Krishna Pillai. We have Dr. D.K. Ghosh as the session chair. Dr. D.K. Ghosh was professor and head of Department of Statistics, Saurashtra University, Rajkot. Presently, he is UGC BSL Faculty Fellow after his retirement. He has over 44 years of academic and administrative experience and has published over 150 publications in national and international journals. He has published over 3 books. He is also Fellow of Royal Statistical Society, Fellow of Gujarat Science Academy, also holds editorial board membership in over 10 journals including International Journal Agricultural and Statistical Sciences, Indian Journal of Statistics and Applications, and many more to continue. He is also a life member of Indian Society of Agricultural Statistics, Indian Society of Probability and Statistics, Indian Society of Medical Statistics, etc. I take this opportunity to welcome Dr. D.K. Ghosh to chair this session. Sir, please.
Thank you very much, Professor Satish. Now, I think we are already late by 2 minutes. So, without losing our time, I request Professor Muralidharan to deliver a talk. And his talk is a revisit to consistent asymptotic estimators. So, with this, I request Professor Muralidharan, please start.
Thank you very much, Professor Ghosh. Nice to see you on board.
Thank you.
Nice to see others also. Thank you, Professor Devashish Kundu as well. See you. Okay, let me share my presentation. Is it okay? Can you see that?
Yeah. You can see. But not slide. It is not slide. It is just.
Yeah, now it is in slide show mode. Is it okay? Is it okay now, sir?
It's fine, Professor. It's fine.
Okay.
Okay. Yes. Thanks once again to Professor Satish Kumar. I met him online 2 days ago. Nice to see you again. So I'm going to talk on a revisit to consistent asymptotic normal estimators. And this is in honor of Professor R. Krishna Pillai. Satish, I am not very well, versed with the person Krishna Pillai. If you can give a 1 or 2 line insight to who is the Professor Krishna Pillai, then I was expecting a kind of introduction about him.
Yeah, Professor Krishna Pillai is our former professor and head, and he was instrumental in initiating the Department of Statistics in the University of Botswana under the direction of the United Nations, the assignment of United Nations. And he is a very nice, he was a nice personality. I have little, only 2-3 times I visited him. And he's no more. And Professor Krishna was a very good teacher, in fact.
Okay, that's very nice. Yes. So I'm really happy to give this talk in honor of Professor R. Krishna Pillai.
Also a good researcher, yeah.
Okay, thank you. Now, I dedicate this presentation to my beloved sir, Professor B.K. Kale of Department of Statistics, who is no more. He passed away on March 13th of this year, just 3 months ago, almost. Okay, so, and that's the reason why I have taken a topic called consistent asymptotic normal estimation. This is one of his favorite topics. Whenever we meet each other in Pune, most of the time he talks about estimations, and that too about consistent asymptotic normal, that being very close to his heart. We had a lot of association, almost 10-15 years, I think. Almost 10 years we have been interacting physically. Many often I went to Pune University for doing some research with him.
After that, I remember we had a lot of communications online, on email and all the, I mean, even phone also. And for last few years, there was no communication as he was not mobile. He was a kind of, a bedridden kind of situation he had. And this year, this year, on March 13th, he passed away. So I dedicate this presentation to him. Okay, so I'm sure that you might have seen this book jointly written with Professor Kale, Parametric Inference and Introduction, published nationally by Narosa Publishers. And here is the international version of the same book, Parametric Inference, published by Alpha Science. This is a sister concern of Oxford Publishers. So you can have any one of these, contents are same. So there's a beautiful chapter on consistency, chapter number 5, and chapter number 6 is on consistent asymptotic normal estimators. So I'm trying to I'm just trying to recall the concept first, and then I will get into the estimation into a family where I'm working on. We are generally, of late we started working on, that is in-lab models. Now, I don't want to discuss what is discussed in the textbook. A lot of examples, lot of theories, lot of insights, lot of interesting facts are given in the book regarding consistent asymptotic normal. So I will not repeat those things. I will take up a model which we are working even now also. And, that is what is called inlier prone models. That's our contribution as such. We only coined the term inlayers in the statistical literature. And so I will see how estimation procedures can be developed for and those kind of models. The reason why I wanted to discuss estimation, estimation, consistent asymptotic normal estimators for that particular model is because that's altogether a different model. We have a degeneracy at some point, and then there is a continuous portion of the remaining data set, etc., etc. The usual, discussed distributions like normal distribution or any other distribution you talk about, one parameter, two parameter, etc., etc. You can always construct consistent estimators and all any other classical estimators, which again I'm not going to talk about. Now, the reason again, other reason is that we can suggest estimation, consistent asymptotic normal estimation for parametric functions of the involved in the model. Generally, we can go for classical estimators for parameters, single parameter itself. Now here, there's a difficulty in this particular model that we cannot unbiasedly estimate the parameters in single form. So that's the difficulty. That's the reason why I'm considering the distribution, the inlier prone distributions here. So this is a definition of consistency, which I am sure most of you are familiar with. I do not want to discuss too much on this thing, etc. Okay, so consistency as such, it is a large sample property of estimators. Okay, so you can construct consistent estimators, I think, without any difficulty in all this, the regularly seen distributions. And here is the definition of consistent asymptotic normal estimators. And see that, make sure that you have an estimator, consistent estimator exists for theta. And you wanted to construct a consistent asymptotic normal estimators for a parametric function, say for example, psi theta here. So that is possible through invariance property as well. So, a lot of properties we study, we talk about estimators. Now, consistency also satisfies the invariance property. If t is consistent for theta, then psi of t is consistent for psi of theta, like that. So that property is also going to be a part of this can estimator, can definition. So look at, you have a parametric function, say psi theta, and psi t is going to be can for psi theta if psi t is asymptotically normal with parameters psi theta, and the variance part is very, very important. You can see that consistent estimator, you have the variance sigma square t indexed by t and parameter indexed by theta divided by an square. So if you write this in the same form, you can see that. So I'm just I'm showing the consistent asymptotic normal estimator form here. So you can see that a constant an square. That an square, we call it as block factor, or it's as good as a normalizing constant or something like that. An usually seems to be, root n times. you see in the normal case, root n times x bar minus mu follows n0 sigma square by n, something like that. So that constant, that normalizing constant, you may call it as, but in most of the time it may not be a normalizing constant. That I will discuss where that cannot be called it as normalizing constant. Why it is called blow up factor is also evident from some of the discussion which is going to come. Just wait. Okay, so this is as good as, and the condition for whereby you can construct consistent estimator or can estimator in short is that the psi function, the parameter function, has to be differentiable and should be continuous. That is the only condition which is not very hard, very strict, but it is possible. Most of the time we talk about the parametric functions, and parameters range is most of the time it is in 0 onwards in the real line. So differentiable function going to be is something which is assured and continuous and non-vanishing. That's another small condition, very important. Even if it is vanishing, you can still construct can estimators. Okay, that discussion will also come. So there you may use some asymptotic chi-square distribution instead of chi-square in normal distribution. So I request all the young researchers to see the book. Okay, please go through the chapter number 6 at least for can estimators and see how best you can suggest estimators, and without any, too much of technical hurdles or, computational procedures. It's very easy to construct. Okay, so let me get to the model first. Let me introduce the model, inlier prone models. So look at the model. This is what we are going to discuss. So far, we have not discussed any, earlier we have not discussed any can estimators for this kind of models. Okay, UMV estimation is done, base estimation is done, and all parametric based estimations, everything is suggested. Okay, we want that people use can estimators also as a part of their estimation, because most of the time people talk up to linear estimators, percentile estimators, and many other best linear estimators, etc., etc. I think this is, high time that it should be, people should use can estimators as well. Okay, so look at the density. This is the form. Now, if d equal to 0 in this case, the model becomes an instantaneous failure model, and d greater than 0 and is very small, the model becomes an early failure model. Both these situations are very common in clinical trials, reliability studies, survival studies, time series studies, etc., etc. Many examples you can contemplate where observations 0 also comes, and observations close to 0 also will be a part of the other observations. So they are in fact inconsistent observation. Now, please look at that. This model is not like a usual truncated kind of model or a generalized Poisson or generalized versions of, many generalized versions are there available in literature. Please note here the fx theta is a continuous density, not a discrete density. So that is how this differs from all other, truncated kind of distributions. Okay, so here you have a discrete portion as well as a continuous portions. And that's why the inference is going to be difficult. Otherwise, if it is both continuous or both discrete, then there is no problem. We have mixture models available, inferences, all kinds of inferences can be suggested. So here it's not possible at all. Another importance of this model is that theta is not possible to estimate unbiasedly. So you will have to go with either UMV estimation, even parameter functions are possible. You can use a Cramer-Rao lower bound, then many theorems like Lehman-Sheffi theorems, etc., to construct variance part estimates and variance estimations, etc. That is possible. So examples, if you look at a lot of examples coming in survival studies and reliability studies. Most of the time, survival studies and reliability studies talk about lifetimes of electronic components, lifetimes of systems, etc., etc. So many often systems fails instantaneously with 0 life. Many often it remains for a few hours of time. That means you will have early failures. Once it starts its full life, they will have a lot of, positive lifetime. So it's a combination of zeros, observations close to zeros, and positive observations, etc. This is what exactly happening in survival studies. Even you have meteorological studies. If you look at rainfall, for example, for a particular season, for example. There are a lot of, if suppose the season starts from June to September, for example, these 3-4 months, you can see a lot of days goes dry. When you say dry means no rainfall. There are going to be days with less amount of rain, a small amount of rain. You can say early failure. You can just make a parallel to that. If you want to model those kind of situations, it is very easy with this kind of model, in prone models. Surgical studies. A person recovers after surgery. What time? How fast? If the person recovers very fast, then you can have a very small, that zero is important in this case. In all these examples, what I mentioned, zero is very important in some cases. Some cases, zero will not have any meaning. Look at some of the examples which discuss. Financial studies, for example. Look at the audit reports. Zeros. If you look at a number of pages, if you are inspecting, a lot of pages will have many number of errors. Some pages will have few errors. Some pages will not have any errors at all. So in that case, pages do not have errors is good. So zero observation is good in this sense, in some cases. So that is how the model comes in, the inlet prone models. So D is also important, D equal to 0 is also important. Okay, so let us now take up the simple model where D is 0 is considered. That is x equal to 0, you have a proportion 1 minus p, and x greater than 0, you have a continuous distribution, p by theta e power minus exponential distribution. And therefore, this model is called exponential instantaneous failure model. All these kind of models we have started long back, about 10-15 years ago. I actually wanted to bring the CAN concept in this one, consistent asymptotic normal estimation concept here. Because theta estimation unbiasedly is not possible. That's the most important part of this particular model. So you can write down, if you have any observations, you can write down the likelihood in the form, where with ix, you define it as an indicator function. If x equal to 0, ix becomes 1, otherwise 0. So you can estimate also x equal to 0, you can just count number of zeros in that proportion. So if p is that probability of x greater than 0, we call it as the positive observation and denote ix is equal to n minus r. Where r is number of positive observations, the joint density can be easily written in this form. And if that is the case, all these results are obvious. The proofs and everything is given in various papers, so in our own papers, so I'm not discussing that. Joint density is actually a two-parameter exponential family because we have p also, theta also. Please note that D, we have taken the simple model with D equal to 0. If D is positive, definitely there will be more number of parameters. D can also be a random variable also, D can be a fixed constant also. Okay, so there, if it is a random variable, definitely there are going to be, the complexity will definitely come again. Now, summation ixi and summation 1 minus ixi of xi are jointly sufficient for p theta. It's also very easy to show. And maximum likelihood estimates are given as r by n for p cap and 1 by r summation xi or positive observation for theta. And they are jointly asymptotically normal with diagonal elements that variance p into 1 minus p by n, that variance of p cap, theta square by np as variance of theta. You can see the theta square by np, p is also coming up there. P and theta are orthogonal because off diagonal elements are 0 here. And true reliability can also be estimated. That also involves p and theta, both the parameters. And distributional properties, if you talk about this density is very important. Conditionally, given R, if you know the number of positive observations in the model, given R, then that Z is going to be gamma distribution. Okay, so that result is also obvious. So let us see UMV estimation and CAN estimation. So we have the density function, the likelihood we have taken, and we have rearranged that likelihood in a form which suits to the two-parameter family. And you can see all those indexing parameters and the corresponding functions in terms of x's. So they are all jointly sufficient. And also we have shown that it is complete, summation ixi and 1 minus ixi into x. If you consider summation ixi or summation 1 minus ixi, that's also going to be complete. So, okay, so we have taken up a lot of results from here and there. In this case, if you denote summation 1 minus ixi and xi as number of positive observations as z, then in simple sense, you can write down the joint likelihood in this form. NCR 1 minus p raised to n minus r, p by theta raised to r, e power minus z by theta. And n minus r and z are jointly sufficient for p theta. And yes, z given r is gamma. Okay, now comes to the point UMV estimation. The usual sense we generate, develop the UMV estimation that expect a value of some function, parametric function. The statistics is going to be the parametric function. Okay, so phi p theta. So it's not singly estimated. It's p theta. It can be anything. It involves p. It can be p square. It can be linear, non-linear, or any kind of things. So it's actually the first part, that is alpha 0, that is coming to the 0 component and plus the remaining positive component. So you have, if this is equal to pi p theta, you can develop So we have tried a lot of parameter functions to see how it estimates. So here is the result. So the UMV estimate of 1 minus p raised to m is given as n minus m CR divided by NCR, R is equal to 0 to 1 to m and 0 otherwise. And for m equal to 1, you get simple estimate of 1 minus p. So instead of, so p cap is not possible again. P cap can be estimated through maximum likelihood, no issue. Okay, so 1 minus p is estimated, not p. So 1 minus p estimate is given as n minus r by n for the other conditions like r greater than 0, z greater than 0. And the can estimator correspond to the same parametric function. 1 minus p raised to m is given with as 1 minus r by m and n whole power m as the estimate, and the asymptotic variance is given as np times 1 minus p raised to 2m minus 1. And this can be estimated through, if you want to compute this can estimate, the variance of that for a given data, you just substitute the p cap, the maximum likelihood estimate, and get the sample. That's possible. It's possible that for m equal to 1, it is going to coincide with the UMV estimation. Please also note that UMV estimation most of the time coincides with the variance part. The variance of the estimate, UMV estimate, is going to be equivalent to the Cramer-Rao lower bound. So in this case also we have investigated, and most of the time it coincides. Okay, in some cases, some parametric function cases, we get a better estimate. I mean, the variance is much lower than the UMV estimation. Okay, so we found, in fact, even through this small research, I found that the can estimate, the only drawback, what I can say is that if you numerically compute, the variance of the can estimate is slightly going to be more than UMV estimator or even CRLB estimators. So that is the only drawback. Okay, maybe that may be the reason why people are not using it. But it is not very, very high. I mean, the magnitude is not very high. It's a very small portion it differs actually. But it's more or equal. At the most, it is equal, or in most of the other cases, it's going to be more than the other issue. So that's the only drawback. So I wanted to place that also on record, because we have seen the various parameter function and its variance is computed, can variance is computed, and found that slightly more than the other estimators. So that is going to be, I don't think this is going to be a very big drawback, because we anyway work with large samples. These days, most of the time we have big data and this kind of big data where we can suggest estimators. So that case, I don't think you will have a very huge variance for the estimators. Okay, and for big data concept, because most of the time we will be working with various parametric functions, because a lot of parameters are going to be there in the model. Once you identify a particular distribution, so that distribution may not be from your regular family of distributions. So you can suggest various parametric function estimates in that case. So here is the variance of that the parametric function the UMV estimate of the 1 minus p whole power n. So it's need some computation. I mean, combination based simplification, etc., and that can be done in this way. Okay, so here is m equal to 1. You can get the variance of that UMV estimate. Okay, so that actually coincides with. Yes, the result 3.6 is very, very important here. So look at the parametric function. It's a very big, and you can have a lot of combinations, lot of particular cases also for various values of k here and various values of theta. You can have parameter function of p only. With p1, p0, you can have various parameter functions of theta alone, and with various combinations of k, p, and theta, you can have estimates, UMV estimates for this parameter function. Now, can estimation may not be very easy for this kind of this thing, but we can have some parameter function if it involves only one parameter, and that will be shown. Okay, so here is the estimate hk zrn. So r k r minus 1 k divided by etc. That can be simplified. Okay, it's simply a factorial notation. Okay. So in HSN 1955, that was the first paper which discussed the degeneracy at 0. He provided a UMV estimation for 1 minus p square theta square as phi zrn as what is shown here. You can see that. Now let us talk about the estimator for theta raised to m. Okay, so fortunately we have some, relaxed session that we can estimate theta here with m equal to 1. If you put, you can have estimated for. So please note, unbiasedly, it is not at all possible. But through CAN estimator, you can at least come up with a good estimate. And this, I am definitely going to be, perform better. And I vouch for its performance also in terms of its asymptotic variance. Okay, so if you compare with the MVU estimation or MVB estimation, bound estimation, Kramer-Rao lower bound estimation, this is going to be a better estimate. For a CAN estimator is better for in that case. We have done. There is no need of any simulation here. We can easily compute this in a normal mathematical sense, because you simply get some data and estimate the theta and p and substitute, and you can go for various values so far. So psi t3 for us, another parametric function, that is, again, look at the survival function. It's also going to be a parametric function, right? Probability of x greater than t, in this case, is p power minus t by theta or something like that. So for that, you have an estimate r by n e power minus t by summation xi, and with asymptotic variance p power minus 2 by theta by. Again, we vouch for this particular survival function. This is going to be the one of the best estimate, and the variance is also going to be at par with the variance of the UMV estimation. Okay, and here is the UMV estimation of the survival function, r by n 1 minus t by z raised to r minus 1 t less than z, and the variance is also given, variance of the UMV estimate. Okay, so that can also be computed. You may need simple mathematics. Okay, even in Excel you can carry out. So that's the reason why I'm not done any kind of simulation. There is no need of any simulation. You can directly compare the parameter estimates. Yes, here is the linear estimation of linear parametric function. You can see L1p plus L2p as your psi p theta. And you can see that it's all differentiable everywhere. And even in most of the earlier cases also, you can see that the psi theta function is differentiable, continuous, and not vanishing. So in here also you can see that a simple linear estimation for t, that is t dash, is given in this form with a CAN. Variance is going to be again 1 by p L1 square p 1 minus p by n plus L2 square theta square by np. You can substitute any value of L1 square and L2 square, L1 and L2, and you can decide what is going to be. For a simple way, say L1 equal to L2 equal to 1, for example, you get the asymptotic variance as 1 upon n, p1 upon. So that is norm. That's very, linear. P plus theta, psi p theta become p plus theta. That's again straightforward. Okay, now if you want to see that, compare how it compares with the Kramer-Rao lower bound estimation, we have taken for psi theta is equal to theta square as variance of t is 4 theta raised to 4 by np. So simply substitute the maximum likely estimate of theta and p and get the estimation for the other. Similarly, 1 minus p whole power m is obtained in this particular form. Okay, now I don't want to get too much on the discussion on this part. Okay, so my time is also very, close to. We are now working on some aspects on estimate. The testing part of this. We are thinking, trying whether this concept can be extended for suggesting test procedures for t and theta. So this is the usual parametric test. I have not used so far any CAN estimator, but we are thinking to use somehow how that can be incorporated in this particular one. Okay, so with that I conclude, and we found that one of the viable estimate which can be easily obtained, which is just a plugging in. If you see the definition of CAN estimators, what you need to do is you have to simply identify the function, see whether the conditions are satisfied, and then just plug in. So once the plugging in is done, you may need to find, okay, if you are altogether working with a different distribution, as I told you, in some one place that if that differentiable function, although it vanishes after differentiation, then also you can construct CAN estimator through asymptotic chi-square distribution. In some cases, the blow-up factor an may not be equal to root n. Sometimes you will have to consider an as n. So this discussion is also there in the book. So please refer to the chapter number 6 for all these kind of interesting discussions. We have also constructed CAN estimators based on percentile based estimation also, and through moment estimator also. And interestingly, moment estimators and percentile estimators also coincides with the regular UMVU estimators. Okay, so please read one of the best chapter, in fact. One of the, what I could say as a co-author is that is one of the best and formidable quantity or research point which you can include in your research. Thank you very much. So here are some of the references. Thank you very much, sir.
Professor Ghosh?
I hope I am in time, within time. Okay, 60. Okay.
Yeah, within time.
Yeah.
Dr. Muralidharan, congratulate. Your talk was very clear and very sound.
Thank you.
You explained the subject normal unwise estimator and compared Kane with the UMV also.
Correct.
So now we have time and floor is open. If anybody has question, please ask Professor Muralidharan. Very, very interesting talk. Please ask questions.
Yeah. I'm really interested to know from the students, research students at least.
Yeah.
Who are using estimation procedure. Almost everyone is using estimation or maybe.
I have no question, I have a query. You said that it is a consistent estimator if under convergency, is it strong convergency or weak convergency or both?
Convergence, strong convergence. Yeah,
because it was under probability, but not probability 0 and 1. That's why my query was like that.
Yeah.
It is strong convergency.
Strong convergence, right.
And one dot I have that d psi by dt, you are telling it is continuous and non-vanishing. What is the meaning of non-vanishing at this point?
Non-vanishing means, for example, suppose if you differentiate the psi theta function with respect to p or theta, for example.
Yeah.
Suppose that function, that quantity vanishes, maybe sometimes in some cases becomes 0.
Okay, or negative. Or negative.
Yeah, negative also. That's what is the meaning of it. Yeah. For that also, can estimators are developed. You can see that chapter. Yeah, it is there. Yeah.
Still we have time, please. If any have any question or suggestion or advice, go ahead.
Because he was my mentor after a certain stage, and a very nice guy, Professor B.K. Kale, as you all know. So I had that opportunity to work with him very closely, and very nice guy, very friendly. We had dined together in canteen, and we had a lot of, many often we discuss these kind of things during our snack time or lunch time and all.
I have also met him several times, and he was also my mentor, I can say. He was also guiding, and I am remembering one incident. Actually, when first time 2001, I went to University of Manitoba, Winnipeg, Canada.
Yeah.
So he was first chairman of the department.
Oh, okay.
And
he was there.
When I came from India, they were asking, and his name was Raja Babu there, not Professor B.K. Kale. His name, everybody was knowing as a Professor Raja Babu. So he told me, they asked me, where is Raja Babu? I mean, who is Raja Babu? Then he explained that Professor B.K. Kale. So he was very famous in University of Manitoba, Winnipeg.
Okay. Thank you.
So, Professor Satish, I think now there is no question from any side.
Thank you.
So let us complete the lecture, and I will hand over to you for your.
Thank you, Professor Ghosh, for chairing the session, and thank you, Professor Muralidharan, for very interesting talk.
Yeah.
In fact, I'm also very much interested to hear about Professor Kale.
Okay.
Because this is a time we can. I think you can spend some more time for 5 or say 6 or 7 minutes.
See, Anyway, I
recollect. Yeah.
No issue. I can. See, actually, a note, a press note kind of thing is going to appear very soon. Professor S.K. Upadhyay, they are coming up with an issue. There is a kind of newsletter. So there going to be a kind of. I have written already an obituary kind of thing for Professor B.K. Kale. He asked me to write it, and that will appear very soon. So one or two interesting things I have mentioned. So I told you, very often we meet at his cabin. Sometimes we have discussions, sometimes in canteens and etc. So let me tell you very frankly, he was very fond of South Indian dishes. Very fond. And idli and dosha. Dosha was his favorite.
Okay.
Yeah, not masala dosha, plain dosha. Plain dosha was his favorite. Yeah. So, we know once he said we ordered for a dosha and the dosha came with a very big bag, very huge one. It was going away, out of the plate also. So he found, see, I'm so short. He's very short height. So he said, I'm so short, but this particular stuff is too big for me to eat. We jointly ate that, and
this must be outlier problem.
Yeah, outlier problem. That's exactly outlier problem, right? Yes, his pet projects were all outliers, no doubt. Yeah, we all know that. And estimation is one of the favorite distribution if you talk about, and I think it is gamma distribution. Very fond of gamma distribution.
Right.
Exponential family. Every time he talks about exponential family, he is carrying the Abramovich and Stiegen table of gamma distribution. There's a huge, very big, huge volume book, and he has in possession of that. So
because exponential is increasing or always it is increasing order.
Yeah.
So naturally exponential will fit for every any whatever failure case or is there. Naturally exponential will be fit more better than any other.
Yeah. So exponential family of distributions. Then connecting that with sufficient statistics and completeness. So he has given a very nice proof of this Lehman-Sheffield theorem. Please go through it. The students especially should go through that particular concept. That's there in the chapter number. First chapter is starting with sufficient statistics. Second chapter, first chapter is introduction. Second chapter starts with the sufficient statistics. Most of the time we were taught that in the classroom that it's the properties once you start, it starts with unbiasedness, consistency, efficiency, then sufficiency. But this is the book where you can see that the whole chapter starts with sufficiency, and then the all unbiased estimation is slowly and gradually. So please refer to the book. I'm sure most of the Department of Statistics in India are referring using the book. Thank you very much.
They are using, of course.
Thank you.
In fact, he has produced or he has instrumental in shaping a group of estimation.
Yes. He had a lot of students from Kerala, and especially Kerala, a lot of students have done a PhD in Pune University department. Most of the department teachers are, familiar to Kerala. And so although I am not a student directly of Pune University department, but many often people confused with the same with me. It means they ask me, are you from Pune University? Are you a product of Pune University? But I said, okay, although not direct, but I'm a student of Pune University. So I get a honor that way. So I really enjoy it.
Okay.
Okay, so did I complete very fast? I don't know. I thought I may not. I have to be always in time. I always make sure that
it is time. It is time. Don't worry. It is time. It is already 6:25. Don't worry.
Okay.
It is perfect time.
Thank you.
Can you say, don't worry about the shorten the thing.
Yeah.
Our next session will start at 6:30.
Okay.
So you have break. 5 minutes break is there.
Yeah. Okay. Thank you very much. Thank you, Sadish. Thank you, Professor Bose. Thank you, all others. Thank you, the delegates as well. Thank you very much. I will leave. I'm in the department. I have to go back to home.
Oh, okay.
For a tea, at least. Thank you very much.
Okay, Professor. See you then.
See.
Okay. Professor Bhattacharya, Professor Srilin, also Professor Gauri Datta, also there in the group. I think Gauri Datta is also joined, I think. So.
Am I audible, sir?
Yeah. Okay.
Yes, I am here. Yeah. Thank you.
Welcome, Professor. Welcome. Our session scheduled at 6:30. That is why I'm waiting some 3-4 minutes. We have to, or 2-3 minutes thereafter. We are talking about Professor B.K. Kale, the year just before. That's why. What about the time there, Professor Dutta?
It's 8:57 a.m. in the morning. 8:57.
Okay. 57. So there also we get sharp at 9, isn't it? At the start. Anakha?
Yes, sir.
Are you ready, isn't it?
Yes, sir.
Okay, just a minute. Little bit. Professor Lahmander? Hi, Professor Lahmander. Professor Peter Lahmander. Hi. Yeah. Okay, Anakha, you please introduce the chair and please help the chair to for the smooth running of the session, please.
Good evening. Now we have technical session number 30, which is a special invited session chaired by Dr. Bhadra Charyulu. He is presently working in Department of Statistics, Osmania University, Hyderabad. His major area of research are design and analysis of experiment and data science. He has published 75 papers and also presented 50 papers in national conferences. He has delivered around 100 invited talks in various seminars, workshops, and conferences. We are truly honored to have you here, sir. I warmly welcome you to share the session. Sir, please take over.
Thank you. Thank you.
Professor Bhadrajali,
Am I audible, sir?
Yeah, now audible.
Yeah.
Now audible. Yeah.
Thank you, madam. Thank you, Professor Satish, sir.
Thank you, Professor.
So it is a great pleasure to me to introduce Professor Shilly Lin, the Professor of Statistics, the Wsta State University. She has a co-authored one book and co-edited another book, and also authored more than 165 referred book chapters and journal articles. Her research interests are statistical genomics, genetic epidemiology, and bioinformatics. In addition to the methodological research, Dr. Lin also works on collaborative projects with researchers at Wsta University. Dr. Lin currently serves as Associate Editor for Biometrics, Statistical Applications in Genetics, Molecular Biology. She is also editorial board member of Genetic Epidemiology. She elected as International Statistical Institute member, and Dr. Lin is a fellow of the American Statistical Association and American Association for the Advancement of Science. Thank you, madam. Please, I request you to deliver your talk and inspire and motivate the researchers.
Thank you. Can you hear me?
Yeah.
Yeah.
Okay, so let me try to let me try to share my screen using my iPad because my laptop doesn't work. So let me try that. Can you see it?
Yeah, you can see it's visible now. It's fine. It's fine, Professor Lin.
Great, perfect.
It's visible.
Okay, well, I'd like to thank the organizers for the invitation and the kind introduction by Professor Chai Lu. It's a great honor for me to be presenting among many great statisticians, those in India and elsewhere in the world. I have had actually great memory attending conferences organized by Indian statistical organizations. And I have to say that my fondest memory was the 2010 conference in Hyderabad, and Professor Chai Lu just mentioned that he worked in Hyderabad. In honor of Professor C.R. Rao's 90th birthday. I actually had the privilege of meeting Professor Rao earlier, actually in 2003, when he came to Ohio State University to deliver a really inspiring raw study lecture. He was at Penn State at the time. And so today I'm going to give an applied talk, quite different from the previous talk, but there's some similarity that I'm going to point out. My research interests, as Dr. Chai Lu already pointed out, are generally in statistical genetics. And so my talk will be on discussing challenges and solutions. Maybe you may term the imputation methods for a very special type of genomic data with high dependency and sparsity. And that is the single cell Hi-C data. So to get everybody up to speed, I will start by talking about competent 3D structure, which is the underlying biology, step by step, before getting into the data structure and imputation methods. So this is joint work with two former students. Qing is currently at Novartis, which is the pharmaceutical company, and Chen Gong is at Google, which needs no further explanation. This work is being further carried out by Yong Qi, who is a current PhD student in the department. And so when we draw a chromosome as a statistician, guess what? We typically draw it as straight line, like a piece of uncooked spaghetti noodle, where we indicate genes and the regulatory elements. Of course, this is just for convenience, because the DNA is located in the nucleus of a cell, where that it may only be 10 micron in diameter. So it's a 200,000 time reduction from the thread's length of 2 meters. And so these 2 meters DNA ought to be folded into this tiny space. It turns out that this folding is not done haphazardly. It's in fact highly organized in a hierarchical way. At the highest level, there are these things called the A and B compartments. A containing active elements, indicating maybe regulating genes that are currently being expressed, and B contains inactive elements. Now, within each of these elements, the chromatins are organized into what one calls the topologically associated domain, the TAD. Sorry for all the jargons, but it's important for me to get it straight. And so those located within the domain, and let me see whether I can get a pointer on my iPad. So those located within the domains interacted much more often than those between domains. So this will be between domains. At the finer scale, one can see spatial gene regulation, and that is how distal elements are being brought to close proximity through looping. So you can think of that as now a piece of cooked spaghetti noodle. You can fold it any way that you like, so that the red regulatory elements will become close together with the red gene that it's regulating, and the same for the green counterparts. So the story actually started in 2002, 2 decades ago, and it really revolutionized the entire field of gene regulation. Now, 20 years later, with well-developed technologies, it's known that spatial regulation is actually prevalent not just in humans, but in other complex organisms as well. And the differences in spatial regulation also has a great deal of implications in health and diseases. So as I said, the story got started 2 decades ago with actually chromosome conformation capture, or 3C, which was low throughput. Now, through generations of improvement, in 2009, Hi-C was born, which was able to detect genome-wide chromatin interaction through coupling with next-generation sequencing technology. Many further improvements have also been made, mainly to enhance the resolution and the signal-to-noise ratio. A big breakthrough came in 2017, the banner year for single-cell Hi-C, with a number of technologies developed that you can now produce literally thousands of single cells in one run. And these are really important for understanding cell-to-cell variability and subtype discovery. Regardless whether we're talking about bulk data that involve thousands or tens of thousands of cells or single cells, data are actually naturally organized into a 2D matrix that can be actually divided into blocks. Excuse me. So the diagonal block here denote interactions within chromosomes, and these are called the intra-chromosomal interactions. The all diagonal capture interaction between chromosomes, and so these are referred to interchromosomal interactions. And so this is literally the first Hi-C data set from a lymphoblastoid cell line. And we are looking at interactions between and within chromosome 14 and 22. And so just to make sure that everybody understand here, we see that the first segment and the second segment of chromosome 14 interacted 657 times. First and number 88 do not interact. That doesn't mean that they actually are not connected to one another. It's just that we do not capture the interaction. And this number here indicating that chromosome, the first segment of chromosome 14 and first segment of chromosome 22 interacted 990 times. And so we see that that we can also express the data in terms of heat map, where the darker color indicating interacting much more. So the key challenges here in modeling such data are the spatial dependencies and sparsity, because there are a lot of zeros. And this is, we heard quite a bit of that from the previous talk as well. So let's look at a set of Hi-C data for K562, which is leukemia cell line, our motivating example. So the lab two on the first row are for both data. This involves tens of thousands of cells. And we can see that they are very similar, signaling that there is good reproducibility and provide high quality data showing these topologically associated domains or TAD that I described earlier. And the right two are single cell heat maps that are dimmer, but you can still make out similar patterns. And that is the good news. The problem here is that these are the two best single cell data sets. Among the rest, I'm showing some representative on the second row where there are some patterns that have little resemblance to the bulk data, and some have no signal at all, and some they're just showing random patterns with a few white spots, like what you see when you are gazing into the starry sky. And so, to make matter even worse, the observed zeros are actually not of the same type. Some of the zeros are referred to as structural zeros, representing segments that truly do not interact because of biological properties that prevent them from interacting. But some of the zeros are called sampling zeros, or referred to as dropout. These are simply because they interact in low frequencies and therefore they are missed because of not sufficient sequencing depth. And so the trouble here is that these two things are actually confounded. You don't know which zero is due to which. So it's a mixture problem. The same issue occurs in single-cell RNA-seq data and microbiome research. This may be more familiar to the audience. And the methods have been proposed there in RNA-seq and microbiome for studying structural zero and dropouts. Adapting them for single-cell high-C data have also been explored. There are some successes, but none of the main features of the data, especially spatial dependencies, cannot be accommodated in a straightforward manner. So you may ask, well, are there any imputation methods proposed specifically for high-C data? And the answer is yes, but the objective there is typically described as data quality improvement. And the concept of structural zero, these are really zero because of biological properties, is really not present in those papers. And so this distinction, the distinction between these two types of zeros are not made. However, such distinction is important for downstream analysis. And so to fill this gap, we propose a method called high-C impute. That is a method based on Bayesian hierarchical model. So the main feature of high-C impute is that it considers three levels of data here. There's neighborhood of a position in the 2D data matrix to account for spatial dependency. And then there is information from similar single cells to bolster the information, and then relevant bulk data that comprise of thousands or tens of thousands of cells if such data are available. The output of the model is the probability that a position in the 2D matrix is structural zero, and also the imputed normalized mean interaction frequencies in a particular position in the 2D matrix. At the heart of the model is this indicator variable, denoting whether a position is structural zero or not, and the use of binomial Poisson mixture. So let me try to expand on it a little bit. Recall that this is a mixture problem, and our goal is actually to separate structural zeros from sampling zeros. Therefore, our variable S here indicate whether an observed zero is really zero or not. And this indicator variable is assumed to follow a Bernoulli distribution. Even observed zero is simply a dropout. It's not supposed to be zero biologically, but not sufficiently sequenced, so you don't see it. Or if the observed count is not zero, then the count follow a Poisson distribution, leading to this binomial Poisson mixture that I already mentioned. And that can actually capture not only structural zero, but allowing for zero inflation as well. The three levels of data, again, the neighborhood, similar single cell and bulk data are really naturally captured and integrated into a Bayesian hierarchical model framework, with all of them contributing to the price of the hyperparameters. And then MCMC is then used to explore the posterior distribution of the parameters, especially the identification of the structural zeros and implication of the dropouts. So let me first show you some results considering data quality improvement, because these are the ones that there are methods available in the literature. We simulated high-C data set model after the K562 real data set, the motivation example, where the ground truth is known because it's simulated, and we call them expected. We can see that Hi-C recover the true underlying heat map really well and much better compared to the other three comparison methods, where the 2D-MF is the 2D mean filter, and then there's the 2D Gaussian kernel. And again, both are based on smoothing. And then there's also the RW3S, and this is the popular random walk method. We can see that the imputed value from Hi-C impute is highly correlated with the expected, whereas the other methods have lots of random scattering. Further, based on 5 other criteria, we can see that Hi-C impute is highly sensitive for detecting structural zeros, have high correlation with expected and observed, low bias, mean square errors. Finally, we use the ROC curve to clearly show that by taking both sensitivity and specificity into account, Hi-C impute is better than the 3 comparison methods by a large margin. So next, we applied the method to several real data sets. The first is on a single cell data set consisting of 14 GM cells and 18 PBMC. With the observed data, there was 1 misclassification for GM and 7 misclassification for PBMC. Now, with the imputed data from Hi-C impute, all GM cells were clustered correctly, and the 7 misclassification is reduced to just 3. So that's a very large improvement. But if you would use the 2 smoothing methods, you don't see improvement. If you use the random walk method, you actually see that it goes the opposite direction, basically making things worse. Hierarchical clustering result also shows that Hi-C impute only have 3 mix-ups. So just like before, we can see that the imputed data from Hi-C impute are highly correlated with the observed data, whereas the other methods scatter around, and this is now a real data set. So it's very similar to our simulation result. I want to show you the second application that is to the K562 cell that motivated this study and inspired the simulated data. For this data set, we have 2 types of K562 cells. One is A, one is B, and each has both data available as well. But just like we discussed before, other than some, which is about 10 single cells, the rest has extremely low sequencing depth, very little data. So we only consider 10 best cells on this left range of the dendrogram that has sequencing depth of at least 5,000 times. Our result lead to the same conclusion as before, and that is Hi-C impute provide a much better result. It got no error compared to the other methods. The most interesting one is the last application that I'm going to show you. Okay. And so this one is about the frontal cortex cells. It's known that there are 14 cell subtypes, but 8 of them were all clustered together if you are using these data sets before imputation. And what's interesting is that there are 2 particular subtypes called the L4 and L5 that are located on different cortical layers. These are the neuronal subtypes, and are expected to be separated, but you see a lot of mixing here when you use the observed data. And so this presents a far more challenging problem than the previous 2. And we are really happy to report that Hi-C impute was able to separate L4 and L5 completely. And in fact, our analysis based on dimension reduction method shows that there are actually 2 further subtypes, each within L4 and L5. And that is consistent with the literature on the existence of subtypes. On the other hand, we look at all the other comparison methods, and we did not see any improvement at all. And this is showing the high correlation between the the imputed and the observed much higher than the 3 comparison methods. So since one of the major goals of Hi-C study is really to investigate gene regulation, we also study whether the different subtypes of L4, L5 lead to different gene expression profiles. Plotted in the heat map are the 500 position in the 2D matrix that have the largest variations among the cells. And we also did a two-way clustering that places L4 and L5 in the two L4 subtypes in the purple and the 2 L5 subtype in the orange. Zooming in on the 200 MB regions in chromosome 20 for the 2 L5 subtype, just an example to show you, we see that the subtype on the right has higher intensity than some larger domain structures. It's reassuring to see that the corresponding gene expression data for 2 L5 subtype in this region also shows clear differences in gene expression based on data from literature, indicating that we perhaps have got the right thing that people were not able to get in the past using Hi-C data. So all is well with Hi-C impute, but there must be a catch, as always. And yes, indeed, there is, which is that Hi-C impute runs much slower than the other methods, as you can see here. But it's obviously a good idea to utilize information from neighbors and similar single cell. You've got data there, you really do not want to waste them. And so therefore, we propose another method that we call cell representation smoothing, or SRS. So this method is inspired by the smoothing idea in the 2D mean filters and 2D Gaussian kernel, but there are two key differences here. The first difference is that the weights in our method in SRS is chosen adaptively instead of being fixed. And the second is that we borrow information from similar single cell to achieve shrinkage effects, which is not done in the other method. They just look at one single cell at a time. The parameters are then estimated using a lasso type penalization optimization. For computational efficiency, what we did was that we vectorized the data from each single cell, and we take neighborhood into consideration. So the effect matrix here is this B matrix. Already itself is sparse because the neighborhood are taken into consideration. Only cells in neighbors contribute, not everywhere else, and so therefore it's already sparse, and that's not in the penalty here. But we do penalize the effect size of similar single cells. So if you recall, the effect size of similar single cell is in the gamma. They're collecting into a matrix. So in matrix notation, it's really this gamma matrix you are penalizing. So in other words, you might have a set of single cell that you believe are similar from other biological knowledge, but we want to be data centric. It's a data informed selection. And so if a single cell, we put it in and it doesn't really contribute to helping with better understanding structural zero in imputing the dropouts, then we just drop it out by having this penalty term. For computational inconvenience or feasibility, optimization is iterated between the data matrix and the gamma matrix. So after the observed zeros are imputed, we model the imputed data using a mixture of Gaussians. And as I have already said, it's understood that structural zero are those with very small counts. And so when you go through this SR procedure, it will still be very small. And so therefore, we compute probability of each observation belong to a structural zero, assume that the component that has the smallest imputed values with small variance represent structural zero. And so therefore, we have a rule of deciding which observed which observed zero is structural zero, and which observed zero is not structural zero. And they are then the imputed normal counts, the normalized counts, and then these imputed normalized counts are then further transferred into at the scale where they were originally measured. And so then we assess the performance of SRS and compare to the same set of data quality improvement methods using the same K562 inspired simulated data that we use for high-C impute. And what we see here is that SRS can really recover the underlying structure well, just like high-C impute. In terms of the 5 different evaluation criteria that we used earlier for high-C impute, averaging over 100 simulations, we can see that SRS is competitive and often outperform the other methods. With good simulation result, we apply SRS to the same 3 data sets, and the results are clearly showing that SRS perform well. As you see here, SRS has much higher correlation compared to the other ones. And it clearly shows that the last data set on the brain data is the most difficult. However, we can still see that L4 and L5 are actually clearly separated. You see that L4 is that triangle. Don't know where you can see that, and L5 is the dot, and they are completely separated. But the other 3 comparison methods, just like the observed, they are not separated at all. However, despite this good news that we can separate L4 and L5, we do not see additional subtype within each of L4 and L5. And so in that regard, it's perhaps inferior to high-C impute if those additional subtype that we saw was real. However, SRS is much faster. Computationally, it reduced the computational time by a factor of at least 2 or 3, and it can be much larger depending on the type of data. So as we can see here, for this particular data set, it reduced the computational time from 1.5 hours to just 3 minutes. For the most difficult data that we're seeing here, it reduced computational time from 17 hours to just over 5 hours or less than 6 hours. And so it's computationally much efficient. And certainly there are rooms for improvement for further improving computational results, and this is what we are currently working on. And so just to summarize, just a couple take-home messages. The first is that the data structure for high-C is quite unique, and so special attention is needed to come up with methods that can accommodate such features for better imputed results. And obviously, we didn't want to reinvent the wheel at the beginning. We adapted existing methods, and they just didn't work well. And so for these special type of data, it seems like new methods are, proposing new methods is really in order. The second is that single cell high-C data present a huge challenge, just the sheer amount of data. So we are really in the big data era. Genomics has been in the big data era for a long time, but now in other domains as well. But it remains a really huge problem in genomics. And what we are doing right now is really just the beginning. We have just scratched the surface, so to speak, and it would be great to get more statisticians to be involved, especially the young researchers. And finally, another performance message is that computational time really dictates scalability and criticality of the method. If your method runs quickly, people in the practical domain will be willing to give it a try. If it runs slowly, good luck of trying to convince people to use it. Even though I have to point out that one cannot sacrifice important features just for the speed, because as we saw in the brain data example, if you just simply use a quick and dirty method done in seconds, you are really not able to not just separating the type. They are on different cortical layers, but you are not able to detect the fine structure of the cell-to-cell variability, the subtypes. And I'm going to stop there. Thank you for listening, and I'll be happy to take questions.
Thank you, Madam. Any questions or any from the audience or participants or researchers?
Hello, ma'am.
Yes.
I have one queries. Thank you very much, ma'am, for your wonderful presentation and very nice work. I would like to know about whether this genome data is mentioned in your work is available in database like Geo database, or is there any specific database from which we can get this data?
Yes.
That is my first question.
Yes, that's actually in our R package in GitHub. And so if you would email me, I will send you the link to my GitHub, the R package, where all these 3 data sets, also the simulated database on one of the data sets are all there. And so I will be happy to share that.
Okay, this work is done in R package, and you have developed a package for this analysis?
Yes, so the HiC, so there are 2 pieces of information or packages that I talk about here. One is HiC Impute that has been published, and the R package is publicly available. The SRS is a bit more preliminary that has not been published yet, but the R package is also available, and I will send you the link to both of them. So that you can...
Ma'am, my name is Bindu Punathambarambat. I did my PhD in gene expression studies also, and I will contact you. Thank you, ma'am. Very interesting.
Yeah, thank you.
Thank you very
Thank
much.
you for interest. Yeah, it's great to hear that there are other people working in this area.
Yeah, thank you, ma'am. Very interesting talk. Thank you very much. Thank you.
Thank you.
Any other colleagues?
Yes, sir. Can I speak, sir?
Yeah, Balakrishna, sir.
Yes, sir. Sir, I'm pursuing my research in statistics department in a deemed university in Mangalore, India, sir. Mangalore, Karnataka, India, under the guidance of Dr. Ismail, sir. Sir, my topic of the research for PhD is also the same, sir. My topic of the research is generalized mixed model for genomic studies. And I'm facing little bit difficulties. Why? Because I'm just going through the lot of review of literature where the review of literature is saying how successfully we can classify or discriminate the genomic conditions based upon the characteristics or the features. Then here, I just wanted to know whether this technique of IC is what I understood from the presentation is this also is this is taking a less time and giving the high impact of discriminating the data. So I just wanted to learn more about this. Can we get any material for this to do this month?
Yes, so sorry that your voice keeps sort of cutting out and a little bit murky for me. I could not hear you clearly.
Due to the weather, due to the heavy rain here, the weather condition is not so good, man. So that's why the network is fluctuating.
Yeah, it's not. Yeah, sorry. So sorry. It's not very clear to me, but I would absolutely be happy to discuss this with you. Again, send me an email and then we can talk. Or email or talk. And I would say that many of these so the method that I'm discussing today actually have broader applications in other areas of genomics as well. And I've been working in this area for 20 some years, and we have been building on things. And so potentially it could be something that to look at, or I can point you to some literature. So please contact me, and I'm so sorry, apologize again. It just doesn't come clear to me, and I don't want to misrepresent your question.
Yeah, you can contact my mail, madam. Madam may provide the material related to the work.
Sure, thank you, ma'am. Thank you. And even I'm just working on a calibration model, ma'am. which is a combination of the hybrid model with partial least square with clusterification. I send my work, ma'am, just to go through any, from your side, any guidance if I obtain that will be very lucky for me to proceed with that, ma'am.
Yes, that would be wonderful. So please just send me an email and then we will take it from there.
Sure, ma'am. Sure. Thank you so much for your time, ma'am.
Yeah, thank you. Thank you for your interest.
Thank you. Any more? Thank you very much, Professor Sherilyn, for your excellent talk and wonderful talk on the challenges in high-dimensional genomics and statistical inference. Thank you very much, madam, for delivering and motivating the researchers towards the same. Now, I request Professor Gauri Shankar Datta, sir. Sir?
Yes, sir. Yeah, thank you. Thank you, Dr.
It is great honor to me to introduce Professor Gauri Shankar Datta, Professor of Statistics, Department of Statistics, University of Georgia. He received his PhD from the University of Florida in 1990. His research interest is Bayesian statistics, model-based inference in survey sampling, small area estimation, and large sampling theory. He serves in the editorial boards in many statistical journals, and including the Journal of Royal Statistical Society Series A. He is elected as a fellow of the American Statistical Association, Institute of Mathematical Statistics. He is also the statistician at the US Census Bureau. Now I request the professor to hand over and
thank you, Dr. Chariulu, for the nice introduction. And Satish, thank you very much for your kind invitation. I hope you can hear me.
Yeah.
And you can also see my screen, right?
Yes, sir.
So I'll try to do this full screen. Let's see. Okay. Yeah, thank you very much.
Yeah, now it is fine.
Yeah, okay. This is actually, joint work with my former student, Dr. Hichol Chang. And this is also, as I have some association with the US Census Bureau. So there is some work on small area estimation that I'm going to present here. So standard disclaimer. What is basically small area estimation? In the survey sampling, usually data are collected at the national level, in the sense that survey is designed to have the required sample size so that you get accurate estimation of some characteristics when you are estimating that characteristics at the national level, maybe for the country, say India or US, like that. However, for the same characteristics like, say, unemployment rate or income, you like to know not only for the national, but you also want to know for what's the unemployment rate for the women in some particular state or some district and like that. So in that case, the data that we get from the survey, and if we just look at the subset of the data corresponding to that demography or geography, so now the data size is much small, and consequently the sample mean or some other quantity like ratio estimate and things like that, they will be less accurate. So now question is how we can improve those estimates by building on some other using data from some other variables or data source. And that is basically the whole idea of a small area estimation by borrowing information from other covariates and other related demography or geographical areas, and we improve on the direct estimates, the estimates that are computed based on the sample from a particular areas. So in the small area estimation, there are various ways to build or develop a model. Here we are going to look at what is called area level model, and the corresponding parallel version is the unit level model, basically the units that you collect the data on in the survey. So now we are looking at the summary data, YI, for the ith small area. It could be like a district, or it could be like the women in some district or in some state, and we want to look at their characteristics, like maybe their average income or unemployment rate or some other characteristics. Okay, and the theta I is the corresponding population characteristics, and we want to estimate that. So the model that is used, that YI, is kind of an unbiased estimate of theta I. So we just write it like that: YI is theta I plus EI. EI is basically the estimation error. It's called the sampling error. And if you have a large enough sample, relatively large, then the EI will be approximately normally distributed based on central limit theorem. So here we are assuming that that sampling variance corresponding to EI is DI, and we are assuming that this is estimated. Actually, we will treat it like known. And for the theta I, the main quantity that we want to estimate, and there are m small areas, okay? And for all m of them, we want to estimate this theta. So this is like a simultaneous estimation of many related parameters. So for theta I, you are saying that there are some covariates, and that actually explain a big variability in the theta values, these covariates of xi. And we are assuming for simplicity a linear regression model for theta I, which are actually latent variables, unseen, unobserved. So we are using a latent multiple regression, linear regression on the xi. And that error term on the regression is the VI. That's basically the random effects. It's basically saying that whatever variability in the theta I cannot be explained by the linear regression on xi's, that's like part of the model error. So based on these two models, if you look at it, that YI is related to theta I by this sampling model, and theta I is related to xi, and together actually you can combine as a mixed linear model. Or and then using mixed linear model, you can make inference on the theta I, and you can use empirical based linear unbiased predictor approach to make inference about theta I, or you can be a Bayesian. You can put a prior distribution on beta and sigma square V, and you can make inference on the theta I. This is in the spirit of James Stein's shrinkage estimator. Here I have a map here for the US, the counties, and what we have here, based on this National American Community Survey, we have based on 5-year data from 2013 to 2017, we estimated the median household income for counties based on American Community Survey. So based on the 5-year data, in US there are about 3,000 counties, and for most of the counties you get data when you combine data for the 5-year period. And if you look at this map here, that you can see some kind of special dependence. The neighboring counties, they have like the income. If you look at the color code here, that somewhere you might see the deep color, and they're kind of neighboring, and then other places you see light color, and they're also kind of close to each other. So there is some kind of dependence actually in this these characteristics of household income. So we like to use a suitable model to explain the similarity in the population characteristics for the nearby counties or nearby areas. So first thing is that without the special dependence, the neighboring areas, we look at the standard model, what is the Faharian model, And here, all these random effects VI, V1, V2, Vm, they are assumed to be independent, IID. And here is this model in the hierarchical Bayesian form. You write this Y as this vector of M components, and similarly theta is a vector of M components, and D is a diagonal matrix, known matrix of the sampling variances. And you have this X as the design matrix corresponding to the covariates. Then this model that we had here, you can write it in the matrix representation, which will be like this: that given theta, beta, sigma square v, this is a hierarchical Bayesian representation of the model. So it's a multivariate normal, mean vector theta, and variance covariance matrix D, which is known. And given beta and sigma square v, this vector theta has multivariate normal with mean vector x times beta and variance covariance matrix sigma square v times identity. In the Bayesian case, we put a prior on beta and sigma square v, and you might have a proper prior, or you might have some other non-informative prior. And in our analysis, we're going to use a non-informative uniform prior. That means G function will be equal to 1. So that's basically the standard model. But when we see this dependence in the characteristics in the geographical variation, a special model might be useful. Here is a map of the median household income of the counties in Georgia. That's where actually I live in USA, and there are 159 counties, and you see that this dark area here, that's basically the Atlanta region, and those counties nearby, they have higher income, whereas there are many rural counties in the south or in the southwest, or in the west, they have less income, and they're kind of grouped together. So there is some kind of special dependence in the characteristics of this household income, and how to exploit some special dependence to improve on the estimated household income. And so here is basically I'm showing you for a special models. This corresponds to the simultaneous autoregressive model. I will introduce it below later on. So corresponding to this model, there is a parameter there. This rho equal to 0. That's basically essentially corresponds to independence of all these characteristics plotted here for all 159 counties. And you see that there are no specific pattern you see when rho equal to 0. On the other hand, when you take this extreme value of rho equal to 0.95, rho is a number parameter which is between -1 and 1. It's something similar to the correlation parameter. The higher values of rho will introduce higher degree of dependence, and a value of rho equal to 0 is no dependence. And you see that as I increase the value of rho, pushing to 1, like close to 0.95, you see that a lot of like this northern region of Georgia, all of them have like white color, like those are the smaller values, whereas kind of in this the central east, there are a lot of deep color like that. So basically you get, if you have much special pattern in the dependence, then you need to have a higher value, and if there is no such dependence pattern in the spatially, then you take rho very small in absolute value. So that is a simulation based on the spatial autoregressive model. So, and then here there is another geographical representation for the 4% family median incomes for the 49 mainland states in US and Washington DC. And this is coming from the data collected in 1990 census. And based on the 1990 census, you get income for the 4% families in the state, and you look at the median income here. And you look at this geographical plot, and you have this, see that there are some, the neighboring areas, they have kind of similar neighboring states, they have similar color. And so basically it is indicating there is some kind of dependence here. And, you can measure the dependence based on the Moran's I, and Moran's I for this particular data is like 0.44, which corresponds to a rho equal to 0.8 for this SAR model that I introduced before. And here I'm just simulating for this SAR model corresponding to rho equal to 0.8, which will give a Moran's I equal to 0.44. And if you see on the right panel the simulated data, and the left panel, which is the real data, and this is the population characteristics coming from the sensor, you see that you can capture the spatial pattern. You do not see the exact same pattern here, but I'm just trying to tell you that there is a pattern here, and whatever the difference is that, because here you have the actual value. On the other hand, this is a simulated value, but we did not use the same parameter that would be appropriate. Only basically we use this to capture the spatial dependence. We use this rho parameter. To introduce these spatial models, so if you look at here, there is this geography here. These are the states. So we say that state here, Florida, and then state Georgia and state Alabama, they are kind of neighboring states. So to indicate that they are neighbors, like 49, we are going to introduce a 49 by 49 matrix, and that matrix diagonal elements will be all 0, and the off-diagonal elements for Florida and Georgia will be 1 because they are neighbors, whereas Florida and South Carolina here, that off-diagonal element would be 0 because they are not neighbors. But on the other hand, we look at Georgia and South Carolina, they are neighbors, so that off-diagonal element will be 1, and otherwise it is 0. Like Georgia and say, if you look at New York, they are not neighbors, so that off-diagonal element will be 0. So it's like a 49 by 49 matrix of 0 and 1. All the diagonal elements are 0, and off-diagonals are 1 if two states are neighbors, otherwise 0. And so that's basically the matrix W. And this matrix W is a normal matrix, and some properties there. The eigenvalues of the matrix, the smallest eigenvalue is negative, largest eigenvalue is positive, and then if you look at a matrix L, diagonal matrix, basically you just sum the W matrix, which is a symmetric matrix. You just sum the elements in the across row, the ith row sum. You get this L matrix here, and this L matrix is going to be positive definite. And if you have some correlation parameter rho, the parameter rho for that L minus rho W matrix is going to be positive definite. And then this matrix L inverse W, it's a stochastic rho stochastic matrix, and which is important in defining this the simultaneous autoregressive model that we talked about before. And there are some properties that eigenvalues of W tilde will be bounded between -1 and 1. And for any row between -1 and 1, this I minus rho W tilde is going to be a non-singular matrix. In fact, it's a positive, this determinant is bigger than 0. So using these matrices, the W matrix here, from the W matrix, we create this L matrix here by summing the elements on each row. And then corresponding to matrix W and L, we define the W tilde matrix here. And then also we define L minus rho W matrix here. And based on L and W, we introduce the matrix R here. This matrix R is also a positive semi-definite matrix. So based on these matrices, we introduce 4 positive definite matrices, omega 2, omega 3, omega 4, omega 5. These corresponds to, if you take the inverse of that, they will give the variance covariance matrix for a simultaneous autoregressive model, random effects, simple conditional autoregressive, or Leroux conditional autoregressive models. So these are some of the most important spatial random effects model to capture spatial dependence among the random effects quantity, the V1, V2, Vm that I introduced before. And in our simulation, I use this model SAR for various values of rho. If you remember that I use rho equal to 0, 0.75, 0.85, and 0.95. And inverse of this matrix is actually going to be the variance of the random effect having simultaneous autoregressive model. So these are the models. So based on those quantities, our model is now the hierarchy-based model is for the data y. It's y given theta beta sigma square v is normal. This is same as the one we introduced before for the simple Faherian model. Now we are building in dependence among the theta quantities through this special variance covariance matrix, that omega k equal to 2, 3, 4, 5, and omega 1 is just the identity matrix corresponding to the Faherian model, and omega 1, omega 2, omega 2, 3, 4, 5 introduced here. Okay, and there is a single parameter, and sigma square v is the variance parameter. And we are going to study all these models in our setup. So this plot that I showed you here, we are going to analyze this data, estimate. This is coming from the census data. So this is kind of the true values, but not every year we have the census. We have the census every 10 years. But there is survey going on, like this American Community Survey. It is going on every year, and it provides you data for the median income for each of these states. And we want to use the median, the income data from this survey, and also we want to use certain covariates to improve for the years in between census years. Okay, so we are going to talk about, in particular, we are looking at, we are considering estimating again the 1990 census income. The reason we are using 1990 census because it will allow us to use the true value that we get from the 1990 census, and we can see how accurate, how good is our various models and estimation methods. Okay, so what we have, the data yi, it's the estimated median income for the 4-person families coming from the data collected in 1990, the current population survey. It is a big survey in US. It is carried out monthly, but the income data is collected only once a year. Now, to explain, to borrow strength on this improve this estimate from the current population survey, we are looking at some covariates. You know that if you are estimating the median income for a state in year 1990, obviously that state's situation will depend on what it was the case for the 1980 and 1980 census. You have the true median income, so that number is kind of known, and use that thing. On the other hand, 1980 and 1990, they're kind of little bit about 10 years apart, so situation might change over time. So to update that situation, we also look at the per capita income, which is available for every year from some administrative data. And we are looking at the per capita income for the 1979, and also we're looking at the per capita income for 1989. And based on those two per capita income, we are adjusting the 1989 census median income, and we are creating a second covariate xi2. Okay, so this xi2 happens to be, x2 happens to be more important than x1, because x1 is a little bit obsolete, whereas x2 has been created by updating the old census median income. And we are going to use both these variables, x1 and x2, to generate estimate for the true median income for the 1990. And a surrogate value for 1990 income is coming from the 1990 census. Okay, so we want to check the accuracy of our estimator based on this census value. The reason you might say that why that the census value is also actually not really the truth. It's based on a much bigger sample. It's like it's about 16% of the whole population provide data on the income during the 1990 census year. So in that sense, it is not exactly the true value like the theta I value, but they should be kind of similar. So now, just to show that if what I'm trying to show you here, that as I mentioned to you, the covariate X2 is kind of more appropriate in explaining the theta I than the covariate XI1, because theta I is the characteristic for the 1990, whereas XI1 relates to 1980. It's kind of an old data. So what I'm doing here, I'm just looking at the usefulness of the spatial model. So what I have here, I have two mean models. One is involving both the covariates, and the other one is involving only the covariate X1. Covariate X1 is a little bit less useful in estimating the mean function, the mu, which is giving related to the theta actually. And if you look at here, what I have provided here for these various spatial models, I have this estimate of the rho based on the Bayesian method. And the rho is like you have this mean here, posterior mean, and the posterior standard deviation. And in the first column, you can see that all the rows are kind of within, if you try to test, if you look at the confidence interval for rho based on the point estimate and the posterior standard deviation, you see that for most of them, the zero is actually included. In other words, one can claim that the rho equal to zero is a possibility. And rho equal to zero means that you do not need to use any of the spatial model. So for that, basically, the independent Faharian model is appropriate, good enough. On the other hand, if we do not have a good covariate, in this case X2, if we do not have that thing, then again, if we fit the spatial models, these various models, we get these different estimates of rho. And you see that point estimate for this simple conditional regressive model, rho is 0.14, and the posterior standard deviation is 0.04. And definitely, the zero is not within 2 standard deviation of the mean. You can see that this is true for all of them actually. And then basically we can claim that rho is definitely different from zero. So in that case, this is from this simple analysis shows that when you do not have good covariates, you will be better off including adopting a spatial models for the variance for the random effects. On the other hand, if you have good covariates, you may not need a spatial model for the random effects. So I just did this, fitted all these models, and I look at, as I said, that theta I star that's coming from the 1990 census. This is like kind of it's called the gold standard. It's not exactly the theta I, but it's based on like, 1/6 of the data of the entire country, entire state. So this is kind of a reasonably accurate estimator of the true value theta I, whereas theta I hat is the estimator of theta I based on the model. And we fit 5 different models, and we compare these 4 spatial models in terms of the percentage improvement in average square deviations. Okay, this is for these 49 states. We look at the estimate and the gold standard value and look at the average square deviation. Or you can simply look at average posterior standard deviation, and I'm looking at the corresponding the spatial model SP, and the Faharian model is the standard model without spatial structure. And if this number is bigger, that means you are getting bigger improvement by using a spatial model. And if this is not so good, then you are not getting much improvement. And here I'm showing you when you have both X1 and X2. I showed you before that when you have both X1 and X2, the spatial parameter is not really significant. And you can see that the maximum improvement in this mean square prediction error, you get like maybe 15%. Whereas if you do not include the most important covariate X2, you just include only X1, you can see that you get actually quite a bit of improvement in the mean square prediction error over the independent Faharian model, like you get like 40% and like that. And similarly, in terms of the average posterior standard deviation also, you get a lot of improvement by using spatial model. The thing is that the important thing you need to consider, keep in mind, that when you have good covariates, you possibly do not need spatial model. Many times we do not have good covariates, and in those cases we should gain significantly by using the spatial models to model the random effects. Basically, the spatial model is capturing the variation in the true parameters which are not explained adequately by the covariates, because in those cases we do not have good covariates. How much time I have?
You can take some more time, no problem.
Okay, thanks. So here, I'm just again just showing you that sometimes in small area estimation, as I told you, in the U.S. county, there are more than 3,000 counties, and this American Community Survey every year it collects data for about 1,000 counties, but over 5-year periods, when you combine that American Community Survey collect data for all the 3,000 counties. But over the 5-year period, the income or poverty data will be kind of little bit less, will be outdated. So if you want to estimate the income or unemployment rate for the counties, you need to do it every year based on annual data from the American Community Survey. And that American Community Survey annual data, it does not give you data for all the counties. So those counties for which you have no data, they are called non-sample counties or unsampled. You have no data, so you have no direct estimate for those. All you have for those is the corresponding covariate xi. And you use the model, and if you know the value of the regression parameter beta, which you can estimate from the counties for which you have the data, and you can plug the value of beta in xi transpose beta, and you get an estimate for theta I for the unsampled counties. Okay, so here we are trying to show you that if you have for this, again for this 1990 US census data and 1990 current population survey data, we kind of created a data set by arbitrarily, randomly removing states, like this is Mississippi, Oklahoma, Arkansas, South Dakota, like that. So we created like 12 different data sets. There are 49 states we are talking about, and from in these 12 states, in some set we have removed 4 states data from the modeling, and in the last case we removed 5 states data from the modeling, and we are basically estimating the theta values for those states which have been removed from the analysis data set. Okay, so remember that we know kind of the true value from the 1990 census, so we are just comparing the estimate of these states for which we are not using the data, and how good various spatial models do in predicting these or estimating these the median income. Okay, so what I did in terms of little bit of notation, I'll just skip these things. Basically what I'm saying that the first M1 areas we do not have any data, and then last M minus M1, which I call M2, they have data. Okay, and then based on the data part, you write this model here, and for all the entire vector theta, you still have the same model as before, and for the parameter beta, sigma square, v, and rho, you use the same the prior distribution that we used before. And idea is to estimate the theta values for the states for which we have no actual direct estimate y. And you can also do it for the other thetas also. There is no problem with that. So I'm just, and there's some little bit of theory here. I'm just skipping that thing. One thing is that if you use independent Faharian model, for all the states for which we have no y value, their estimate is simply just the what is called the synthetic estimate. It's basically the xi times the corresponding beta estimate. On the other hand, if we use spatial model, then it will be that a linear combination of xi transpose beta estimate and the residuals for the neighboring states for which we have the data. Residual means yi minus xi transpose beta estimate. That's the residual. Okay, whichever state has neighboring state has residual, that will be used in estimating theta I. Again, I'm just comparing the same quantity, the square deviation. The theta I star is the gold standard for the ith state, and theta ki hat is the estimate of theta I for this that ith non-sample state based on the kth model. And we're just comparing with the base model, the Faharian, where basically no spatial dependence there. And we're looking at this ratio of the square deviation. The smaller this number is, that means that better is the spatial model in predicting or estimating the theta value. And similarly, you can look at the ratio of the posterior standard deviation. And the smaller this value is, better is the spatial model. And you can see that the blue color means that spatial model is doing better, and red color means that spatial model is not doing okay. So if you see that more or less, you see more blue or bluish color than red or pinkish color. So all in all, we can say that the spatial model is actually giving you some over the independent Faharian model. It is not uniformly good, but when you look at the accuracy of the estimator in terms of uncertainty estimation, you can see that the ratio of the posterior standard deviation, these are all compared with the posterior standard deviation from the independent Faharian model. So this ratio is more or less smaller than 1. So this blue color means that the spatial models are actually better than the independent model. We have a simulation study here. That's for the actual data I showed you. Now here we have a simulation study. And again, we are just simulation study is actually formulated following the setup of this US states example, 49 states. And what we did, we randomly excluded 7 states, 1/7 of, and for those 7 states, we do not generate any data for the Y. And for the remaining 42 states, we generate the data, and we have the value for D values, the sampling variance we get from the actual data. We use that same D, and the random effect variance sigma square V used to be like half of D bar, and we take the value of rho equal to 0.85, which is actually related to the Moran's I for the 49 1989 census median. You remember that that number is available from the 1990 census, and that Moran's I came out to be 0.44, and that 0.44 Moran's I will translate into a value of rho if we equate that thing to the Moran's I that we get from this variance covariance matrix for simultaneous autoregressive model. So we use that rho, and what we did, we generated 2 covariates x1 and x2 independently, and we generated those two based on this simultaneous autoregressive structure. We use the value of rho here corresponding to 0.85. And so if you look at here, x1 and x2, they have like a special structure there, spatially dependence. And using x1 and x2, we create the mean function mu, which beta 1 x1 plus beta 2 x2. And we took the value of beta 1 equal to 2, beta 2 equal to 1. That means that x1 is kind of prominent in determining the variation of mu compared to x2. And we have generated 100 simulated data sets. And for the SF data set, now we generate theta S from multivariate normal, mean mu, and variance sigma square V times identity, okay? And sigma square V, I told you that it is half of this value, the known values. And then for the generated theta, we compute the Moran's I, and we just split these 100 data sets based on the low Moran's I, medium Moran's I, and high Moran's I. So basically 1/3 in the lowest group, then middle 1/3, and the high 1/3. So like that. And then, so we have this special dependence in theta s through mu. And then we are using this model, and we want to estimate the theta 1 corresponding to the unsampled areas, unsampled states, and also theta sub 2, those are corresponding to the sample state. So we have two settings, the two covariates. One case I look at, we exclude the good covariate. How much time I have?
Sir, already time is over, sir. Please,
Okay, so
now
you can take one.
we can give some, no problem, sir. Next time,
yeah.
there's a brainstorming session. That time we can utilize if needed.
Okay, okay, thank you. I appreciate it. Thank you.
Thank you.
Okay. What I'm trying to show you, the main point that I'm trying to drive here, that if you have good covariates, which is very important in small area estimation, if you have good covariates, you possibly do not need sophisticated spatial dependence modeling. But if you do not have good covariate, your estimator will be improved if you use spatial model. Okay, so I'm looking at two cases that, as I told you here, that mu is generated this way, beta 1 x1, and theta is basically dependent on the mu, and then the independent random effect. So there is a special pattern in theta, and when the pattern is dominated by beta x1 because beta 1 is bigger than beta 2. So now when I'm feeding the model, the simulated that we're analyzing it, we can analyze using only the second covariate, which is a weak covariate, or we can analyze the data based on x1 and the intercept, the strong covariate. We did not analyze based on both the covariates x1 and x2, because if we do that, then there would be no special pattern, because all the special pattern will be captured when you include both x1 and x2. So there would be no need to study the special the model. So that's why we are just looking at x2 and x1 case. And obviously, you kind of guess that in this weak covariate case, a lot of the special pattern in the theta is unexplained. And if you want to recover that special dependence, you need to use some special random effects model that we have introduced. On the other hand, when you have used the best covariate in the model to estimate the mean, to explain the variability of the mean function, you possibly do not need the spatial model, or in other words, you may not gain a lot by using a spatial model over the independent, the Faharian model. Okay. So what we have, we basically for each of these setup, we feeded 5 models, like the independent Faharian model and 4 spatial model. And for each of those, we are estimating the theta for the sample states and for the unsampled states. Okay, so theta sub 1 is the unsampled, and theta sub 2 is the vector for the sample state. So theta sub 1 is like 7 component, and theta sub 2 is 42 components. Okay, so now I'm just looking at this a subset of the small areas M49, but we split it into unsampled. There are 7 of those, and sample there are 42 of those. So we're just grouping the simulation results based on if we are predicting for the unsampled states or we are predicting for the sample states. Okay, so and now this is the mean square prediction error for the SH simulation. Okay, for the SH simulation, and then we are averaging these simulations, SH simulation, for all those simulations for which we had the low Moran psi. We average over that. Then there are SL replications which has a small Moran psi. We average that, and similarly we do it for the medium set of simulations for which we have the medium Moran psi, about 33, 34 simulations, and also high the subset of the simulations for which we have the high Moran psi. Okay, so we have those numbers. And we are doing this thing for each of the 5 models, like the K is 2 through 5. This is 4 different spatial models, and K equal to 1 is this independent Faherian model. So we are looking at those quantities. And so we are summarizing this thing, and in the summary, okay, I have this notation: the northwest block, northeast block, southwest block, and southeast block, like that. Okay, so here is the table or plot. So what I have, if you look at this is the northwest part. So what we have here for the unsampled states, there are 7 unsampled states, and we have the weak covariate, and I'm presenting a result for this average empirical mean square prediction error. And then if you look at the northeast part, that's same thing for the average posterior standard deviation ratio. So in terms of average empirical mean square prediction error ratio, if you look at the northeast part, and there you see that there is 3 actually sub blocks there. In the leftmost part is presenting you result for the low Moran psi, and then middle one is presenting for the medium Moran psi, and the rightmost one is giving you the high Moran psi. And when you have the high Moran psi, that means that you're capturing, you have a lot of spatial dependence there. In that case, you see that the length of the bar here actually much less than 1. And the length of the bar less than 1 means that the spatial model is doing much better in predicting the population mean that we are trying to predict over the Faherian model. So here you see a lot of gain. On the other hand, if you look at in the simulation part where you have low Moran psi, that means you do not really have in the simulation good spatial dependence there. And you still see improvement, but not as spectacular over the Faherian. But still, it's like, you're getting like at least 10% improvement, and somewhere here you are getting like 40-45% improvement. So this is for the unsampled areas. This is very important because for which you really have no direct estimate. On the other hand, if you go down to this the southwest block, this is giving you for the sample areas. That means for all those states, you have actually some data, Y, but you try to improve it by using the other the states estimate Y and the covariates. And in that case, again, you see kind of similar picture where you have high Moran psi, the length of the bars kind of smaller, where you have low Moran psi, length of the bars are kind of higher. The higher the length, you do not gain much over the Faherian model. But if the length of the bar is smaller, you gain over the Faherian model. And again, when you have high Moran psi, you see that you gain some, but these gains are not as spectacular as you go to this northwest part here, corresponding to the unsampled area. So this is basically saying that you are going to gain by when you have only weak covariate. Okay, when you have weak covariate for the unsampled areas, you gain overall quite a bit. I don't have much time, so now I'm going to show you when you use the strong covariates. Okay, when you use the strong covariates, the same kind of picture, but now the gain is less spectacular. Okay, if you look at it now, again here doing the same thing for the unsampled states, 7 of those averaged over, and for the simulations about 33-34 data sets where I have the high Moran psi, a lot of spatial dependence captured by the spatial model, and there you see that the spatial models is predicting better than the phase with all these highs, all these bars, their length are actually less than 1, but not really a whole lot, but about 25% to 15% lower. So you are gaining for the unsampled areas, but the gain is less because you have good covariate. And then for the sample areas, the gain is even less because for the sample areas themselves, they are held by their direct estimate Y values, whereas for the unsampled, they did not have the direct estimate. So this is kind of, so basically showing that if you have good covariates, then your improvement by using the spatial model will be less. But if you do not have good covariates, you will gain a lot. So in summary, we propose Bayesian spatial small area estimation models. We studied 4 spatial correlation structures for the random effects. We used a hierarchical Bayesian framework, and we showed that these spatial models will have better performance, superior performance, when we do not have good covariate to explain the population mean status, and when many small areas have no direct estimates. So I will stop with that, and thank you very much for your attention and for the extra few minutes. I do not know how many minutes you gave me.
Thank you, Professor. Any queries, Professor, or researchers?
Yeah, I have a question.
Yes, please.
Go ahead. The thing is, Gauri, it's quite a convincing kind of thing. First of all, I have a feeling that if you don't use X1 at all, just use X2, you may have very similar results with both X1 and X2. That's my guess, because it seems like some sense of overfitting. I understand X2 is important, X1 is far out, but just X2 itself might be good enough rather than the joint X1, X2.
Okay, let me thank you, Malaida.
That is one question. Okay.
Thank you. So actually, if you look at it, there is a little bit of notation switch here. In the actual data analysis, X2 was the important covariate. In the simulation, X1 is the important covariate.
No, I was talking about the data analysis first.
Yeah, data analysis. Okay. In the data analysis, X2 is the more important part. In fact, if we look at the credible intervals for beta 1, that means it includes 0 actually. So
no, that I understand. Rather than what I'm saying, rather than X1, X2 both, just use X2 possibly.
Yeah. If you use X2 only, you'll get more or less similar results. Yeah.
That's my guess.
Yeah. That's what it is. But then again, since in small area estimation, we try to borrow anything just to improve, because our goal is not estimation, prediction. So we just even if X1 is not really significant, we still use it in the fitting.
Okay, that's one thing. Can you get the slide where you define all the car, L-car?
Yeah.
I could not quite get the difference. Car, L-car, SCAR, and SAR.
Okay,
I think there was one slide where you got all of those.
Yes.
Can you get that slide? That's for my clarification.
Yeah.
Nothing else.
Yeah. So these are first thing, just to clarify. These are introduced through the precision matrix. That means if you take the inverse of those matrices, then multiply by the sigma square V, that will give you the variance covariance matrix for the random effects.
Correct. Okay.
And if you see that if you take rho equal to 0, all of them will be like diagonal matrices. So inverse will also be diagonal. So basically that will correspond roughly to the Feherian model, except this conditional autoregressive, this L is, this diagonal thing, it depends on the number of neighbors each state has. So it may not be equal. In the Feherian model, we assume equal covariance, but in this case, you'll have like different small areas will have different variance, but they will have some common variance parameters.
Okay. Those are the final thing is this spatial thing. Of course, if you are within a state, I mean, geographic locations could be a very important factor, because sometimes, even if they're far apart, there are similarities and there is correlation.
Yes,
Really?
yes. Actually,
that is hard to quantify, possibly. Like,
no. Actually, due to lack of time, I kind of moved very quickly when defining.
yeah, that's right. You did some of that later.
So this W matrix, actually, it does not have to be 0, 1, and it does not. You don't have to define it in terms of only physical proximity. Okay, like boundary, sharing a boundary like that. You might have, like, you might define proximity in terms of traffic. Okay, so physical traffic. Maybe the two different airports might be well connected, like Atlanta and New York. A lot of air traffic versus maybe much less traffic between Atlanta and Columbia, South Carolina. Okay, so that way you can bring in. So you have to have some other information to define this matrix W.
Very nice. Yeah.
And
that's what
I like to make one more comment here. Those of us are familiar with Rao and Molina's small area estimation model. In their book, actually, this LCAR model, which is Leroux, L-E-R-O-U-X, Leroux introduced that model, Leroux conditional regression model. They refer to this model as special Rao Molina SRM model, like that. But since it was introduced earlier by these people, so
intra-class kind of intra-class, not quite, but similar. Not quite. Right.
Thank you, Professor. Wonderful and very interesting talk on the small area estimation.
Thank you.
Professor Gauri Shankar Datta, thank you very much for delivering the excellent talk on this. Now I'm thankful to Professor Satish Kumar for giving this opportunity, and handing over to you, sir.
Thank you, Professor Bhattacharya, for nicely managed the session and for chairing the session in a very nice way. And in fact, we are grateful to you, professors, Professor Shili Lin and Professor Deodika, for your wonderful presentations.
Thank you very much. Thank you very much for inviting me. And if anybody has any question, can send me email.
Yeah.
Also want to say thank you as well, and I posted some links to the R packages if anybody interested in that, and also the preprint. It's a before correction version. So if anybody interested in that, they are in the chat. Thank you. Thank you all.
Thank you, Professor Lin, for your support to the youngsters. And in fact, both the presentations, talks are very useful to our young researchers in particular.
Thank you.
Thank you. Thank you so much. Thank you so much for your support. And
thank you, Professor.
Thank you, Professor Bhattacharya. In fact, we have placed some as our earlier schedule. There is some slot time comes up, and we plan to maintain it as some brainstorming session. But now there is only 15 minutes time is there before the next session. That is, I hope some professors will. In my mind, Professor Ashish Sengupta probably will join by the time, and or otherwise, professors, you can give some valuable advices to our young researchers. Because while we are conducting offline conferences, there are enough time to interact with the young researchers. The young researchers will get much time to interact with the top class scientists like you. So, but here in online conferences, it is not much. That is a difficulty to them. So, if possible, you can please utilize this time to give some inputs to our youngsters. Professor Datta, you can also give some.
If anybody has any specific question, I'll be happy to do that. Otherwise, if someone is interested about the general idea about small error estimation, I can say the small error estimation is you are interested in making inference about many related population characteristics, which are like I call theta 1, theta 2, theta m. And this same problem was actually the Stein's shrinkage estimation. And in fact, all these problems in small area estimation, they are actually Stein's shrinkage estimation. Depending on how you are modeling, you can do a frequentist approach, which will give you empirical best linear unbiased prediction method for the mixed linear model, which is like, used in analyzing data from animal science or agricultural experiment like that. And like C.R. Henderson, so many years back, he used mixed linear models for animal breeding, and he developed the prediction for which cow or which animals will give either produce more meat or give more milk, like that. So you have to estimate that or predict that thing. So that prediction thing was actually the concept for best linear unbiased prediction. And you know that based on this mixed linear model, you have this variance covariance matrix. There will be variance for the random effects term, variance for the usual error terms. So those parameters you have to estimate, and they all together is going to give you a variance components model. And you estimate the variance parameter from the data. So you first pretend that the variance parameters are known, and you just come up with best linear unbiased predictor, which is in some sense like maximum likelihood estimation with penalty term for the random effects. So once you have that, you get the best linear unbiased predictor. And then you replace these unbiased unknown parameters, namely the variance components estimate, you get empirical best linear unbiased prediction. That's the frequentist method. You don't have to be a frequentist. You can even take a Bayesian approach. So what do you do for the unknown parameters? You have for the random effects, you again assume, say, for simplicity, a normality, and then you use maybe sum of square error loss, and based on the loss and assume all the random effects variances are known, you can generate the Bayes estimator of all the thetas, theta 1, theta 2, theta m. And the Bayes estimator will be essentially the best linear unbiased predictor. Okay, they will be the same for the normal case. And now you have these Bayes estimators will involve the unknown variance components. You can estimate those things, or you can put a prior distribution on those. So if you estimate those variance parameters from the data, so basically from the marginal distribution of the data. So here you have integrated out the random effects. Because you do not want to keep any unobserved latent random variable in defining your estimator. Okay. So based on the marginal distribution of the data, you estimate the variance parameters, and you plug those things in your Bayes estimate. This is going to give you what is called empirical Bayes estimator. On the other hand, if you want to be a fully Bayes, so as it is, you have already introduced the distribution of the random effects in a hierarchical setup. You can put a prior distribution for the parameters in the model, like the thing that I did here. And you might have, and if you put prior distribution of the parameters, and that is called hierarchical Bayes. It's basically Bayes. Hierarchical Bayes is basically you are specifying the joint distribution in several stages. Sometimes it is easier to specify univariate distribution over a multivariate distribution. And maybe you have some positive dependence among several components, and you can capture that thing by introducing some latent variable, which is maybe either part of the mean structure or part of the variance structure. So this is the way we basically introduce this hierarchical model. And typically, we have this hierarchical Bayes maybe in 3 steps, like y given theta, theta given the parameters beta sigma square, and then for the parameter beta sigma square. But you don't have to have in 3 steps. You can also introduce more steps there. In fact, as many steps as you think suitable, just like it's like your nested design, okay? Remember, it's kind of the nesting structure is going on in this hierarchical the modeling. So a hierarchical Bayes modeling, now again, in the Bayesian setup, you can have, if you think about the usual Bayes theorem is really nothing but the conditional distribution of the parameter given the data. So you are updating the prior distribution for the parameter in light of the distribution of the data. So if you have some known distribution of the parameter, which is the prior, and you update that thing. And sometimes you may not have good information about the prior distribution. In that case, you might use just all of them like equal distribution, which is like called like a uniform distribution or non-informative representation. And taking this thing one step, like a theta, like a probability of success, which is between 0 and 1. You can say it's like uniform between 0 and 1. Because you have no real knowledge what to. But sometimes the parameter may be not in a bounded set. It might be in an unbounded region. In that case, what does it mean to have a uniform distribution? There's a uniform distribution over a unbounded range. So that's basically called this improper uniform distribution. And I have used in my data analysis, not only me, this is typically done, improper uniform distribution on parameters like for beta and sigma square v, like that. So even though you are using improper distribution, still your Bayesian methodology is still appropriate and typically produce useful inference results. And you may not have, and I did not highlight it, when you use improper prior, one job you need to make sure that your posterior distribution is a density. In other words, that if you integrate that thing, this conditional density, it will be 1. And you need to have some condition there. And there was just one line there. I just quickly moved through that thing, okay? So those things are, but that's kind of sometimes important, but many times it's a small technical thing. And what people do, like, if you want to approximate your idea about a uniform distribution over a big range, you can take like a normal distribution with a big variance. You can plot your normal density with very large variance. You'll see that in the big part, the density will be kind of flat, and then it will disappear to 0. So that is another way you can model this uniform distribution over a big range. And people do that, so these are some useful tools one can utilize and still get, using Bayesian method, still get useful results. And these days, because of the fast computing, implementation of Bayesian methods is not really a problem. When I was a PhD student, even before my time, I'm talking about 35 years. So that time, the computing was just catching up. Okay, so their implementation of complicated Bayesian models were difficult, but it's not anymore.
Thank you, Professor. Very, very nice interpretation. In fact, it is. I think students or delegates anyone can anything have to ask. Professor Shililin, do you want to add anything?
Yeah, so I just probably want to add, since my research everything statistical genomics, I just want to add that it's a really a pitch to the young researchers and students that it's a really great area to get into. And even though my work is in a different area from Professor Dada, but I also use hierarchical Bayesian modeling because I want to incorporate 3 types of data that has not been incorporated in the literature, which is the neighborhood, that is the spatial dependency that Professor Dada has been talking about. But I also have similar single cell. So here you can think about, maybe similar states in Professor Dada's talk. And then I also have bulk data, which is like I have, not only individual cell, but I have data combining tens of thousands of cells. And this information I don't want to waste. And one of the easiest way of incorporating them is through hierarchical modeling. And so the way that I did hierarchical modeling is that I want to do shrinkage because I don't want to have a single parameter for each of the single cell and they contribute differently. I want to say that that is the reason that I'm including them is because they have similarities. And so therefore, I set up the additional hierarchy so that I can say that these hyperparameters follow some common distributions. And I'm also using flat priors, just like Professor Data, for some of my parameters, the very high level parameter that I don't really know what they should be. It's not guided by data anymore at the very final step. I'm just simply saying that I'm going to set it as a non-informed multiplier. And so that my data speak. Whatever my data tell me what they should be, let it be. Okay. And so then, hierarchical modeling in Bayesian analysis is extremely useful for data integration. And that's what I'm doing here. I'm not only utilizing its own data, I try to borrow information from everything else. And in some of my other work, I borrow across platforms. I am looking at high-C data, but I'm borrowing information from gene expression. I borrow information from epigenetic called methylation. I'm borrowing genomic annotations. Well, you tell me where are the promoters, where are the enhancers, and I borrow all the information. How do I combine them? Well, you can combine them in any way you want. But one of the easy way to combine, and that really get you to be able to model your data, is through hierarchical modeling. Okay. One of the drawbacks here is obviously computational burden. And that's one of the things that we're looking at variational base, trying to improve the computational efficiency. Thank you for the opportunity to further speak and connect with Professor Data's talk.
I like to make a small comment. So although Professor Lin and I, presented the research in 2 completely different areas, but the common theme is really data integration. We are actually utilizing data from various sources, and we try to improve the estimate of the main characteristics. And as Professor Lin said, that she does not want to use the individual estimator, she wants to shrink. And I'm also doing the shrinkage sometimes I do not have any estimator. In that case, I cannot do any shrinkage individual estimator. But when we are doing the shrinkage estimator. And one more thing, this hierarchical model, also known as conditionally independent hierarchical model. This is another popular term for the students.
Thank you, Professor Lin and Professor Datta, for your very valuable information to the student, to the young researchers, all other researchers in the area. And in fact, we have the time to move to the next session. Let us move. Professor Ashish Gupta is here to chair this session, and Professor Evans to speak. Hema, would you please introduce the chair and help the chair to do whatever manage this session, please. Ardra?
Yes, sir.
Ardra, please.
Now we have a plenary session titled Relative Belief and Combining Evidence. This session will be chaired by Professor Ashish Sen Gupta, advisor at Indian Statistical Institute, India, adjunct professor at Augusta University, Georgia, USA, and distinguished professor at Middle East Technical University, Turkey. And he is also a visiting professor worldwide, including at Stanford University, Michigan State University, University of Missouri, Columbia, etc. He has published more than 120 publications, including 12 books and volumes in multivariate analysis, directional statistics, statistical machine learning, financial statistics, and reliability inference. We are truly honored to have you, sir. I warmly welcome you to chair this session.
Professor Ashish? Professor Ashish there in the group just before. Probably the network issue. Maybe he will join. Just let us wait for 1 minute. Is online. Professor Ashish, please unmute your mic, Professor. Please unmute. Your mic is muted.
No, we lost connection also.
Yeah, okay.
The internet connection was gone temporarily. So,
okay. Okay. Professor?
okay. Can you hear me now?
Yeah.
Professor Evans, I'm terribly sorry. So this is a problem with the modern technology. And I am in Kolkata and the weather is sort of inclement here. Now we are having off and on rain. We are approaching the monsoon season. So I told Satish that this could be a problem, but he sort of insisted that I should chair this session. And you being the person as a speaker, it's my pleasure, it's my honor, in fact, to chair your session. And I also work in multivariate analysis. So for the benefit of the students and the participants, let me just give a brief introduction to Professor Evans. He's a celebrated statistician. He is known all over, and especially for the people who work in multivariate analysis. He has been an icon. And since I work in multivariate analysis, I'm familiar with some of his work. And of course, University of Toronto, we had some other top stalwarts. In fact, I had an occasion to be with Professor Muni Srivastava. Maybe, yeah, Professor Stevens, he shook his head, yeah. So he has also been like a guiding light to many of us. But in any case, without further ado, Michael Evans is currently a professor of statistics at the University of Toronto. He received his PhD from the University of Toronto in 1977 and has been employed there ever since, with leave spent at the prestigious universities like Stanford University and Carnegie Mellon University. Unfortunately, even though I was at Stanford, I don't think I ever got the fortune of meeting Professor Evans there. But anyway, both of us were with, of course, Professor Anderson and Professor Stein, and that was that is still a good department. So he's a fellow of the American Statistical Association. So youngsters, if you look up the website, this is the pinnacle award. This is the pinnacle recognition for statisticians. So I am proud to have such a person with us today. He has been the associate editor of JASA, Theory and Methods, another outstanding journal, the Canadian Journal of Statistics, and the associate editor of the journal called the Bayesian Analysis. So that means he works in a variety of areas, as you can see, JASA and Bayesian Analysis. So of course, I was very much impressed to see the later part of it, but let me finish it. He has been the president of the Statistical Society of Canada in 2013 and 14. He works in computational statistics, foundational statistics, and multivariate statistical method. Now, if you look at the foundational statistics, that's something we really appreciate. We are at the juncture of statistical paradigms. In the last few years, we have seen lots of changes, lots of new ideas, and Professor Evans has written several books. One, of course, I would recommend all our students to read, The Science of Uncertainty. Okay, and if you combine that with Professor C.R. Rao's recent publication, the book and the chance, I think all of you have seen it, so it will be also a pleasure to combine these two, and the students can learn a lot of things for our evolving statistical methodologies. So without further delay, it's my pleasure, my honor to request Professor Michael Evans to give his plenary talk. Thank you, Professor Evans. Over to you, Satish.
No. Professor Evans, please. Yeah.
Okay, so can you see my screen?
Not yet. It's taking a few seconds, I think.
Okay.
So I guess I have to say share screen, do I?
Yeah, you have to put that, click on that arrow, and it will give you share screen. Have you found that arrow?
Is unmuted. Please unmute the mic and.
Professor Evans, we can't hear you. You are not audible. I think your mic is muted.
I've unmuted, and
yeah, now I can hear now.
Okay, so can you see my screen now?
No.
Noted, person.
You can't see my screen yet.
It's better to repeat.
Have you clicked on that box with an arrow mark on it?
Yes, I have.
It opens up the window saying your entire screen.
Yep,
So you can
and there I've done that.
Right. Then it will show you several small screens. You choose yours.
Okay, I see, yes.
For that.
Yeah. You click on that and it will
Then
just give us your, yeah.
What is coming?
Okay,
Yeah,
great.
it's coming now.
Thank you very much.
Good. Yeah, very good. My pleasure. Go ahead, please.
Okay, well, thanks very much for the opportunity to speak. I've spoken at a conference from University of Kerala before, and I hope sometime in the future, and it's always been remotely, so I hope sometime in the future I'll get a chance to visit and meet people personally. Anyway, the title of my talk is Relative Belief in Combining Evidence, and here's an outline of that. 3 sections. The first 2 sections are kind of review. They're things that I've spoken on here before, but to understand the main point of my talk, I think one has to understand a little bit about where I'm coming from, because it's a bit different than other approaches to statistics. So part 1 is about a theory of statistical reasoning. Part 2 is saying something about what is statistical evidence. And part 3 is the part that I think is somewhat original to the talk today. So what is a theory of statistical reasoning? Well, I go back to one mentioned in the introduction that I'm interested in the foundations of statistics. And I think the question one has to ask is, well, what is statistics for anyway? And that may seem like an obvious question, but the answers are not so obvious, right? Well, there's questions concerning a real world phenomenon. We'll cast this from the point of view of some scientists. And there are 2 broad questions. And that's the estimation question. There's an object of interest, and based on data, you want to say something about the value of that object of interest. Or the object of interest is a hypothesis that the object of interest takes a specified value, and you want to assess what's the evidence for or against that value being the true value. And of course, this is going to be based upon data. And then what the scientist needs, what he wants, or he or she wants from statistics, is a theory that tells them how to properly collect the data, and then once you've got the data, how to reason to answer the question of interest. Now, from my perspective, there are 4 aspects that a theory of statistics needs to supply. First of all, we have to tell people, this is a scientist knows nothing about statistics, but has a bona fide scientific question. So we know, well, they're going to collect data. We have to tell them how to do that, and I'll say something about that in a minute. But first thing we have to do is we know we need more than the data. So we have to tell them how to choose the ingredients that are going to go into a statistical analysis beyond just the data. And I call that step the elicitation step. And elicitation should apply to both 2 components of what I'm going to talk about here. All the ingredients that I'm going to use are a model, a sampling model, and a prior. And I'm not going to say anything more about that today, but I have in other publications, and at least with respect to the prior. I still don't see much in the literature about how to elicit a model. How do we choose a model? Often these are just things that are chosen off the shelf. A regression model with normal error, for example. Anyway, that's one step. Secondly, we have to tell the person how to collect the data. Now, this is the design phase, if you like, because we know if data is not collected correctly, there's some suspicion concerning the quality of our inferences. And I call this step measuring bias. And it turns out that this step is before we see the data, so I call it a priori, and it's frequentist in nature, and I'll say something briefly about that in a few minutes. The third step is these ingredients that we've chosen, or the statistician has chosen, whether the model or the prior, these are subjective. And we have to check to see what is objective. Well, what is objectivity? That's a good question. There isn't really a clear definition of what objectivity means, but if the data is collected correctly, we can say, or at least hypothesize, if you like, that the data is objective. The statistician hasn't chosen his data or her data. It's driven by some other external agent, right? So what we have to do, if our inferences are going to depend upon these ingredients, so at least to say something about their objectivity, we have to check that these make sense in light of the objective data. And I call this the falsification step. And we also have to say something about how to modify the ingredients. Now, there's two parts to that. We have to check the model, and most people are familiar with that. But there's also the notion of checking for prior data conflict. And I'm not going to say anything about that here, but I have done a fair bit of work about that. And there's a number of publications there that one could look at and by the way, all these are available on my website to see how I go about that, at least. Now, one thing I leave out here is the loss function, because it turns out the theory that I'm going to describe of inference doesn't require a loss function. And there's another aspect to loss functions that I don't like, namely, I don't know how to falsify them. How do I tell from the data whether the loss function is sensible or not? And the final step here is when we're satisfied that we have a well-designed experiment, a well-designed study, we have checked the ingredients after we've collected the data that these make sense, they're not contradicted by the data, we have to say how to determine the inferences, how to answer those questions, the estimation and hypothesis assessment question. And what I want a theory that tells me, how to characterize statistical evidence. I'm not the first who has that desire, and I've listed here a number of publications by different authors, perhaps not even really starting with Alan Birnbaum, but in Birnbaum in the 1960s, was certainly concerned with trying to characterize statistical evidence via equivalence relations. Now, he did all his work within the frequentist context, and one of the reasons I've added the prior here is because I believe it gives me a very clear characterization of statistical evidence, and I'll say something about that in a minute. Anyway, there's the book. I won't go through all the references here, but I have a book in 2015 which describes in greater detail some of the aspects of the theory that I use. Now, these two ingredients that I have, the model and the prior, these prescribe together a joint probability model, right? A joint probability model for the model parameter theta and for the data x. So I'm going to state my rules of inference just for a probability model. And by the way, my priors are always proper. So I have a true probability model, joint probability model here. And there are three principles that I use. The first is the principle of conditional probability. So suppose I'm interested in whether the event A is true or not. Something has happened, right? And I want to know if the true value of what I want to know is it in the event A. But something has happened and I've observed that the event C is true. And then the principle of conditional probability, and it is a principle, it's an axiom if you like, it's not dictated to us by mathematics, is to say, well, my initial beliefs are that the A is true as P of A, I must replace that by the probability of A, given that I've observed C is true. Now here's the main ingredient, if you like, of what I want to talk about, or my inference approach, is what I call the principle of evidence. And that says that if the probability has gone up, if my belief that A is true after observing C is bigger than my belief that A is true before I observe C, then I have evidence in favor of A being true. If that probability has gone down, I have evidence against, and if it's the same, I have no evidence one way or the other, because A and C are independent, right? Statistically independent. Now, I think that's one of the most intuitively obvious things I've come across in statistics, although others may disagree, but that is where I start from. And others have agreed with that, and I've just given one quote there by the famous philosopher of science, Karl Popper, agreeing with me. People have thought about this before, often in the philosophy of science literature, not so much in statistics. And finally, I have another principle here, which I call it the principle of relative belief, because sometimes I have to order. There are alternatives, and I have to order the alternatives. And the way I'm going to choose to do that is via what I call the relative belief ratio, and that's just the ratio of the conditional probability to the marginal probability. And that's a valid measure of evidence because it agrees with the principle of evidence. There's a cutoff. If the relative belief ratio is greater than 1, I have evidence for. If there's a If it's less than 1, I have evidence against. There's other valid measures of evidence, for example, Bayes factors. Now, the Bayes factor is closely related to the relative belief ratio, but I prefer the relative belief ratio because it's simpler. It has nicer properties than the Bayes factor. How do I do it in the case of a continuous parameter? Well, it's a limiting argument, and I've outlined how I go about that here. So if I have a model and I want to make inference about a marginal parameter psi, how do I get the relative belief ratio for psi? Well, I take a limit. I'll take the relative belief ratio of a ball centered at psi, for example, with radius epsilon, let epsilon go to 0, and that relative belief ratio converges to the ratio of the posterior of psi to the prior of psi. And then I interpret the relative belief ratio in exactly the same way. Relative belief ratio greater than 1 is evidence in favor and otherwise. Now, hypothesis assessment. Well, right away, I know how to do that, right? Because I have the relative belief ratio for the hypothesis that the object of interest psi is equal to psi naught. I have the relative belief ratio at psi naught. I know whether I have evidence for, against, or no evidence one way or the other. And that doesn't really depend on the relative belief ratio. It only depends on the principle of evidence and the principle of conditional probability, actually. Any principle of valid measure of evidence will give me the same answer. I've either got evidence for or evidence against, typically. Rarely is the relative belief ratio equal to 1, but sometimes it is. But then there's another question I have to answer, is how strong is that evidence? There is no, in my opinion, I've put bold statements that might be controversial and bold, but I don't believe there is a universal scale in which evidence is measured. I have to calibrate it in some way, and that depends on context. And the way I calibrate it, not always, there's not one measure of strength, but I'll compute the probability I have in the middle of this, the posterior probability, that the true value has relative belief ratio no greater than the hypothesized value. If I have evidence in favor of psi naught, and that's a big probability, then close to 1, then I know the probability the true value has a greater value of the relative belief ratio than psi naught is very small. So I have strong belief that psi naught is the true value. And if I have evidence against, and that's a small probability, then there's a big probability that the true value has a bigger relative belief ratio, and I have strong evidence against. And there's other ways to measure strength, as I mentioned, but that's what I use. Now, what about estimate? So that's a hypothesis assessment. How do I deal with the estimation? Well, I'm just going to maximize the relative belief ratio, right? Take the supremum of the relative belief ratio of psi. And now I also, if I'm going to quote an estimate, I have to see something about the error in the estimate. And I'm going to do it by what I unfortunately have called the plausible region. There's other things called plausible regions in statistics, but and some reason I chose this. I should have chosen the evidence region. I'm going to report all the values of psi for which there's evidence in favor. And then I'm going to measure the accuracy of my estimator by computing the posterior probability of that, because that tells me how strongly I believe the true value is in there. And we're also going to look at the size. I might compute the volume of that region as well. And again, the plausible region only depends on R1 and R2. It does, even though I've expressed it in terms of the relative belief ratio, it doesn't depend on the relative belief ordering. I could also quote a credible region. The only problem with credible regions, a credible region, is I've got to make sure that the posterior content of the credible region, and this is how I form a relative belief credible region, right? Because that's what I'm going to use to form my credible regions, the relative belief ordering. I better make sure that the posterior content of that region is less than or equal to the posterior content of the plausible region. Otherwise, the credible region contains elements that have evidence against them, and that doesn't make sense. Now, here's a first link with more classical statistics, if you like. If I implement that and I want to make inference about the full model parameter, well, I get the MLE. And the plausible region is a likelihood region. Now, a nice thing about the relative belief approach here, now that's not true when we go for a marginal parameter, but then the relative belief estimate will be obtained by maximizing an integrated likelihood, right? But it's a little different than that because I've got a specific value, a specific cutoff, one, telling me when I've got evidence for and when I've got evidence against. And one of the nice things about the relative belief approach is that it's invariant under all reparameterizations, just like likelihood methods are. but a little bit better than likelihood methods because now I have an unambiguous way of dealing with marginal parameters or nuisance parameters. I just integrate out the nuisance parameters using the conditional prior given the object of interest. Now, another thing I want to mention, and this goes to the design step, is bias. And I should have put that first statement there in bold because I think it's a somewhat controversial statement because people don't do this nowadays. Bias calculations are necessary as part of assessing the quality of a study, and they're part of the design. So we do this before we collect the data, and I'll explain why. Suppose I have a hypothesis assessment problem. I want to assess whether or not psi is equal to psi naught. Now suppose that the prior probability of obtaining evidence in favor was approximately 1 when H naught is true. Well, I think you'd agree. I base that on the ingredients, the amount of data that I'm going to collect, and I do this a priori. I think you'd agree that that's not a very good approach. That's not a very good study. So I need to compute that probability before I collect my data and make sure I've collected enough data, and I'll explain why, to make sure that probability is small. I call that bias in favor. Now to do this, by the way, I also need something else, which at times I find people think of as a little bit controversial. I've got to specify what I call the meaningful difference. This is the difference that matters, so that if the distance between two values of psi, possible values of psi, is less than or equal to delta for some distance measure, that means practically speaking psi 1 and psi 2 are indistinguishable. And this is part of the application. This isn't something the statistician knows. The person who wants to answer this question, for example, a physicist wants to know the half-life of a neutron, of a free neutron, has to tell us what delta is, because there's all the measurements in the experiment are going to be taken to a certain accuracy. And this has long been a theme in statistics, although I think statistics still doesn't deal with this very well. It goes back to a paper in 1919 by Boring, who pointed out that statistical significance is not the same as scientific significance, right? So for hypothesis assessment, we compute the bias against by computing the prior probability of not getting evidence in favor of the null hypothesis when it's true. We want that to be small. Also, there's bias in favor. Namely, we compute the maximum prior probability of not getting evidence against the hypothesis when it's false. And I have to specify this meaningful difference here to do that. There's no point in, for an arbitrary small delta, it won't get something sensible. This is like a power calculation, right? And the bias against is like the size calculation. So think of bias in favor as doing something like a power calculation. And I got this, since time is a bit short, I won't go over in great detail what bias against and bias in favor is for the estimation problem, except to say that bias against, when I'm computing bias against, that's like computing a priori confidence. What's the prior probability that the plausible region, the set of psi values that are going to have evidence in their favor, that it contains the true value? And the bias in favor is like computing what's sometimes called the accuracy of a confidence region. I'm computing, well, what's the prior probability that the plausible region is going to contain the true value, it's going to contain the hypothesized value when the true value is meaningfully different, okay? And I'm expressing that here in terms of the implausible region, where the implausible region is a set of all psi values that have evidence against them. Now, both these biases can be controlled by sample size. So I can't control them by choice of prior. When I choose one prior to get the bias against down, that pushes up the bias in favor. When I choose a prior to get the bias in favor down, the bias against goes up. But I can control both of them by sample size, and that's the design aspect. And I guess, again, this statement should be in bold because it's maybe perhaps a bit controversial. The consideration of bias effectively resolves what's called the Jeffreys-Lindley paradox, which is caused by choosing an overly diffuse prior, which produces, as you choose your prior typically more and more diffuse, you get more and more evidence in favor of a null hypothesis, or the probability of the plausible region containing a false value goes up. Okay, and you have to be careful. You can't just arbitrarily choose diffuse priors because you get this Jeffreys-Lindley phenomenon, which I think is really a pretty serious criticism of the standard Bayesian methodology. The other nice thing about considering bias is that it gives a partial resolution between Bayes and Frankwitzism. Inferences are Bayesian. As I've explained already, I call those Bayesian inferences, the plausible region, its posterior content, etc. But the design phase is frequentist. So I'm in that design phase, when I'm computing these biases a priori, I'm addressing the reliability of the inferences, which is another criticism that is labeled as is directed at Bayesian inference by frequentists, and I agree with that. I think we do have to be concerned about the reliability of Bayesian inferences. Now, what about combining evidence? Well, a nice feature of this approach is now I've got a clear characterization of statistical evidence. So I can address an issue that has long been discussed in the statistical literature. If I've got two different experiments, let's say, and I have evidence from one experiment, like there's the classic case nowadays of two experiments concerned with the half-life of a free neutron, two different experiments, and they get two 95% confidence intervals that don't overlap. But anyway, the question is, how do I combine the evidence from the two studies? Or from multiple studies for that matter. I'm going to split this into two contexts. Context one, I have a collection of k inference spaces composed of all got the same data, they all have the same model, and they have possibly different priors. But I'm also going to require that the priors on the nuisance parameters, when I condition, the priors on the object of interest can be different, but the priors on the nuisance parameters can have to all be the same. Okay, now that's a lot of restrictions, but the reason I put those restrictions on, because I think there's a pretty obvious answer to the question of how I should combine the evidence in that context. Context two contains context one, but now I allow complete freedom. Different data sets, different models, different priors, but still there's a common object of interest, and we want to make inference about that common object. And now we want to know, we've got these different outcomes from different schools. How should we combine? So I'm going to talk about context one, and sometimes, obviously, the only thing we're going to have to combine here is the priors. So there's a lot in the literature about how to combine priors. Now, my contention is that that's actually putting the emphasis in the wrong place. We really want to talk about how to combine evidence. Do we really care about what getting a common prior from the different statisticians? I say no. What we want to do is we want to say, well, what is the overall evidence from all these different groups about the object of interest? So there's a number of papers I've cited there. There's a very long list about how to combine priors. And I'm going to restrict myself to what are called the power laws here. So I'm combining by taking a combination of the priors raised to some power t, and I have weights, alpha I, these sum to 1. And there's, for different choices of t, we get these different power laws for combining. And these are always valid priors, at least as long as t is less than or equal to 1. They integrate, and we have to check otherwise if t is greater than 1 to make sure it's a proper prior. So how to choose t and alpha? Well, if I choose a t power law, I've got a prior, I've got a posterior. I can compute the relative belief ratio based upon those two ingredients, and that I've denoted by RB sub t alpha psi, because the relative belief ratio depends on t and alpha. But here's what I'm going to give you my overall conclusion. The right way to do it is the linear pool. Okay, the linear pool just gives me, that's when I take t equal to 1. I'm just taking effectively, if you like, the linear combination of the individual relative belief ratios from each of the study, where the weights are given by these weights right here. Alpha I, the MI is the prior predictive for the data from the ICE study, and M1 alpha X, I should have put that there, is just the linear combination of these MIs with the coefficients of the MIs that are given by alpha I. So these give posterior weights. Now, the nice thing about that, and one of the reasons I like it, is because I'm going to give a bunch of reasons here why I believe that's the right conclusion. First of all, that's formally Bayes. If I put a prior on, and this tells me something about how to choose alpha, by the way, so I put a prior on I, psi, and x given by alpha I, pi I, and the conditional distribution of the data after integrating out the nuisance parameters, that's my joint density, then I observe the data, and I condition, I get the linear pooling relative belief ratio. And this weight here is the posterior probability of I. It's formally based, and that's not true of any of the other combination rules. Also, it's marginalization consistent. This goes back to results about combining priors by McConway in 1981. If I marginalize the relative belief ratio for the full model parameter by integrating out the nuisance parameters, I get the relative belief ratio for by linear pooling, for linear pooling as well. And that's not true for any of the other rules for combining. Thirdly, all the relative belief ratios based on the power laws are related to the relative belief ratio from linear pooling by a constant given by the ratio of these prior predictives, depending upon which combination rule. If this is a constant, right, and I'm considering this is a function of psi times the relative belief ratio based on linear pooling. And so the estimates, no matter which pooling rule I choose to use, I'm going to get the same relative belief estimate. And also, when I go to measure the strength, at least the orderings are all the same. All the relative belief orderings are the same, no matter which rule I choose to use. Fourthly, if all the studies agree that certain psi values have evidence in favor, then linear pooling includes all of those in the plausible region. So there's a consistency there, right? We'll still agree that those values of psi have evidence in their favor. And similarly, if we have all the studies agree that certain values of psi have evidence against them, so will linear pooling. In fact, more generally, linear pooling preserves consensus. So what I mean by that, if all the relative belief ratios do not give evidence against and at least one gives evidence in favor, then linear pooling will give evidence in favor. And similarly, if all the relative belief ratios give evidence against, then linear pooling will give evidence against. At least one gives evidence against. Linear pooling does not preserve independence of events for the prior, and that's one reason why people have been maybe a little chary of using linear pooling, but that's irrelevant for combining evidence. Independence with evidence means the data is independent of the parameter value. Well, then you can learn nothing about the parameter value, so the relative belief ratios are all one, and indeed the linear pooling relative belief ratio is also equal to 1. Linear pooling is consistent. As long as the models, at least one of those models is correct, will converge to the correct value as the sample sizes go up. And also the linear pooling will give the highest weight to that study where the prior gives the most weight to the true value for large values of n. But now that's context 1. Context 2, it's not so clear. But I'm going to assume a common data set because I don't know how to handle this situation yet where the data sets are different. So I'm going to assume a common data set, but the priors now don't have to be the same. But I'm going to generalize linear pooling from context 1, and that's why I put a star there, because this is not formally based. Similarly, the posterior, I put a star on the posterior because the posterior is not formally based either, okay? But it has all the other nice properties. One way to justify these expressions that I've given here is by something known as Jeffrey conditionalization. This is Richard Jeffries, not Harold Jeffries, the statistician. Jeffrey was a philosopher. There's a nice paper in JASA on Jeffrey conditionalization by Diaconis and Zabel. And the idea behind that is that the updating of the individual beliefs is done separately from the updating of the probabilities on the partition elements, right? So each of the relative belief ratios is formally based, and the posterior probabilities that goes into the linear combination, those are formally based as well, but they're done by different prior distributions, right? And this is sometimes called Jeffrey conditionalization. So you can imagine there's a convener, and the convener has weighted the individual studies according to the alpha i's, and then their prior on the data is given the study is the correct one to use is alpha I MIX. And then after they observe the data, their posterior probability is alpha I MIX divided by the linear pooling, a marginal prior for the data. And this has all the nice properties of the context one, but it's not formally based. So I guess I'm going to go over just by a couple of minutes. I won't go much more. So here's a simple example. This is where I've got 3 studies, an example where I can work out all the details in closed form. And what I've given 3 priors, location normal, I've got 3 priors. They're reasonably different. I plotted here the posterior, combined posterior, and I plotted the combined prior here. And in the paper that I cited at the beginning of this section, I've given how to elicit the priors, etc. And on the right here, I've computed the combined relative belief ratio, and this horizontal line is 1. So the plausible region, I just come down here and pick off this interval where the relative belief ratio is bigger than 1, and that's my plausible region. That's for a sample of size 10. And here it is for other sample sizes. And it does, sample of size 10, the true value is mu equal to 10. I don't always get that the true value is in there for the plausible region, but certainly as the sample size goes up, I do. And those, even for samples of size 10, I've put up here, by the way, 0.92, that's the a priori coverage probability. So it's the confidence, right? So it's 92% confidence interval for the true value. Now in context 1, all the weights depend on the data through a minimal sufficient statistic, but this is not for the model I get by integrating out the nuisance parameters. As in random effects, you integrate out the nuisance parameters, right? And you're left with a model. But that's not true in context 2 generally. So the question is, are the weights comparable? So I need to add something to Jeffrey's conditionalization. I don't know completely how to solve this problem. But in certain contexts, I do, namely when the data splits into 2 parts, where I have L of X and A of X, and A of X is ancillary for each model. And then I modify the weights that the convener uses by conditioning on getting the a priori conditional distribution of the data L of X given the ancillary. So if I apply that in the case of the location normal, I have 3 priors. They now have different, I'm assuming the models have different, they've chosen different known variances, right? So the models are different and the priors are different. And then I know immediately that the residuals are ancillary for each model, and the location statistic, if you like, is X bar. And then I get the weights are a little bit different, right? They depend upon the sampling distribution, and they depend on the prior distribution as well. And it behaves in the right way. I'm running short of time, so I have another example here for linear regression with different error distributions. I looked at normal error and t error with, made sure my t always had a variance, and I standardized the t distribution to have variance 1, so the sigma is the same parameter in all the models. And I won't go through the details there. Whoops, went the wrong way. Here's an example from Zellner in 1996, as an example that gets used a lot, and I used a conjugate prior. And here's the table at the bottom. You can see here's normal prior. I just have 2 studies here. One statistician uses normal errors and one uses t errors. And here's the degrees of freedom for t. Well, when lambda is equal to 100, there's very little to distinguish between. And these are the weights, right? I would weight one statistician is using a normal prior, a normal error, and one's using a t error. They're both using the same prior in this case. And the weights are pretty much the same, right? And the inferences are basically the same. But now, for this data set, as I increase the degrees of freedom for the t error, the normal is getting greater and greater weight. In fact, when I use a t on 3 degrees of freedom, all the weight goes with a study that used a normal prior. And when you look at the data, that's not too surprising because there's no real indication there's any problem with normal error for that model, okay, from when I do model checking. So my conclusions. Overall, we need a theory that addresses all aspects. There's no point in just talking about a theory of statistical inference. We need to include the other, that's step 4, right? We need to include the other steps as well. All these things need to fit together properly. And we also want our theory to make clear what we mean by evidence, not vague. I think we're coming to some agreement that p-values don't do a good job of measuring evidence. So that's unlikely to be our resolution of the problem, is that we're going to fix the p-value somehow, but maybe. I can't rule out that. And we need ingredients beyond the data, it seems. And to a degree, these are arbitrary. This is the thing that keeps statisticians awake at night. We know the models are not correct. And to a degree, though it doesn't make sense to say a prior is correct, we have to worry about that as well. But I say that it's not unimportant, but it's of secondary importance to having a logical framework for reasoning. And so I think what I presented, that's my thesis, that is a logical framework for reasoning. And I've also given away a methodology, which I didn't talk about today, for addressing this aspect of the model being arbitrary and the prior, somewhat arbitrary. And I didn't talk about that, but there's also ways, at least for the prior, to modify the prior that is not so data dependent, right? To fix a problem when there's, for example, prior data conflict. So we address the issues of correctness by checking these ingredients against the data. Even if the ingredients were to pass, we have to say something about the reliability. And that's an a priori consideration. We want to make sure that our biases are small. So a good study will have small biases. So, and this leads to separate but necessary roles for Bayes and for frequentism. Bayesian, the inferences are Bayesian in the way that I described. But frequentism plays a role in making sure that we can believe that our inferences are reliable. And I've gone very quickly, and I apologize for that, but this leads to what I consider a reasonably good way at this point, where there's still problems, of ways to combine the evidence from different studies. And that's my presentation. Thank you. If there are questions, I'm happy to answer.
Thank you, Professor Evans. Satish, you have to unmute your mic.
Okay.
Yeah, Professor.
I'm okay. I think it's unmuted.
Yeah.
You can hear me?
Yeah.
Okay.
Yeah, you are audible. Fine. Yeah. It's an excellent talk. We thoroughly enjoyed it. But I would not say that we could understand everything.
Yes.
There's a lot of wealth in it. A lot of research has gone in it.
Well, it's all statistics, right?
Also, of course, it's all statistics with philosophy. It's not only mathematical statistics, but also philosophy.
Yes,
a lot of
that's
into the paradigm. That's a wonderful thing. I think both youngsters and the established researchers will be very much interested in your talk. So, is there any question from the audience first? Anyone, any question? Okay, just let me quickly.
Excuse me, Ashish. Hello, Ashish.
Yes.
Can you hear me? Bimal, from the University of Maryland.
Yeah, I can hear you. Bimalda, yeah, you have a question?
I do. I'll just a comment. Professor Michael Evans. We met a few times, but long time back.
Yes, I do remember.
Yeah, Bimal Sinha from the University of Maryland. As always, your talk is excellent and a lot of new ideas. So thank you so much for sharing your thoughts with us. And I thank the organizers to be able to bring the excellent speaker in the program. Dr. Evans, thank you, sir. Thank you.
Okay. So, Bimalda, thank you for your nice input. And definitely, Professor Evans, we would like to see you in person, as you mentioned earlier. Sometimes over here, with a lot more time. Yeah, with a lot of more time for us to discuss with you. So, I just have a quick question for you. I think we should ask a question. And maybe a comment. I should not say a question. It's more like a comment. And while Bimalda is here, I think it's in his area. I was just wondering that you have given us a new paradigm I may say so, using your measure of relative belief. Okay, that's a wonderful idea, and it combines both the Bayesian as well as the frequentist paradigms to a certain extent. And now, in both these, of course, we have problems. And I just had a quick question, maybe. Again, going back to Bimalda's area, possibly. See, in the meta-analysis, for example, a problem with the model selection, which model to select. We have AICs with different types of models or different AICs. Some give us acceptance, some give us rejection. Okay. Similarly, with the prior selections, you could have the same type of conclusion. In some of the priors, you get a positive, maybe acceptance, I should say, quote unquote, and the other rejection. So how would you combine? This is like the meta-analysis. Bimalda has worked a lot in this. So I'd like to give a suggestion from you. If you use your idea of this relative belief, how would you compromise such a situation?
Well, the combining, I'm sort of ambivalent about model selection a little. One could treat it as an inference problem, right, where you put a prior on the different models and then you just apply a relative belief, right? But that's might not be what you want to do. You might have different people with different models, different priors, and that's the combining evidence approach, which I might prefer to do in that context. Now, I have said something about that today in context.
You talked about pooling. I do remember you talked about pooling. You talked about pooling in your, So that's the reason I asked.
That's right. So that's one approach. As I said, I'm a little bit, I would have to think more about the model selection aspect of things, because sometimes I think people put together models that seem to have absolutely no relationship, or they might even overlap, and then the issue of inference about the correct model, when I put it in the relative belief context, is problematical. So I'm not going to make any categorical answer. Give any categorical answer to
that. You are making a statistical conclusion, just as a statistician should do. Bimalda, any comments, any input from you?
I may mention that yesterday we had a very similar, excellent talk by Ryan Martin from North Carolina State University. The two extremes, the frequentist and the Bayesian, and all this continuous paradigm from one end to the other end. And it was very nice. Again, a lot of philosophy, a lot of math also, just like in your talk. It was kind of hard to understand.
An interesting aspect of this is that I never started out to, I started my career as a frequentist, more Bayesian, right? Yes. I never started out to reconcile Bayesian with frequentism, but now I feel I'm a Bayesian and I'm a frequentist. Yes. And I think that's a lovely place to be. And of course, Bayesians don't like it because it's got some frequentism, and frequentism don't like it because it's got some Bayesianism. But I think that's a good place to be.
I think we should follow both them. They should be 2 in 1. 2 in 1 is always a good idea.
We have a new school, Bimalda and Ivan. So I think we have a new school now. New school.
Yes.
The relative belief, of course. Anyway, I thank Satish. You have kept the very good ones to the end, for the end. I think those of us who are here really enjoyed it. And those who did not, did miss a substantial our contribution to statistics. Thank you again. And look forward to seeing you in our next meeting. Okay, over to you, Satish.
Thank you, Professor. Thank you, Professor Evans, for your wonderful talk. And Professor Ashish, nicely
you're welcome.
Make it very
so nice to see Bimalda again. Bimalda,
nice to see you.
Bye-bye. Good night, everybody.
We have to add all this comment.
And good morning in I think in Washington. Bimalda, in your place, maybe
it's now 11:45, 11:44 a.m. Yeah.
Still good morning, right?
Yeah, kind of midday, so no problem.
Bye now. Bye, everybody.
Bye.
Okay, bye. Thank you, Professor. Thank you so much. So let us move to the next session. Professor Peter Lohmander is here to speak, and Professor Naufal is here to share.
Yeah.
Ardra, please introduce our chair and then do the needful for the session, please.
So now we have a special invited session titled Optimal Dynamic Forest Fire Management Adapted to Stochastic Weather. This session will be chaired by Dr. A. Naufal, Assistant Professor, Department of Mathematics, Cochin University of Science and Technology. He has extensive teaching experience as Assistant Professor at Government Brennan College, Dharmadam, Kalashiri, Government Polytechnic College, Kannur, etc. His publications include Korokian Theorem, Study on Heisenberg Group, Functions Analytic on the Upper Plane, Study of Multiplication Operator. He has research interest in the areas of functional analysis, representation theory, differential geometry, signal processing, and wavelet analysis. So I convey my gratitude to you for your honorable presence, sir. I warmly invite you to chair the session. Welcome you, sir.
Welcome, Peter Lomand, sir. As far as I remember, last conference also I chaired this same person, Lomand, sir. Yeah. Professor Peter Lomand is the professor in Forest Industrial Economics, SLU Department of Forest Products, Sweden. And he is a prolific writer and a good researcher in the field. And he has more than 50 publications. And his main area of research includes the development of methods for optimization, in particular dynamic and stochastic decision problems. And I welcome you, sir, for the presentation on this conference.
Thank you. Thank you very much. And I have prepared my presentation as a YouTube movie, so I think I'll try to see if it's possible to show that. Yes. I share. What happens here? Aha. Okay. We see this in many levels. I have to try again, I think.
I had the same problem. When the little screen comes up, click on your presentation with inside the little screen, and then it'll come up.
Thank you. Whatever happens here, in the chat window, I wrote the direct link to my presentation. So if someone has a problem to see it through the presentation window here, you can go directly to the chat window and look for the latest link there. And just click on that, because then you go directly to YouTube. I'm trying to make this work, but I'm not sure if I will succeed. That's very strange. Maybe it works anyway, somehow. Here we go. Can you see this?
Yeah, Professor. Now it is.
Okay. Let's try. Dear colleagues, can you hear it also? I'm Peter Lomander from Sweden. Thank you for inviting me to this conference. Today, I will give you a presentation of optimal dynamic forest fire management adapted to stochastic weather. We will also get the presentation of the empirical data and background from my colleague Dr. Suri Mohammadi from Czech University of Life Sciences in Prague. This presentation is based on the following open access articles and documents. More details can be obtained from the links found below.
Somebody has their mic open.
Sir, there is echo coming up.
Somebody has their
Some
mic
kind
open.
of some kind of echo.
I think somebody has their mic open. That's the problem.
I suggest that you read the abstract at a later point in time. This presentation is divided into different parts. First, we look at the firefighting capacity optimization problem in general terms. Then we look at the general solution to the firefighting capacity optimization problem. We will look at comparative statics analysis of the optimal solution. How is the optimal solution affected by the parameters? We will then go to fire growth as a function of weather conditions. We will also investigate background to the empirical weather and fire data. We'll go to dynamic and stochastic properties of air temperature, relative humidity, and wind speed, and finally end with some conclusions. This page shows the firefighting capacity optimization problem. Forest fires have a spatially uniform probability density function. Firefighting units marked with blue balls have initial locations in a regular infinite network with roads in directions north to south and east to west. The distances between roads is small, and firefighting units can always use roads in the two directions to reach the different fires. See the purple arrows. The decision problem is to determine the optimal value of K, where the distance between the nearest neighbors is L, which is 2K. The optimal value of K is affected by many different parameters, some of which are functions of the season. For instance, air temperature, relative humidity, and wind speed. These parameters affect fire growth. We are interested to minimize the expected total costs as a function of K. Firefighting groups are located in a regular network with roads in directions south-north and east-west. The distance in one of these directions between two neighbor groups is L, which is 2K. So K is a decision variable. CI is the expected cost of firefighting capacity investment and use of these resources. And CF is the expected cost of destroyed and damaged forests, including costs of CO2 emissions. In this picture, we see CF, the expected cost of destroyed and damaged forests, and see how this is containing different parts, namely the expected cost per burned hectare, CD, the expected number of fires per time unit, capital N, and B, the expected size of burned forest per fire, where B is a function of air temperature, humidity, wind speed, and the time that the fire has been alive, where this is a function of K, and M, where M is the fire lifetime before the firefighting unit leaves the initial location and starts to move towards the fire. The expected cost of firefighting capacity and the use of these resources is the expected cost per unit times the number of units per 10,000 square kilometers. And you see the equation down where this can be transformed to a function of K. The expected size of burned forest per fire can be seen as a product of two components, namely B1 and B2, where B1 is a function of K and M, and B2 is a function of A, H, and W. Now, B1 can be expressed as a function which you see in the bottom, a quadratic function of K and M. The curious observer may wonder why B1 is this particular quadratic function of k and m. And now we look at that in some detail. First, we consider x as the east-west coordinate and y as the south-north coordinate. And we remember that the probability density functions in both directions are uniform, and we see them to the right in the graph. Our interest here is to know how long it takes for the fire unit to reach the fire. Therefore, we have to know how far east and how far north the fire unit has to go to reach the fire when they start in the corner down to the left. And we denote the move in the east direction, x, and the move in the north direction, y, and z is the total distance. And the probability density function of z is shown at the bottom of the page. When we calculate the probability density function of the distance z, we get this result. And here we see that f, as a function of z, is a triangular function. The size of a fire area is generally proportional to the square of the time that the fire has been alive, if conditions are constant during the time of the fire. So therefore, we see this expression z plus m in square used in the expression of B1. And also this is used in combination with the probability density function of z. So here we use this information to get B1. And of course we want to know exactly the value of B1. And in the following pages we'll see how we can get this as an explicit expression of the parameters. Now, finally, we know why B1 looks exactly like the quadratic function that we saw in the beginning of this presentation. And since this is a quadratic expression, we can easily take the first and second order derivatives, and we find them in the end of this page. And we also see that they are all strictly positive, which is very useful when we make the next derivations. Now we move to the general solution to the firefighting capacity optimization problem. Welcome. So this is the problem. We want to minimize C, the sum of Ci and Cf, and they are both functions of k. And we see the expression in two versions. One is more general than the other. In row 1, we have the minimization problem. In row 2, we have the first order optimum condition. And in row 3, we have the second order minimum condition. And we see that the second order minimum condition is always satisfied, which means that the first order optimum condition gives a unique minimum. In this page, we see that dc dk intersects the k axis only in one place, and that's where we have k star, the optimal value of k. Now it's time for comparative statics analysis of the optimal solution. The question is, how is the optimal solution affected by the parameters? In comparative statics analysis, we look at the first order optimum condition and we look at some change in some parameter. This change in some parameter affects the first order condition, which means that we have to change the optimal value of k star. And when we have the optimal adjustment, the first order condition is again satisfied. This way, we can determine the derivative of the optimal decision k star with respect to the parameter. These derivations, we get the conclusion that if the cost per firefighting unit increases, the optimal distance between firefighting units increases. And this can also be seen graphically. In the same way, we can derive the following result. If the cost per fire-damaged hectare of forests increases, the optimal distance between firefighting units decreases. Note that if the cost of CO2 emissions is considered, the optimal value of k is lower than if we do not care about CO2 emissions. And this can also be seen graphically. If the expected number of fires per area unit increases, the optimal distance between firefighting units decreases. And if the general fire speed parameter c increases, the optimal distance between firefighting units decreases. Possible reasons: more open terrain and/or larger amounts of dry grass or other fuels. If the fires get more time to grow before the fire suppression starts, m increases, and the optimal distance between firefighting units decreases. Possible reasons: less efficient and/or intensive fire surveillance, fog, smoke, or worse road conditions, forcing the firefighting units to decrease the travel speed. The comparative statics analysis now needs some empirical information, and therefore we will look at fire growth as a function of weather conditions. Relative humidity, air temperature, and wind speed affect the size of a burned area according to the function found here. The publication where this is developed is found to the right, and there you also find the link where you can read more about this. In the graph, you see that this function is highly nonlinear. The empirical estimations gave these results. We remember B2 as a function of air temperature, relative humidity, and wind speed. And the derivative of B2 with respect to air temperature is strictly positive. The derivative of B2 with respect to relative humidity is strictly negative, and the derivative of B2 with respect to wind speed is strictly positive. Now we use the new empirical information and come to the following conclusion. If the air temperature increases, the speed of fire growth increases, and the optimal distance between firefighting units decreases. If the relative humidity increases, the speed of fire growth decreases, and the optimal distance between firefighting units increases. And finally, if the wind speed increases, the speed of fire growth increases, and the optimal distance between firefighting units decreases. Comments on the optimization problem. Above, we have assumed that labor employment constraints are applied that require that the numbers of firefighting units at different points in time are determined before the true weather component residuals are known. Optimality conditions of the dynamically changing firefighting capacity levels have been analytically determined. The solutions have been found to be unique minima. Comparative statics analysis has been used to determine the directions of change of the optimal capacity levels under the influence of alternative parameter changes. The expected fire sizes can also be numerically approximated via random numbers with relevant correlations based on Cholesky factorization. The stochastic dynamic programming version of the dynamic investment decision problem is also possible to present based on a very flexible labor market, where the number of firefighting units rapidly can be adapted to the sequentially revealed weather situation. However, since time is limited and since such labor conditions are not relevant in many countries, this will not be presented here.
Hello, this is Zohra Mohammadi. I'm a postdoc researcher at the Faculty of Forestry and Wood Sciences at the Czech University of Life Sciences in Prague. In the project, we are working on evaluating uncertainty techniques and risk assessment methods for providing decision support in the Czech Republic forests. Between 2006 and 2020, an average of 726 forest fires were recorded annually in the Czech Republic. The total burnt area across these years was 25.8 kilometers square, and the average was 2.58 kilometers square per year. The dominant type of forest fire area burnt, and the number of wildfires from the database of the Czech Republic Wildfire Rescue Service for the study period 2006 to 2020. The forest burnt area and the number of fires were collected monthly. Climatic data, including average temperature, average relative humidity, and the average wind speed, was acquired from the station nearest the fire location using the Czech Republic Hydrometeorological Institute.
The following parameter estimations related to dynamic and stochastic properties of air temperature, relative humidity, and wind speed can be used in the firefighting capacity optimization problem. Air temperature can be considered as a sine function of time with some residuals. And here we have the PDF of the temperature residuals. Note that this function almost looks like a normal distribution. And here we have relative humidity as a function of F2. You see F2 to the right, which is a kinked linear function of time, where time is the time of the year. And you also find the residuals and the properties of them. The PDF of the relative humidity residuals looks like this, and again we almost have a normal distribution. It's even better to express relative humidity as a function of F2 and of the residual in temperature. And here we see how this works, and we see that the residual in temperature and relative humidity have strictly negative correlation. We see here that the relative humidity is negatively affected by increasing temperature residuals, which can also be expected. The PDF of the relative humidity residual looks very nice. It's almost a perfect normal distribution. The wind speed shows a very dramatic and stochastic pattern, and it's not easy to find any seasonal variation of a simple type. And here, this graph represents day numbers from January 1, 2020 until December 31, 2021, so it's 2 full years. The probability distribution of wind speed looks like this. Very rarely we have 0 meters per second, and very often we have 1 meter per second. In this area, it's very uncommon to have more than 5 meters per second. Conclusions. The optimal firefighting capacity is a dynamically changing function of several parameters. The optimal solution has been derived and presented in general form. Comparative statistics analysis has been used to show how the optimal decisions are affected by parameter changes. Since the optimal decisions are functions of many local cost parameters, and since different regions have different and dynamically changing weather parameters, the optimal capacity solutions are not the same in different regions. The general approach presented here should be possible to use in most countries and regions of our world. Thank you very much for your time and the most interesting conference.
Hello, are there questions from the audience? Any questions? If there are no questions, let us thank the speaker, Professor Lomander, Peter Lomander. Thank you very much for the wonderful talk. Thank you, sir.
Thank you, Professor Lomander, for your wonderful talk, and thank you, Naufal, Professor Naufal, for chairing this session. Thank you so much. I hope we can the delegates can ask questions, if any. We can contact Professor Lomander through email or other way. Anyway, let us we expect your support in future also. Let us and now it is too late. Let us conclude this session. Today's session, we can conclude here, and tomorrow morning they can please everyone. We request everyone to meet by 8. You can join by 8:30, and from then onwards the sessions will be there. In this same link, you can use the same link on platform, and there are several parallel sessions also there tomorrow. With expecting your support, just let us conclude the session. Thank you so much. Thank you, Professor. Thank you. Thank you all, and good night to all. To especially those. Thank you, Professor. Bye. Bye. Yeah. Bye.